So good morning, everybody. I will be chairing the session today up to the coffee break. And let me go straight to the first speaker, who is Stephen Louis, who doesn't need any presentation in this community. And he will tell us about electron correlation in multiparticle excitations, in time-dependent phenomena and superconductivity in materials.
Okay. Is this on? Could you hear me? No? Yes? No? No. All right. Thank you very much for the introduction, Amelia. And first of all, I'd like to thank all the organizers for inviting me to give this morning's talk. So what I would like to do today is to share with you some of our recent work using many-body perturbation theory to study electron correlations in a couple of topics: multiparticle excitation, time-dependent phenomena, and superconductivity in some materials. So this is going to be the outline of the talk. I will begin with looking at interaction and time-dependent phenomena in photophysics of atomically thin 2D crystals. That would include looking at correlated multiparticle excitations, such as trions and biexcitons, and exciton-enhanced nonlinear optical responses, such as shift current. And then we will look at how correlation influence experiments, such as results from experiments such as pump probe transient optics and time-dependent angle result for the emission spectroscopy. And finally, as the last topic, I will look at the role of self-energy effects in the electron-phonon coupling and superconductivity. So let me begin with this topic of try to calculate from first principle using many-body perturbation theory of non-equilibrium phenomena and excitation going beyond 1 of 2 particle excitations. So if you want to look at this kind of phenomena, one has to go beyond the standard GW and GW beta salpeter equation approaches. For example, if we're interested, let's see. If you're interested in correlated high number particle excitations, such as trions and biexcitons, then one has to actually investigate the interacting 3 and 4 particle Green's functions. And if you're interested in time-dependent and high-field phenomena, such as those measured in pump probe experiments, nonlinear optics, or even field-driven transitions, then one should look at the explicit time propagation of the Green's function. For example, looking at the GW approach and look at this time propagation using the non-equilibrium Green's function formalism. So let me begin by looking at correlated multiparticle excitation in 2D systems. As you all know, interaction is enhanced in 1 and 2 dimensions. So it's not surprising, experimentally, one finds that multiparticle excitations are actually prominent in those measurement of those systems. The example I give you is biexciton on monolayer tungsten diselenide. Plotted here is the photoluminescent spectrum. And what you see here is this peak labeled XX, which actually grows with the intensity of the excitation light. And this peak has been identified as a biexciton, a combination of 2 excitons, and it has been well studied experimentally. And this kind of phenomenon, in fact, are of fundamental and practical interest in a number of other areas, such as exciton condensate and the fission of a single exciton into 2 excitons in organic crystals, for photovoltaic applications. So in terms of theoretical approaches, you were interested in the quasi-particle excitations, you had to look at the single particle Green's function. Say within the GW approach, then you solve this single Feynman diagram where that dashed line is the screen-Coulomb interaction. For optical property, including electron-hole interactions, then one has to solve two Feynman diagram using the beta-Salpeter equation approach. For biexcitons, which is a four-particle excitation, then in fact one has to look at solve something like diagrams which look like this, and there are 36 such diagrams involving four particle lines and their interactions. This looks formidable, but in fact, recently we were able to formulate it and develop the computer code to do such calculations. So let me give you some results. This is to look at trions and biexcitons in monolayer tungsten diselenide, which is a semiconductor, and the low energy excitation in this semiconductors are at the K and K prime valley, just like graphene. Here are the calculated results compared to experiment for the binding energy of a negative trion and a biexcitant. So there are no adjustable parameters in the calculation, and you see that there are actually rather good agreement between theory and experiment. In fact, these are the first fully ab initio many-body calculation of this kind of excitations. Our results shows that there's a very rich energy and spin valley level structure for these excitations. They are rather high energy phenomena because the binding energy is in the order of few tens of milli-electron volts. The results elicit experimental observation and in fact give some new predictions. So for example, for the biexciton in this system, traditionally it has been thought as an exciton which is a combination of a intra-valley bright exciton and an intra-valley dark exciton. However, from our calculation, what we find that's really not the case. The biexciton that was measured here, in fact, is an biexciton that combining a intra-valley bright exciton and an inter-valley dark exciton. And this kind of configuration was ignored previously because of the neglect of important electron-hole exchange, the effect that come in on all those diagrams, 36 diagrams. Now let me turn to time-dependent and nonlinear phenomena. Here we have to look at non-equilibrium Green's function and solve it in the time domain using the Keldysh contour. For the experts in the audience, the method we use is one we developed with a time-dependent GW that is within the adiabatic approximation for the self-energy and propagating it in real time with the density matrix approach. Now, the advantage of this approach is that it makes the calculation much more doable. It captures the self-energy and excitonic effects. We expected it to be relatively accurate in the weak and moderate field regime. Within linear response, it is equivalent to the beta-Salpeter equation approach, in which we test that in fact is the case. However, if you do time propagation, then you get our nonlinear responses and time-resolved phenomena, including excitonic effects. And I will show some sample of this. And because of this approximation, one can now perform the time propagation with a single time variable as opposed to time to the third power in the full Kadanoff-Bay equation approach. So let me use shift current as an example. Shift currents are photo-induced DC current in a non-central symmetric crystal without having a PN junction. It is a second-order optical response that is with an incoming AC field, you could generate a DC current, and it is related to band topology, that is the shift of the intra-shell coordinate of the electron from the optical excitations. Now, previously one could do an independent interband transition type of theory for this kind of effect, but for 2D materials, excitons are so important that we decided to use this time-dependent GW approach to look at the problem. So here is some results we obtained for shift currents in monolayer germanium sulfide. Plotted here is one of the coefficients here that relates the optical field to the DC current, sigma yxx. So the blue curve is when we turn off electron-hole interaction in the time-dependent AGW approach, and then the red curve is when we include the electron-hole interaction. So you see that there are dramatic changes in the spectrum. Excitonic effect in this material enhance the shift current in order, at certain frequencies by orders of magnitude, and completely changes the shape of the spectrum. This is quite interesting because excitonic effects is so important in 2D materials. One would expect that this kind of effect to be very large in any kind of 2D semiconductor. And in fact, we also find that for nonlinear response, such as some frequency or this harmonic generations, you can also get order magnitude enhancement. Another very interesting result is that, that you get DC charge transport with illumination inside, frequency inside the gaps. So this phenomena would be extraordinarily interesting and important in possible photovoltaic applications. Here's an example of second harmonic generation for the same system. What's plotted is chi2, and again, the blue curve is without including electron-hole interaction, and the red curve is including excitonic effects. So again, you see that there can be orders of magnitude enhancement in the nonlinear optical response. Now let me turn to field-driven phenomena within time-dependent ARPAs. Normally, you think of probing excitons by optical means, but recently we and others have realized that you could also probe them using time-dependent ARPAs. The idea here is that you excite the light with a pump optical photon, so you put the system in a non-equilibrium state, and then later you probe it with ARPAs. So here's an example for the case, again, monolayer germanium sulfide. What we do here is to simulate this pump hole experiment by shining light first with a frequency that corresponds to the permanent first excitation energy of the system, and then we probe the spectral function after a certain delay time. So on the left here is the upper spectrum when we neglect electron-hole interaction in the calculation. So what you see is as expected. These are the occupied bands, and you also see some of the unoccupied conduction bands because the pump photons. When we turn on the electron-hole interaction, then what you see is this spectrum, which is quite different. You see some novel features now in the unoccupied state energy regime. And in fact, you see several, oops, wrong direction. Several series of features, new features, and those are excitonic features. And by reading out the energy position, you get out the exciton excitation energy, and the spread of the intensity here, in fact, give you information on the wave function of the exciton in K-space. That is, you could think of an exciton as a linear combination of free electron holes, and this intensity here, in fact, is related to this coefficient here. And this kind of experiment, in fact, is now doable in the last few years, and people have seen that experimentally. So by doing this kind of calculation, you could directly get out the exciton energy and its wave function. Another interesting feature is that you could see renormalization of the bands due to photon excitation. And if you increase the intensity then of the pump light, you could see more dramatic renormalization. And this is given by this example here, looking at the same time-dependent outputs for the case of a monolayer monodisulfide. The A exciton, the parameter exciton in this system, is at 1.8 electron volt. Here, we pump the system with frequency, photon frequency at 1.7 electron volt, which is slightly off resonance. And you do see this excitonic feature, and this gives you the excitation energy, and not much happened at the top of the valence band. But if we now do the same simulation and use a frequency exactly at resonance, then you see, again, this excitonic feature, but the dispersion now changes, and the top of the valence band, in fact, is also changed dramatically. And this kind of camelback feature that you see both on the top of the valence band and that of the excitonic features, in fact, is a exciton polarization-driven exciton Fouquet effect in this system. Now let me talk to you about another very interesting optical phenomena in 2D materials. Now we look at bilayer system. Here is for the case of molybdenum selenide and tungsten selenide. And what happened here is that experimentally, what one finds is that you photoexcite layer A, then you actually could influence the optical response of layer B in a very, very quick time scale. So the time scale, in fact, is in the order of hundreds of femtoseconds. And traditionally, in the literature, this has to be interpreted as a single particle transfer, a charge transfer mechanism. That is, when you do this excitation, you create holes here, and this two system forms a type 2 band alignment system. The hole gets transferred here, and then when you try to probe layer B, that will be influenced. And it turns out that if you do a DFT kind of calculation, the coupling between the top of the valence band of layer A and B are actually very, very weak. And it cannot give you this fast time scale, and you have to invoke phonons. But even with phonons, it's still quite slow. And this got us to think that maybe excitonic effects is important because exciton is so dominant in those two systems. So what we did is to apply this kind of, to this system, the TD-AGW method. And the reason is that if you create excitation in layer A, then there actually a continuum, a bunch of interlayer excitons that are in resonance with the excitation in one of the layers. So you could quickly transfer intralayer exciton to an interlayer exciton, and that can lead to a change in the optical response of the unpumped layer. And I won't have time to go into the details, but basically by calculating the time propagation of the Green's function, you could get out the optical response. And when we do that, what you find is the diagonal element of the density matrix, which corresponds to the occupation of the single particle state, has a very slow time scale as a function of time after the pump. But the electron hole coherence, the off-diagonal elements of the density matrix, which describe the transfer of an interlayer exciton to the interlayer exciton, actually go through a very fast time scale. And if you look at directly what the calculated change in the absorption of the system, that is, you pump layer A and then you measure layer B, then what you find is that there is a very fast change in the absorption when you include the full electron hole interaction effects. And if you do the same calculation within TD hot treat, then you don't find any change at all in this time scale. And the rise time that we calculated from our approach is in the order of 300 femtoseconds, which agrees quite well with experiment about 200 femtoseconds. So this is an alternative explanation in addition to the phonon charge transfer, induced charge transfer mechanism. Now let me spend the next 3 minutes maybe to talk about electron-phonon coupling. So as we all know, most of the calculation for electron-phonon nowadays are done within DFT, which are basically describing the coupling of the Kohn-Sham equation electrons with the phonon field. This had worked very well for many materials, but it failed for some. What we have done recently is to develop a method to include self-energy effects at the GW level to the electron-phonon coupling using a linear response theory similar to the density functional perturbation theory. So basically, what you do is for the electron-phonon matrix element, you take away the term that involving VXC and replace that one term involved with the self-energy within linear response. And what you find is, in fact, that correlation effects, self-energy effects can change G by as large as a factor 2 in some materials. So here's some results we have obtained for some metals, series of metals. For simple normal metals, the FPT and GWPT basically give you similar results. However, for some metal oxides, like this one, you could have a difference of factor 2 in the coupling constant lambda. And this change, enhancement in lambda by a factor 2, in fact, explains the very large TC of this bismuth potassium, barium bismuth potassium material, and whereas DFT cannot explain TC at all. And similarly, self-energy enhancement of electron-photon coupling could also explain the king that one sees in the photoemission experiment of the cool plates. And that enhances the king by a factor of 3. In terms of a very recent example, in the case of superconductivity in the Nick plates. And this is a system people are very interested in because it's an analog of the cool plates. And if one could make it and make it a superconductor, then you might find another system with unconventional superconductivity. However, well, this has been done very recently in the last 4 years or so, 3 years. And what's found is TC in this material is quite high, 23 degrees. But if you do DFT and the BCS type of phonon-induced superconductivity, the predicted lambda is 0.2, and TC is much less than 1. I see that the chairman's getting nervous. So basically, I just give you a very brief version of what happened here. What happened is very interesting. It turns out Nick plates is very different from the Q plates. It's a 2-band system. It has the nickel D band near the Fermi energy, but also there's a rare earth band near the Fermi energy. So the band structure within DFT is given by here. If you do a GW calculation, those 2 bands swap in position and changes the Fermi surface dramatically, and also the electron-photon coupling constant. And here is the LRS equation calculated, and with DFT and also with this GWPT. And what you see is a factor of 5.5 enhancement in the coupling, coupling constant. And this comes from the fact that you introduce a rare earth band in the system, and that rare earth band gives you a huge lambda, and you have a bimodal distribution of lambda. And then we solve the k-dependent LRS equation and find out predicted a very interesting superconductivity in this material. And we're actually sticking our neck out now. We're making this prediction that this material is a 2-gaps S-wave superconductor. Here is the distributional gap at low temperature. For the rare earth bands, it's very high, the gap. But for the nickel band, it's very low. And in fact, the gap distribution as a function of temperature is given here. And we have a TC about 22 degrees, which is very close to experiment. And we also, so it's very, very different from the Q plate. And our results could also explain the tunneling experiment data. The tunneling data give you, for the clean sample, give you something look like that. Clearly shows 2 gaps. And then for other dirty sample, it has a V shape. And people interpreted this V shape as being D-wave. But it turns out that you take this 2-gap model and broaden it with impurity scattering effects, then you get the V shape. So I think I'm over time. Let me leave you with this message saying that many body perturbation theory with screen Coulomb interaction to the n-particle Green's function can be a powerful, versatile approach for understanding and prediction of a variety of spectroscopic properties and field-driven, time-dependent phenomena for real material, but you have to treat the interaction appropriately for appropriate phenomena that you're interested in. So as the very last slide, I want to acknowledge my excellent postdoc and student who did all the work, and I leave you look at this slide. Thank you very much for your attention.
Thank you very much for this fascinating talk. So we have time for a few questions. Yes.
Very nice talk.
Thank you.
I just want to ask about the neglect problem. And,
Yes.
Yeah, you have this two gap, as you said, but the symmetry of both the gaps, according to you, are S wave, right?
That's correct.
But if I understand correctly, one of the band is actually coming from nickel x square minus y square.
Yes.
So the expectation was that will be D wave. So do you have any comments on it? Of course, you say that the V shape comes from the disorder and etc.
Right. What happened is that, according to our calculations, there's no OPUS experiment yet, and there's no real detail of tunneling with the phase experiment measurement. So according to our calculations, superconductivity is driven by the rare earth band. And that has a very strong electron-phonon coupling due to the fact that the self-energy effects bring it to the Fermi level, Fermi surface, that band, and also enhances the electron-phonon coupling. So the driving force is the rare earth band, and that's why it gives you a two-gap S wave and large TC. Mm-hmm. So all these predictions remain to be verified by experiment.
Thank you.
Thank you. And thank you very much also from my side. So very beautiful talk and very, very clear. Yeah. Very nice. Let me continue on Tanushree question, because I was also curious about the doped neodymium nickelate. If I remember correctly, experimentally, the Hall coefficient changes sign as a function of temperature, right? Mm-hmm. Suggesting that the carriers actually change from electron-like to hole-like. Do you have a view on this in this context?
We have not looked into that very carefully, but there are many pockets in the system. There are electron and hole pockets and so on. So it might be reasonable using the kind of band structure we have with the GW approximation to analyze that, but we haven't done that.
Question here.
Thank you, very nice talk. Thank you for your very nice talk. I have a question about your correlation effect of the shift current.
Yes.
It's a germanium sulfide. I saw that the enhancement is okay, but there are some sign change if you include the exotonic impact.
Yes.
Do you know the why? It's very strange.
Oh, it's in general, there will be sign changes, even in the independent particle picture of shift currents. Depending on the frequency of light, even with the same polarization, you could change the direction of the current. And that's related to the shift vector in the the band structure, which is related to the Berry connections and so on. So that's not surprising, because you see that even in the independent particle picture. Now, the two dominant peaks below the gap in the plot that I showed you changes sign, and that's related to the nature of the two excitons. One is the A exciton, and the other is the B exciton. And again, if you change the polarization of the light, you could actually change the sign of the coefficient. And that's very exciting, because one of the things that we are doing now with Mike Cromie, where he could try to measure the current on a 2D material, and by changing the frequency of light, we may be able to see this effect.
Well, I think we have to move on in the interest of time. Thank you very much again, Steve. Our next speaker is Johannes Lischner from Imperial College, and he will tell us about large metallic nanoparticles.
Perfect. Thank you very much. And I also would like to start by thanking the organizing committee for this opportunity to present the research of my group on modeling the hot carrier generation in large metallic nanoparticles. So this is a talk about so-called nanoplasmonic hot carriers, where one exploits the capability of metallic nanoparticles, such as a gold nanoparticle, to convert the energy of light into energetic or hot electrons and holes. And what we mean by hot is typically a large energy compared to the thermal energy. And such hot carriers can be very useful for energy conversion applications, such as photocatalysis, photovoltaics, also in sensing, and there's many other applications. So here you see just one example where one basically uses a gold nanoparticle to convert light into holes and electrons. The holes can do an oxygen evolution reaction, and the electrons can be transferred to a titanium nanoparticle and then do a hydrogen evolution reaction with basically what's happening is water is split into oxygen and hydrogen. So this is one of the ideas where these nanoplasmonic hot carriers can be very useful. So where does this ability of the metallic nanoparticles come from? And that has a lot to do with this concept of a localized surface plasmon. So localized surface plasmon is a collective oscillations of all the conduction electrons inside the nanoparticle, and it is responsible for the very large absorption cross-sections that we find in metallic nanoparticles when the frequency of the light is resonant with this natural oscillation frequency of the electrons, and you get a big peak in the absorption spectrum and very large light absorption. But what happens, much like in a pendulum that sort of slowly loses energy due to various damping mechanisms, is that also this collective oscillations of all the electrons is a damped oscillation. And what is happening is that the energy is converted from the collective motion of the electrons into single hole pairs by something that is known as the Landau damping mechanism. And we can visualize it in the following way. So here we see sort of the electrons are sort of pushed down by the applied electric field of the light, and that creates an internal field, and this internal field in turn sort of gives rise to excitations of electron hole pairs, which then constitute this damping channel. And just as sort of a concrete experimental example, so here is a work from the Halos group at Rice University, who demonstrated that they can use these hot carriers to dissociate hydrogen on a gold nanoparticle. So here is the gold nanoparticle. And what's happening, they claim, is that the hydrogen molecule adsorbs to the surface, and then hot electrons tunnel or hop onto the hydrogen, and which then gives rise to the dissociation. And this is a chemical reaction that is very difficult to induce by other means. Okay, so this is sort of the experimental motivation. Now, of course, what I would like to do is develop a way to model these kind of hot carrier generation processes. So how do we go about doing that? So the first thing we do is we map this very complicated problem of interacting electrons onto a problem of non-interacting electrons moving in an effective potential, which of course is very familiar to all of you. But this effective potential is slightly different from what you're used to. So of course there will be a potential arising from the illumination. This is just the electric field from the light, which polarizes the electrons in the nanoparticle. And this polarization gives rise to a restoring force arising from electron-electron interactions. And so this gives then rise to an induced electric field inside the material. And we can calculate the total potential arising from these two contributions using electrodynamics. And here For example, for the special case of a spherical nanoparticle, one can solve the Maxwell equations within the so-called quasi-static approximation analytically and gets a solution for the potential, which is shown here, which involves the dielectric function of the bulk material, which we, for simplicity, just take from experiment. Okay, so once we have the effective potential in which the electrons move, we can then go ahead and calculate the rate at which hot carriers are generated simply by evaluating Fermi's golden rule, which is shown here. So here we calculate the rate of electrons with energy E that are generated by photons of frequency omega. And this has all the usual ingredients. There's a matrix element squared of the effective potential, an energy conserving delta function, some occupancy factors, and then there's some delta function which basically tests if the electron that is generated has the energy that we're interested in. So fairly standard textbook stuff. Now, to evaluate this expression, all we need, of course, are wave function and energies of electronic states in a nanoparticle. And to get those, of course, what we need to do is do some quantum mechanics and solve the Schrödinger equation, which is shown up here, which means we have to diagonalize a Hamiltonian, which typically scales like the third power of the linear dimension of the Hamiltonian. But the problem that we're running into very quickly is that the linear extension of the Hamiltonian, the size of the Hamiltonian, increases very rapidly with the size of the nanoparticle. So if you do standard atomistic approaches like ab-initio density functional theory, you can get to nanoparticles with maybe a few thousand atoms, maybe 10,000 atoms. But experimentally relevant nanoparticles in this field of nanoplasmonics typically contain millions of atoms. So there's a big gap between what we can simulate and what's being relevant to experimentalists. And this is why many researchers in this field actually use non-atomistic approaches, so gellium or spherical well models, which you can solve for much larger nanoparticles. But these come, of course, with a lot of problems. You don't really have material-specific band structures, no D-bands. You can't really describe the different facets that the nanoparticle can have. So a lot of limitations. So there's a problem. How can we bridge this gap between, and model the electronic structure of large metallic nanoparticles? And the way we tackled this problem is with a set of methods which are known as spectral methods. And I'll try to explain briefly what those are. So we go back to Fermi's golden rule, which I'm just copied here, exactly what I showed you a couple slides ago. And we rewrite it a little bit. So what we do is we insert two delta functions, and we also add two integrals. So we haven't done anything, so nothing's changed. But now we can define this function phi here, which is sort of a sum over all the transitions, some matrix elements, and some delta functions. And this function phi contains all the information about the electronic structure of the nanoparticle. The rest is just delta functions and occupancy factors. Now, phi, we can now expand in terms of a series of Chebyshev polynomials. So it will look like this. So there's two energy arguments. So we'll get sort of two Chebyshev products of two Chebyshev polynomials. And there'll be sort of some coefficients mu, mn, which will be frequency dependent. And it turns out that we can write these coefficients in the following way as a trace of four operators. Two of these operators are Chebyshev polynomials of the Hamiltonian, and the other two operators are the effective potentials. So this is what we need to evaluate. And to do that, we use a fairly well-known trick where we approximate the trace by the expectation value of a random vector, which becomes more and more accurate as the nanoparticle gets bigger and bigger. All right, so we need to evaluate this expectation value of these four operators between a random vector. How can this be done? So to do this, we basically exploit the recursion relation of the Chebyshev polynomials. And we define this vector Vn, which is the random vector acted upon by the potential and the Chebyshev polynomial of the Hamiltonian. And if we have Vn, then the coefficient that we want to calculate is just the overlap of Vn and Vm. And so here is basically how we calculate these vectors. And this is just using the recursion relation of the Chebyshev Hamiltonians. So what we need to do then to generate these coefficients is basically to act repeatedly on the random vector with the Hamiltonian. And this is very efficient if the Hamiltonian is sparse. So what we do then is to use tight binding with hopping integrals fitted to ab-initio band structures. And we use a model where we have 9 orbitals per atom. So for the case, if we want to model a silver nanoparticle, it'll be 5 4d orbitals, 1 5s, and the 3 5p orbitals. And that will give us a relatively sparse representation. And this then allows us to model hot carrier generation rates in nanoparticles containing millions of atoms. So let me show you some results that we can obtain with this method. The simplest kind of system that we can look at are spherical nanoparticles. So here we're looking at spherical gold nanoparticles and look at the size dependence of the hot carrier generation rates. So here on the x-axis, you have the electron energy. 0 is the Fermi level. The blue curves are the generation rates of the holes, and the red ones are the generation rates of the electrons. And the different panels are the different diameters of the nanoparticles, 2, 4, and 8. And we're looking at light at the Plasmon frequency of a gold nanoparticle in vacuum. So this is the absorption spectrum here. And we're looking at the peak. And what we can see immediately is that for the smaller nanoparticles, which contain a few thousand atoms, there's a lot of peaks which arise from quantum size effects. So what this tells us is the nanoparticles that we can typically model with ab initio methods suffer quite severely from these finite size effects. And only if we go to bigger systems containing about 10,000 atoms or more do these peaky distributions merge into something relatively smooth. How do we understand these more smooth distributions for the bigger nanoparticles? For that, we quickly need to remind ourselves of the band structure of gold, which has sort of a set of bands with sp characters, which are dispersive and cross the Fermi level. And there's another set of less dispersive d bands, which start about 2 eV below the Fermi level. So with this in mind, we can now try to understand these hot carrier generation curves. So there's one set of peaks, which I've sort of indicated by these green arrows here, which arise from interband transitions, which are transitions from a D band to an SP band. And you can see that these interband transitions generate very energetic holes, but the electrons are very close to the Fermi level, which means they're not very energetic. But there's another set of peaks which are indicated by these orange arrows, and these arise from what's known as intraband transitions. So these are transitions starting in the SP band and ending up in the SP band. And these transitions are forbidden in the bulk, but in a nanoparticle, because you have a surface that breaks translational invariance, they are allowed, and they give rise to energetic electrons, but relatively unenergetic holes. We can also look at the frequency dependence. So here we're just flexing our muscle a little bit and look at a nanoparticle that now contains more than 1 million atoms. And we can basically see as we have more energy available and higher frequency photons, we can excite sort of a broader range of hot electrons and hot holes. We can also look at other materials. So here we're looking at a silver nanoparticle. And because the D bands in silver are further from the Fermi level than in gold, you can see that the peak from the interband transitions is farther away from the Fermi level but otherwise it's quite similar. Okay, so far I have told you about spherical nanoparticles, but one of the sort of cool thing about the nanoscale is that you can make nanoparticles in many different shapes. So here I'm showing you some experimental images from my collaborator Emiliano Cortés in Munich, where he's prepared nanocubes of gold, rhombic dodecahedra, and octahedra of gold. And what is interesting is that these different shapes also expose different facets of the. So you can see that the nanocubes expose a 200 facet, the rhombic dodecahedra expose a 110 facet, and the octahedra expose a 111 facet. So there's a close connection between nanoparticle shape and the exposed facet. And then what they did is they used these nanoparticles to reduce carbon dioxide electrocatalytically. So here's the experimental setup. It's quite complicated, but we don't need to understand all the ins and outs. So what they do is they feed some CO2 into the chamber. This is our working electrode where the gold nanoparticles are located, and then they basically convert the CO2 with some electrons into CO, and then the CO is sort of analyzed in a gas chromatograph, and everything's connected essentially to a battery. And they can do these experiments with a lamp on or in the dark. So first, let's look at what happens in the dark. So on the x-axis here is the applied potential, and on the y-axis is essentially the efficiency of CO2 conversion. And what they see is that the best conversion rate is for the rhombic dodecahedra, while it's somewhat lower for the cubes and the octahedra. And this is consistent with what's known both from experiments and DFT calculations, that the smallest activation energy for CO2 reduction is on the 110 surface. Okay, but this is in the dark. So now let's see what happens when they turn on the light. And what they see are these red curves. And basically, you always see an enhancement. But this enhancement is much, much stronger for the cubes and the octahedra, and only relatively little for the rhombic dodecahedra. So this is something that we wanted to understand. And what we did is we carried out some calculation where we created some models of cubes, octahedra, and the rhombic dodecahedra, each containing about 200,000 atoms. Now, of course, we can't solve the Maxwell equations analytically anymore as we could for the spherical nanoparticles, so we used the finite element method as implemented in the COMSOL package, and then we calculate the hot carrier generation rates for these different shapes. And this is what we get. Yes. Just by looking at these hot carrier generation rates, it's very obvious that there's large generation rates for the cubes and the octahedra, and significantly smaller generation rates for the dodecahedra. So this is consistent with the experimental findings. And when we integrate these curves and look at the total number of hot electrons that are generated in these different systems, again, we see similar and large excitation rates for the octahedra and the cubes, and much smaller generation rates in the rhombic dodecahedra. So this is basically consistent with experiments, and if you want to understand where this difference is coming from, this is essentially, and we're still working on sort of figuring it out in detail, but a big part of the story is the electric field enhancement that you get in the different shapes. So here is our plots of the electric field enhancement in the different systems. So each graph is a cut through a different slice of these cubes. But the bottom line is you see a lot of red, which corresponds to high electric fields for the nanocubes and also the dodecahedra, but much less red for the rhombic dodecahedra. So the electric field enhancement is much larger for the top and the bottom row, which then translates into higher hot electron generation rates. The last part of the story that I want to tell is to look at more complicated architectures at the nanoscale. So beyond just looking at different shapes, you can play even more complex games and try to create different nano-architectures by combining two different materials. In particular, one idea is to combine a plasmonic material, like gold, with a good catalyst, like palladium, and look at these systems for the conversion of formic acid into hydrogen. In particular, these guys in Munich looked at 4 different architectures. 2 of them are core shell nanoparticles, where the gold is in the middle, and it's surrounded by a thin shell of the catalyst. And either it's the pure catalyst or an alloy of gold and palladium. Or the second class of systems are these so-called satellite systems, where they have a big gold nanoparticle that is decorated by little nanoparticles of the catalyst, or in fact, little nanoparticles which themselves are core shell nanoparticles. And then they play the same type of game and look at the enhancement of the chemical activity in the light, and they see the biggest enhancement for these satellite systems and much smaller enhancement for the core shell nanoparticle. So again, this is something that we wanted to study, and so we looked at these 4 different systems here. Just a plain palladium nanosphere, a gold palladium core shell nanoparticle, a satellite system, and then a satellite where the small nanoparticle is itself a core shell system. And we modeled these. Again, we calculated the quasi-static potential using the finite element method for the full system, consisting of both the palladium and the gold part. But then for the hot carrier generation part, we only evaluated the hot carriers that are generated in the palladium. And this is our result. It's very obvious that the largest generation rates are obtained for the 2 satellite systems. So the biggest generation rate is where the satellite is itself a core shell nanoparticle. The second one is the simple satellite systems, and the pure palladium nanoparticle and the core shell are down there, so much, much smaller. And again, this is, at least this trend is consistent with what they see for the experimental enhancements when they turn on the light. And again, we can ask ourselves, where are these enhancements coming from? And again, a large part of the story is electric field enhancements, because you get very large electric fields when you have small gaps. So here you have, in one satellite, you have a small gap between the palladium nanoparticle and the gold nanoparticle. And for this other system, you could say that the palladium is sort of in a gap between 2 sort of gold antennas, which leads to an even larger electric field enhancement, which again then translates into high hot carrier generation rates. All right, so this was all I wanted to say. So I've shown you a new atomistic approach that allows us to look at hot carrier generation in large metallic nanoparticles. And I applied this method to 3 different systems. The first one were spherical nanoparticles of gold and silver, where we looked at the competition of interband and intraband transitions as function of the nanoparticle size. Then we looked at the effect of the shape of gold nanoparticle on carbon dioxide reduction. And finally, at hot carrier generation in these gold palladium nanoarchitectures for hydrogen production. Finally, I want to acknowledge the team that's done the work. Most of it is done by Han-Wen Jin, who is an excellent PhD student at Imperial. And also want to thank you for your attention.
Thank you very much, Johannes, for this very interesting talk. I'm sure there are questions. Yes.
Hi, Johannes. Thanks for the nice talk. I have 2 questions, in fact. First one is that with your methods, you don't really see the plasmon, right? So in the sense that you see single particle excitations, you don't see the many body excitation that is associated with the plasmonic effects. And the second question is, when you have the satellite that is a core shell structure by itself, is this stable? So So your idea is that your palladium is covering all the gold structure. Is this true at these scales, or do you have a separation with something like Janus particles that are, I don't know, how is the coverage in this case?
Okay, let me answer your second question first. I mean, these are all basically motivated by the experiments, right? So, so we haven't studied, so we're assuming that they're stable because the experimental is telling us. Just as a word of sort of, what's actually happening in the real world is that these nanoparticles are covered by ligands. And so these ligands are very important in stabilizing the nanoparticles. But, I mean, thermodynamic stability is a problem. So, for example, the experimentalists actually set out to make alloy satellites like they did the core shell satellites, but what ended up happening is that these satellites nanoparticles ended up being core shell type. So it's a complicated question that we're not answering. To go into your first question, you're right that we evaluate Fermi's golden rule, which doesn't capture electron-electron interactions, but the perturbation that we use is from a solution of Maxwell's equation, and Maxwell's equation does capture the plasmon peak. So in that sense, we do have the electric field of the plasmon as input into our Fermi's golden rule. So in that sense, we do capture the plasmon, if you know what I mean.
Thank you. Any other question? Yeah.
Hi. The chemical reaction takes place on the surface. So whereas you are computing the carrier generation in all your object, what are the diffusion? So is this a realistic thing, or should you consider that only part of electron generated participate to the chemistry at the surface?
That's a really good question. So at this point, our method gives us the full hot carrier generation rate and doesn't give us spatial resolution. The thing that I do know is that intraband transitions are enabled by the surface, so they only happen at the surface. Interband transitions happen everywhere. So we already know that intraband transition, hot electrons arising from intraband transitions must be at the surface. But of course, you raise a very, very good point, and that is the point of relaxation and diffusion and all of these important effects, which are not included. This is just hot carrier excitation, and there's a lot of discussion about how quickly relaxation happens, and do they relax before they can participate in chemical reactions? All of that isn't included yet, but for future work, definitely.
Anything else? I think so, Nicola.
So my question is about the shape-dependent. Does it mean that the field enhancement depends basically on how sharp the corners are of the? So the more roundish the shape, the less enhancement you will have.
Exactly. In a nutshell, that's okay. It. Yeah. If you have a lot of people are interested in sort of nanostars, very spiky things, and then you have lots of field enhancements.
Okay, I think we have to move on again. Thank you very much for this talk. And so a previous session that was on time-dependent phenomena to another one on Hubbard-U treatment in these materials simulations. And so we start with the talk. This session will bridge over the coffee break. So the first talk will be now, and it is by Young-Woo Son from the Korean Institute of Advanced Studies. And he is going to tell us of efficient ab-initio methods for extended Hubbard interactions.
Okay. First of all, I thank organizers for giving me a chance to present my group's recent efforts to implement extended Hubbard interactions in the quantum espresso. So this is my postdoc, then who contributed this project. So it's Dr. Sang Ni recently moved to the Samsung, and Dr. Woo-il Yang and other postdocs here. Okay, so I don't need the introduction here for this community because everybody knows that it's actually LDA or PBE doesn't kind of designed to give a quasi-particle energy gap, even though if you practically many people computed a gap for this semi-local local approximation for the exchange correlation, that for the prototypical covalent material or zinc oxide or two-dimensional molybdenite or even graphene, that all key group quasi-particle, all gap or group velocity is not agree well with do not agree well with the experimental value. And moreover, sometimes it's very qualitatively not good, in some sense that indium arsenide, actually, if you compute the DFT-GGA, it's a topological insulator, but it's just a typical normal insulator if you compute it, including the correlation effect very well. Also, brucite cobalt oxide, you need a U to compute the energy gap. And moreover, for some complicated systems, such as molecular junction, if you use Landauer formula or non-equilibrium green function technique, if you do not include the self-interaction correction, then actually the LDA current, almost kind of, if you should not have a current in some sense, but you have a lot of current here, so kind of qualitative errors. So there are many kind of efforts to overcome that in the Hamiltonian level. So, for example, Steve already introduced that this kind of diagrammatic approaches of GGW approximation and the local self-interaction error correction through the U, including the U or hybrid functional and dynamical mean field theory and so on and so forth. So there's a lot of effort. So the one thing I wanna address in this talk is that all these things are very good, but for example, if you want to do a many calculation and very fast, then for example, high throughput works or database-driven research, openly this kind of accurate computational method is quite expensive and very hard to do that because of a lot of resources you need. Moreover, for example, the hybrid functional or MBJ LDA functional method actually has some intrinsic errors when there is kind of some specific system that was not designed well for the application of this functional. And also, the U value, actually, sometimes people use an empirical correction, but if you do a lot of database or large system, actually you need some way to calculate it, the U value, right? So this is a topic, so how to implement it local and non-local self-interaction energy correction, self-interaction error correction without any empiricism, with a very fast calculation, simultaneously achieving the kind of accuracies comparable to the GW. Okay, so this is Hubbard Hamiltonian. Then this is the direct form of the DFTU formulation. Then this is the density matrices projected on some localized orbiter. Here is the ith atom is M prime. So to compute it, some empirical values and also linear response theory developed by this Computational and Zironkoli long time ago, and also in the momentum space recently Tim Rope and company developed the density function four-dimensional way is a momentum space formalism to compute the U. And also there is another way is that the kind of evaluating the U value from the unrestricted Hartree-Fock formalism. So actually, we focus on the last one. Is developed by recently in this Agavito and the other co-workers, because as I mentioned before, the original purpose of this work is to compute it very many systems with a very fast time. So we want to compute the U value within a self-consistent loop. We don't want to do another additional computational routine. So we think that this is good. So let me introduce a little bit about that. So I think actually original idea was developed by Mossy and Carter in 2007, this PRB paper, that they look at the molecular system that actually the U and J, or Hubbard-Hamiltonian, actually can be think of kind of a projected pairwise Hartree-Fock interaction computed by some other functional. So HCBN0 functional is nothing but an extension of this molecular system ideas to the block wave function. So this is Hartree-Fock representation. So here, this is just a bare electron repulsion integral. So this is just a bare interaction for the given one atoms for I here. Then M is a different orbital. So interorbital Coulomb repulsion representation. And this P is key idea here. So when you projected your wave function, is the density matrix to some submanifold of this M and N prime orbitals, you scale this with this value of N. What is N? This N is just the weight of the total block wave function. So projected total block wave function to the interested molecular orbital. So when this becomes to be 0, that the expression becomes to be LDA or PBE. When it becomes to be 1, it's just a Hartree-Fock. So if you do some calculation that it should have some value, it depends on your system. And also this is also position dependent because it's index of the I. Okay, so this is renormalized occupancies, control the self-energy or U value of system. So if you equate of this expression to the Hubbard-Hamiltonian, then actually you end up with some kind of hybrid type expression. So do you have a bare Coulomb interaction with the weight here for the U and J? Okay, this is nice. So, but this is still DFT plus U formalism. So you computed it within a self-consistent loop with unrestricted Hartree-Fock formalism. So this, even though this is very nice, when you calculate the U within your self-consistent loops, this still has a lot of problem that DFT plus U has. For example, so the semiconductor you cannot describe very well, and also the many metal oxide compound shows over-localization, so electron get to the strongly localized of d orbitals, and also if you have strong PD hybridization, that is very hard to compute it, and also there should be non-local correlation you cannot deal with. So if you decompose a Coulomb interaction, so this is very general expression, then let's focus on the single orbital problem here. So we drop the all orbital index, so just the site index IJKR. Then everything is the same, then it goes to the Hubbard interaction. Then actually this is the hierarchy of size. Then if IK is equal and JR is equal, both are not equal together, then this is interside Hubbard interaction. Then the next one is correlated hopping. through the bond charge. Then the fourth one is ferromagnetism, right? So this is decomposition of Coulomb interaction. So this almost 10 years ago, Computational developed this kind of including intersite Hubbard interaction within a DFT formalism. So everything is ready. So this is DFT plus U formalism. Then you include the B term. Actually, you end up with this. Then actually this is just like a U, then fully localized limit consideration that this is just a double counting for the DFT. So we just deleted it. That this is final expression for the DFT plus U plus V formalism in a density representation. So you can immediately notice that this is very interesting because as already very well known that this U functional actually force the integer filling for the specific localized orbital for the I, right? However, this intersite orbital actually push it away from the electron from localized side, actually to the bond side. So this is controlling the bond interaction. So these are actually competing as you expected, right? So from this formalism, okay, so we now combine those two ideas together. So how you can do that? So intersite Hubbard interaction, as I showed before, this is already written in the Computational, the paper. Then this IJ means that this is we just consider the pair of atom I and J located in different position within a given cutoff. So this is only parameters in our formalism. So you can set up how much pairs do you need. So, and this is nothing but kind of dense matrix. So we use the Reading also normalized projector. Yeah, you can use anything you want. Then we write down the ACB0 Reich expression for the intersite interaction. So because of kind of double counting is at one port. And here is this generalized projector for the this-pair interaction, looks like that. Then this is just a Coulomb interaction. To accelerate the computing time, we're just using the 3 Gaussian fitting for the given projectors. So it's just almost analytical. So it's very quick if you have a given position and orbitals. And this one is the controlling. This is a decisive one. So this is a project generalized pairwise dense matrix. Then this n value here looks like that. So this n is our hypothesis or ansatz. So this renormalized occupation actually controls the intersite interaction. We consider that there is many ways, but there is no justification. This is my ansatz. So we consider that intersite Coulomb interaction will be controlled by the charges located both sides, as well as charges located in between them. So we just adding up the projected density located for the ith electron and jth electron. Okay? So if this goes to the 0, then all calculation goes to the LDA or PBE, original exchange correlation functional. If it goes to 1, it goes to the Hartree bar. Okay? Then using all this expression, then equating everything, you end up with a kind of a pseudo-hybrid functional for the intersite Hubbard interaction. So we implemented this one is Quantum Espresso 7.0 version in our home institution. So it looks very simple, actually. If you have a density matrix and projected pairwise n value, then you can compute it within your self-consistent loops. So actually, the computational time compared with the PBE, it doesn't increase much. It's the same because every density matrix is solved within your self-consistent loops, right? So you kind of converged this matrix and these functional simultaneously in your self-consistent loop, then all calculations have been done within a very short time. So this is the result. So we computed this 23 different three-dimensional solid from a simple covalent semiconductor and 3,5 and 2,6 and zinc compound, ionic compound, some oxide. So this is theory and experiment curve. So this is line. Then this is PBE, and this is HSE, and this is GW. So GW is a little bit overshoot, and HSE is a little bit under the line, and PBE is quite below the line. And this is our one. So you compared everything together, then actually we are on very satisfactory in the sense that, so for example, this is lithium fluoride. So GW is here, and HSE, and this is PBE, and our one is here. And then magnesium oxide, no method agree with the experiment. So magnesium oxide is very notoriously difficult. Then any other things are like that, okay? So this is a projector. You need a projector. So we use a projector inside in the pseudopotential. So we just extracted the already orthonormalized orbitals within the pseudopotential. So there is a kind of dependency on pseudopotential. We tested 2 databases. Not so much, but there are dependencies. Then band gap agree very well. And the important thing is that it's very fast. Okay? So this is some example. So the silicon is about the 116%. And zinc oxide is almost agree very well. As I mentioned, the lithium ferrite is kind of 100%. And moreover, graphene group velocity is almost the same as GW or experiment. And moreover, this is important. This is a low-dimensional material. For example, it's a black phosphorus. So black phosphorus, as you see, that this is phosphorine has corrugated structure. So there are strong mixing between S and P orbital here. Then, and the low dimension is 2 dimension. This is number of layer, and this is computed energy gap. And GGA is quite off from the experiment. So this is quasi-particle gap for the single layer. Then, and as you see that this is hybrid function, HSE06. And this is DFT plus U on a p orbital. Okay, so this is ACBN0. And this yellow triangle is MBJ LDA. So as you can see that all those are actually on top of the kind of exotonic gap. So this is a BSE calculation. Then G0, W0 calculation is this, and GW0 calculation is this. So our one is blue dot is just on top of the G0, W0 calculation. So I'm sorry. So it's okay. So it's a low-dimensional system. Actually, the GW calculation, you need a very high cutoff. There's nowadays some nice technique developed by Steve's group to accelerate the calculation, but essentially our calculation computation time is the same as the PBE. And moreover, then it's very well known, well pointed out in the Manish and Steve's paper in PRL in the 10 years ago, that hybrid functional is not good. Yeah, not good for this kind of reconstructed system. Then this silicon 1-on-1, 2x1 construction that bulk semiconducting gap, and there is a one-dimensional chain. This is also semiconductor. So this is very old RPS and inverse RPS data, and this line is our calculation. So our calculation also agree very well with GW's calculation. because in our calculation, intersite Hubbard interaction and the U interaction are actually changing depending on the position because it reflects the local screening through the number variation of the projected density P. And the magnetic moment is also good. Okay, so, okay. For silicon, actually, our one is 100 times faster than HSE. So, and also, you don't need the resources. You can do it in the laptop. Then, any other things? Yeah, because this is functional, the single particle functional. You can also do the kind of Ponon calculation. As Steve introduced very well, then his achievement is very nice one. It's the GWDFPT. So actually, we think, okay, this one is recently people consider the correlation effect on the Ponon. For example, this is nickel oxide, LDA, optical Ponon. This dot is the experiment, and this field circle is computed by LDA. It's quite different than the Savrasov and Kotelia show that if you include the DMFT calculation, it agrees very well. And also, Steve introduced that this charge disproportional system, for example, barium bismuth oxide, you need the GW. So, as I mentioned before, it's very nice, but it needs a lot of resources. So, our one is just the Hubbard interaction. So it's on-site and inter-site. So you're just using the chain rule, then you can compute it pulse directly. Fortunately, the next speaker and Tim Locke developed the Poulet pulses for this density variation. So we just using it, and the other one is very straightforward to compute. So this is the result. We first tested silicon, copper, diamond, and germanium. You can see that this is what's that? Lattice constant, variation with respect to deviation with respect to the experiment. So this is %. You can see that LDA is tends to be smaller than experiment, and PBE is expansion, and PBE soar is okay, and HSE and this, and our one is this. So LDA PBE error is about 1 to 2%, and PBE soar and HSE and our one is plus minus 0.5 for the here. Then bulk modulus is more dramatic. As you can see that all those things are very bad, that including PBE soar. Then HSE in ours is about plus minus 5%. And this is optical Ponon. Then you can see that this is error with respect to the experiment. Then this is functional for the exchange correlation, and this is high symmetric point of optical Ponon. That it's okay, but silicon is our one is plus minus 1.5. And moreover, actually this is much better. This is Gruneisen parameters. Then this line is our one, and that is the experiment. So the mode-dependent Gruneisen parameters, our calculation is very nice. So what others? So nickel oxide. Then you can see that PB is, that is the experiment. So usually, as I mentioned before, the oxide, if you include the DFT plus U, is self-consistent determined U, typically over-localized. So the optical frequency is very hard compared to hardened, compared with the experiment. So you can see that this one upshifted. Then this intersite interaction is a counterbalancing of that. And you can see that our calculation is agree very well with the experiment. It's very comparable to, actually more than the DMFT. And this is barium bismuth oxide system. Because of time limitation, this is summary. So this study is the experiment for the doped system. And blue one is the PBE, and red one is our calculation. The key critical Ponon mode is M and R as a tilting and stretching mode. So as a function of the doping, it becomes to be charge-dense wave to the superconducting transition at the doping of about 40% of the potassium here. So this line, this is doping of potassium here. And this is a summary of frequency of those four critical phonon modes. So the negative means that it's a CDW state and becomes to be hardened because it becomes a superconductor. So if you compute the GGA, that all those phonons still are negative, means that still in CDW phase. Then if you compute it including plus U for the all orbitals necessarily, that it predict that there should be CDW to superconducting transition around 30%. And this is our calculation. If you're including the B, that our calculation is exactly match the experimental observation. Okay, so let me conclude. We developed and implemented extended Hubbard functional formalism in the quantum espresso. This can be done within a self-consistent loop. So the time consuming the calculation is exactly, almost the same, not exactly, same as semi-local approximation for the exchange correlation. Then everything you can do with DFT plus U or semi-local approximation, actually you can do with this formalism. Thank you.
Thank you very much. That was really impressive results you have here. Any questions?
Okay, whatever. Yeah, thank you very much. I actually have two questions. The first question is about your double counting correction. Yeah, that, as you know, as a practitioner, it's a very tricky thing. I think you use the fully localized limit. Does it work in every case?
Actually, we do not test it very well about that approximation. We're just using it, then tested every others. Then there are some errors, as you can see that. I don't know whether error comes from that approximation or the other. There are so many other ansatz there. So which one contributed the error? We don't test it rigorously. But as you correct, this is not a fully localized limit, right? Surely. So we need to consider it more. Yeah.
Okay. And the second question is, do you understand what is so, really particular about magnesium oxide, that nothing works? Is the nature of bonding, or,
I don't know.
Okay.
I don't know. We just quickly surveyed every solid 23 very quickly, so we do not focus every details, everything. Yeah.
Thank you very much for the very, very interesting talk. And since Tanushi had two questions, I will also take two. The second one will be very short. But the first one is maybe a bit more extensive, and also maybe to the GW experts in the audience, because I'm confused about one point. I understand that conventional methods to calculate U, and also U and V actually, have two ingredients. One is coming essentially from matrix elements, overlaps of different orbitals and representations and so on, and that's important. But there's a second one, which is essentially assessing the screening. And in other methods, this is very explicit. For example, in the constrained random phase approximation techniques, you can even choose the channels that you would like to screen. But also, for example, in the methods that Matteo Coccocioni put up that you cited, you have this linear response actually essentially determining the screening, the response of the system. So now in your technique, I saw the matrix element and all the overlaps, but I didn't understand how you include screening. Yes. So I kind of, for myself, figured out that your scope is a bit different, that you essentially are aiming to parameterize the Hartree-Fock Hamiltonian, which is a different thing than the U of LDA plus U. But then, on the other hand, your results should essentially reproduce the Hartree-Fock, which doesn't seem to be happening. So I'm a bit puzzled about this.
Yes.
Then the second question is very short. It's just a technical one. When you talk about the nickel oxide, and you're referring to the V, do you mean the V between two nickel, or the V between nickel and oxygen? So is it the ligand?
The second is very it's straightforward. Nickel and oxygen.
Okay, thanks.
Yes, here B is the nickel and oxygen. And first one is also, thank you very much. We have very much thought about it very long time, actually. So the matrix element effect is straightforward in this formalism. The screening, that actually, as I showed you before that, we constructed kind of a functional form for the B. It involves the kind of projected electron for the given atoms participating in the intersite Coulomb interaction, that we weighted them proportional to the charge within the unit cell, that how much charge proportion participate in the bonding. So we weighted them with some proportion. That's a kind of free factor for the Hartree Fock. So that's the reason why we do not go back to the Hartree Fock, because we always has kind of weighting factor with respect to the whole charges. So it kind of is sensing in some sense of screening, because of in the whole charge within the unit cell, how much charge participate in the bonding. Okay, so that's.
Why is that an estimate for screening?
That's still we do not know the answer, but somehow it's very remarkably reproduced the GW result. Frankly, we still do not know exactly. But the ansatz is just we summing up all charges participating in that procedure. Yeah, that's all we know. Because this is ansatz. We just write down, okay, this may be better. Okay, so result looks like that. So, frankly speaking, I don't know. Yeah.
Okay, thank you. Is there any other quick question, Federico?
Thanks for the nice talk. You compare your results with band structure calculation, and did you also try optical response?
Yeah, that's a very nice question. But the optical, you need electron hole pair interactions as a Bethe-Sarfati equation, as Steve already demonstrated. So our contribution, maybe we can bypass the GW, but all the other Coulomb matrix elements you need to compute the electron hole pair interaction. So we maybe improved marginally the computational speed, but we tested it. I don't have it, sorry, because I converted it to the PDF file. But we tested it and put silicon and black phosphorus. Then our calculation is quite agree very well with GW Bethe-Sarfati equation.
Okay, thank you very much. And well, there's a quick question by Francesco.
Because I mean, indeed, the critical things is this effective screening.
Yes,
HEC also has we have a mixing parameter somehow, a screening that is somehow hidden in the calculation. A critical case to prove this is an heterostructure between a material with high dielectric constant and low dielectric constant, and the binary alignment between the two. HEC this fail totally, and instead GW take in account. So probably this is the best test. So you have to take an heterojunction with a low low gap semiconductor, high gap semiconductor, and see if you get the band alignment of GW. That is probably a nice test.
Thank you. Yeah. Thank you for a very nice comment. Actually, we will try. That's a list. That's a list to do. Okay, thank you. Thank you very much.
Okay, thanks a lot. We thank the speakers of this morning session again. And now I remind you, of course, there is coffee, but that needs no reminding. But there is the photograph for the workshop happening now. And otherwise, please come back here by 20 past the hour. Please, the photograph will happen here. So if you can stay, please, for the photograph.
So please all come down. The photographer will stay there. We will be here down. So, okay, here he is. Veniamo giù, no? So, yeah, in front and in the back. So he will be above, so he will see both lines. So please. So please form a further line in front. Those on the tails, please come to the center. We are too broad. So I promise this is the most difficult part of the workshop. Everything else. Thank you. So coffee is in the entrance hall, no? So, and please, for the speakers, please come. For the speaker of the next session, please come down so we can test the presentation.
Light up, just to be sure that
it's green.
Yes.
Yeah?
Test, test, microfono test. Provo a parlare. Ok, test, 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 test. Adesso continuo a parlare, provo ad andare sotto la cassa. Ok, troppo, troppo. Test, 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 test. Prova, prova, sa, test, 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 sa, test, 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 sa. Ok, lo sento bene così. Non lo sento innescare e lo sento abbastanza presente. Ok, grazie ragazzi. Slide up. Test, test.
Hello, hello.
Yeah, that's right.
Hello, hello. Hello.
Yes. But even flu is quite.
Hello, 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 hello. Hello, hello, hello.
are allowed to make.
Yeah. Is it stream? Yeah, yeah, I think so. Okay, maybe we can get started with the second part of the morning. This is Nicola Marzari from EPFL in Lausanne and the Paul Scherrer Institute. So I'll introduce the speaker of the second part of the previous session. So we have Yuri Timrov from EPFL on accurate electronic properties and intercalation voltages of lithium-ion battery cathode materials from extended Hubbard functional. Yuri, floor is yours. I give you a sign 5 minutes before.
Thank you, Nicola, for the introduction. Good morning to everyone. So first of all, I would like to thank the organizers for having given me the opportunity to present my work today. And it's really my great pleasure and honor to present my work here. Okay, so let's start with the self-interaction error or the localization error in approximate DFT. So let's consider the simplest case, the dissociation of the H2 plus molecule. So here on this figure, I show on the top the charge density distribution of an electron in green for the H2 plus ion, molecule. So the interesting thing happens when we're actually pulling apart two hydrogen ions. So in approximate DFT, what you find is that the electronic charge density is split equally between two ions. So we have half an electron on the left and half of an electron on the right. And this is the only solution in DFT. But then if you use actually, if you solve the Schrödinger equation exactly for this problem, you will actually realize that there are an infinite number of solutions. One of the solutions is that you have one electron on the left and 0 on the right, or you have one electron on the right and 0 on the left. So this is the so-called, and these solutions are actually orthogonal to each other and degenerate. So this is the so-called left-right degeneracy. And actually, linear combination of these two orthogonal solutions is also a good solution. So why in approximate DFT we obtain only one solution where you have half an electron on the left and half on the right? And this is exactly because of so-called self-interaction errors. So, and there is a link actually between this problem and the so-called spurious quadratic energy change when we're adding or removing a fraction of an electron to the system. So in this figure, I show the energy error as a function of the fractional charge for the H atom. So if we use Hartree-Fock, which is free from self-interaction errors, we will see that the error is 0. It's because of the linearity of the energy, because of the so-called piecewise linearity of the total energy with respect to the number of electrons. If instead we use approximate DFT with LDA or even hybrid functional B3-LEAP, we will see that actually energy changes in a quadratic fashion. And so there is a deviation from the exact solution due to the delocalization error or self-interaction error. So electron is actually spread around, and that's why we have half of an electron on the left and half on the right. But actually, if we come back to our problem on the left, and actually we can, in approximate DFT, we can impose the piecewise linearity, and by doing so, we can restore the left-right degeneracy. And actually, what we will obtain is that the energy cost of removing of an electron from the left ion is equal to the energy that we are gaining when we are putting the same fraction of charge on the right. And this allows us to restore the piecewise linearity. And so this problem of the H2 plus is actually, of self-interactions in 2 plus is actually found also in the mixed valence materials. So if we go to the next slide, so if we consider this cathode material, so the correct solution is actually that we have two types of irons, one in the oxidation state 2 plus and another in the oxidation state 3 plus. But if we use approximate DFT with LDA or GGA functionals, what we will find is actually the average oxidation state of 2.5 plus. And this is exactly due to self-interaction errors of approximate DFT. So what happens is that the iron 3D electrons are delocalized and they're spread around. So you have the equal number of charge on all iron ions. And that's why we have 2.5 plus oxidation state. And we can make, again, a link with the energetics. So we have the spurious quadratic energy change when we're adding or removing a fraction of an electron to iron. So in this figure, we see the exact solution. It must be piecewise linear. It's a function of the number of electrons. But when we use approximate DFT, we have some quadratic-like behavior, which is wrong. OK, now let's talk about DFT plus U, because it's one of the methods to cure self-interaction errors. So DFT plus U was introduced in the early 90s by Anisimov and coworkers. And then later on, Lichtenstein, Duderov, and others introduced other formulations of DFT plus U. So the idea was just to take DFT on one hand, take Hubbard model on the other hand. So since Hubbard model was developed to work with strongly correlated materials, so people initially thought that actually DFT plus U is the method to deal with strong correlations. But later, people actually realized that what you actually cure with the plus U correction is not strong correlations, but self-interactions, like in the H2 plus molecule. So this is the energy expression for in DFT plus U. I want to stress that this is heuristic, that there is no theorem or proof of this. And this Hubbard functional is actually not variational with respect to Hubbard U. So far, there is no any theorem or proof. And in the previous talk, already Youngwoo explained about this functional. I don't want to spend much detail, but what we have DFT total energy, which is augmented with the Hubbard correction. And here, N are the so-called occupation matrices, which are defined by taking Conshine wave functions psi and projecting them on the atom center localized functions phi. And F are some Fermi-Dirac distributions. This is well known, and in 2010, as Youngwoo mentioned, Matteo Coccocioni and Campo, they introduced an extension of DFT plus U. It's called DFT plus U plus V, where we have not only the on-site Hubbard correction, which favors integer occupations and that pushes your electron to be more localized, but you have a second correction, the inter-site Hubbard correction, which actually favors hybridizations between transition metal and ligands. And so these two terms are actually competing with each other, so it's important to have the balance of the two, to have the accurate description of the system. And this is just a picture showing that plus U wants to localize electron on the transition metal atom, while plus V actually restores back the hybridization with, let's say, oxygen ions around. There are two strongly interconnected key aspects about DFT plus U and DFT plus U plus V. So on the one hand, we have Hubbard parameters, U and V, which are unknown. And on the other hand, we have these localized atom center functions phi. So it's actually, one can wonder that they are independent objects, but actually it's completely the opposite. They are dependent on each other. So depending on which type of Hubbard projector functions you choose, you will need different values of Hubbard U and V to get the correct energies. So let's talk more about Hubbard parameters. Already a lot was said in the previous talk, but I would like to summarize after the coffee break. So we don't know Hubbard parameters, so we need somehow to determine them. And there are two strategies. One is to use the semi-empirical values by tuning Hubbard U to reproduce some properties of interest, let's say band gaps, magnetic moments, you name it. But for this, we really need to have experimental data as a reference. And on the other hand, we have first principles methods like CDFT, CRPA, Hartree-Fock-based approach like ACBN0, and linear response. So in the previous talk, Youngwoo nicely explained about the ACBN0 functional. And the topic of this talk is actually linear response theory. Hubbard parameters are not universal. What does this mean? So when we compute Hubbard parameters using ab-initio methods, let's say linear response, we will find that Hubbard parameters are not unique. They depend on many properties. So one is, which Hubbard projectors do we use? So there can be atomic or orthogonalized atomic, maximal localized Lagrange functions. These are those localized functions highlighted in yellow. Then the value of Hubbard U depends on the oxidation state of the pseudized atom, or in other words, on the pseudopotential, simply speaking. Also, the Hubbard U depends on the exchange correlation functional, be it LDA or GGA. and also on the way you compute them, the self-consistency. There is one-shot way of computing Hubbard parameters or self-consistent. I will say more about this later in my talk. So how to compute Hubbard parameters using linear response theory? So let's start with the definition of the Hubbard energy. This is the Hubbard correction. For simplicity, I consider only one transition metal, so I don't have the summation over atoms. And here n is computed by taking a trace of the matrix n, so it's just the number of electrons in the Hubbard manifold. Then we remind ourselves the problem, so the exact total energy must be piecewise linear as a function of the number of electrons in the Hubbard manifold, while approximate DFT gives quadratic-like behavior, which is what we don't like. So we don't like this curvature, so we simply can impose the condition that the second derivative of the total energy with respect to the number of electrons in the Hubbard manifold is 0. So this way allows us to get rid of the curvature and restore the piecewise linearity. So what we do, we simply take the definition of the energy, compute the second derivative. It's a very simple task. And what you will readily obtain is that the U is actually the second derivative of the DFT total energy, as simple as that. There is a more rigorous mathematical proof in this paper by Matteo Coccocioni and Stefano De Gironcoli. And I would like to stress that there is no theorem for the piecewise linearity of the total energy in the Hubbard manifold, only with respect to the total number of electrons. So it's heuristic. How to use linear response theory in practice? We need to take our Conchem equation. We modify it a little bit by putting inside some small perturbation. So lambda is the strength of the perturbation, and V is the perturbing potential, which is simply the projector on the localized manifold. And then we need to construct supercells and perturb atoms one at a time. Since we're using periodic boundary condition, the perturbed atom will interact with its periodic replicas. So that's why we need to use supercells large enough to get rid of this unphysical interaction between perturbed atom and its replicas. So we solve this modified equation for several values of lambda. This way we can measure the response of the system to the perturbation, which is the change of the occupations, delta n, and we divide it by delta lambda, which is the change in the strength. And this gives us the object, which is called response matrix, chi. We take the inverse of this matrix. Then we compute the chi naught, which is the object analogous to chi, but chi is self-consistent value, while chi naught is the non-interacting or bare response. Then we take the difference of the two. We obtain a matrix. On the diagonal of that matrix, we obtain on-side Hubbard U corrections. And on the off-side of the diagonal, we obtain the interside Hubbard V parameters. So this method works very well. It was applied to many problems. However, there are a number of drawbacks. The computational cost, of course, then possible convergence issues, and it's not always easy to use it in practice, so quite low user-friendliness. So we actually asked ourselves, can we have a better, more efficient reformulation of the same theory, but using more effective methods? And actually, we did it several years ago with Matteo Coccocioni and Nicola Marzari. So I will show you that we can go from supercells to primitive unit cells. So what we do, we start with our modified Conchem equations. I said that this is a small perturbation, which allows us to expand all quantities in Taylor series. Then we cut off those Taylor series at first order, so we keep only first order quantities. And by doing so, we can show that this modified equation will be actually a linearized Conchem equation, also known as Steinheimer equation. So we can solve this equation. And moreover, we use the fact that the potential in a supercell can be decomposed as a sum of the Q points in a primitive cell. And by doing so, instead of using finite differences in a supercell, we're actually having an analytical formula in the primitive cell where we need to sum up over Q points, which are different modulations of different monochromatic perturbations. We have a phase factor, and delta Qn are the responses of occupations to different monochromatic Q-modulated perturbations. And then we do the same post-processing step as before to obtain Hubbard UNV parameters. So this is nothing but density functional perturbation theory that is known for 3 decades. So it was used for phonons by Stefano Baroni, Stefano De Gironcoli, Andrea Dal Corso, and Paolo Giannozzi. So it's computationally much less expensive than using supercells like frozen phonon. It's easier to converge and user-friendly and autonomous. We implemented DFPT for computing Hubbard parameters in Quantum Espresso, the corresponding code HP. It's public, open source, distributed with Quantum Espresso. On the left, I show you the scaling. In black, I show you the old supercell approach with finite differences. In red is DFPT with primitive cells. So you will see enormous speed up. This is thanks in particular to symmetry, because by using symmetry, we can reduce number of Q points, while in supercells, we can't use the same trick. We can't reduce number of atoms. So we gain really a lot due to this. And on the right in the table, I show you the numerical comparison of the old linear response for supercells with DFPT, and we see really remarkable agreement. The residual errors are just numerical noise, and we can further reduce them. And then I also mentioned about Hubbard projectors. There are really many choices in different electronic structure codes. We have different types of Hubbard projectors. In Quantum Espresso, we have, in particular, non-orthogonalized atomic orbitals, phi, which are provided with pseudopotentials. However, disadvantage or drawback of these projectors is that the application of Hubbard U is actually twice in the overlap regions here, which is not wanted. So we can use orthogonalized atomic orbitals instead, which is compute overlap matrices, invert them, and we construct these objects using loading orthogonalization method. And by this way, we get rid of this double counting or double application of Hubbard corrections in the overlap regions. Another very good option is to use maximally localized Wannier functions. This also, we're actually working on this, but for us, the standard and the most accurate is the orthogonalized atomic orbitals. And finally, we use the so-called self-consistent procedure when we're computing Hubbard parameters within DFT plus U plus V. How does it work? We start with initial structure, let's say experimental geometry, or you take it from some database. Then you perform structural optimization using DFT plus U plus V with some initial guess of U and V. This could be 0 if you don't have any clue, or it can be some good initial guess. Then we do ground state ECF calculation, and on top we compute Hubbard parameters using DFPT. Then we check whether the Hubbard parameters are converged and if the geometry is converged. If not, we go back and we repeat this cycle until we get to the point where we reach the full self-consistency. That is to say that the Hubbard parameters don't change, the geometry doesn't change, the electronic structure doesn't change. So all is consistent. And what we find in practice is that this is the Hubbard U is a function of this number of iterations or cycles. If we do just one iteration, is the one-shot calculation, we get something like slightly higher than 5 eV. But if we do this self-consistent cycle, we will find actually that the Hubbard U changes, in this case, to 4.3. So there is a non-negligible change, which really highlights that it's important to use this consistency. But I would like to mention that here we need to do structural optimization, which requires Hubbard forces and stresses. So let me mention quickly. Yang Wu already mentioned in his talk previously. But what we do is we use orthogonalized atomic orbitals, and that our goal is to compute Hubbard forces and stresses. I don't have time to go into detail, but in a nutshell, we simply take the derivative of the Hubbard corrective energy with respect to atomic displacements tau, and this all boils down to the derivative of the occupations with respect to atomic displacements, and this instead depends on the derivative of the square root of the overlap matrix, which is not a trivial object to compute. It's not a function, it's a matrix to the power of -1/2. And we have shown that it's actually known that one has to solve the Sylvester, or it's also called Lyapunov equation. It's a non-trivial task, but actually we managed to find exact solution which can be written in a compact form over here. We implemented it in Quantum Espresso and benchmark with finite differences here. And you see in the last column that the agreement between our analytical formula and finite difference is really good, which confirms the accuracy and correctness of the derivation and implementation. So now let's switch to applications. So in my talk, the title you saw, it's all about lithium-ion batteries. So let's try and use DFT plus U to lithium-ion batteries. We know that our energy demands are growing due to the growing population, and we no longer can continue using conventional sources because of pollution and global warming. We urgently need to do something with this. One solution is to use green or renewable sources like hydro, solar, wind. But for this, we need storage energy systems like batteries on the large scale. However, the current batteries are great, but there are safety issues, as you can see on the examples here. So we need to search for newer, more efficient, safer lithium-ion batteries. So let's try to use DFT plus U plus V. On the left, I show you the lithium-ion battery. We have negative electrode, which is called anode. And on the right, we have positive electrode, which is called cathode. Here can be, let's say, graphite. And here, there are many options for cathodes. And there is one can do high throughput to look for good cathodes. And in between anode and cathode, you have liquid electrolyte. And during this charging process, you have lithium plus ions going from the left to the right, and electrons go in the opposite direction. So what happens at the cathode? So in the fully charged battery, we have this compound. It's just an example, but we have iron. All irons are in the same oxidation state, 3+. And when we fully discharge the system, we have this compound where we have iron and 2+ oxidation state. And the interesting thing happens in between, where we have the mixed valence compound with iron in 2+ and 3+ oxidation state. And I would like to stress that it's really important to have a very accurate method that gives us reliable energetics and electronic structure of these complex materials. And Hubbard functionals is one of the methods that can be used for these problems. We start with the self-consistent solution of Hubbard parameters using linear response theory. So this is our simulation cell for this cathode material. We have 4 transition metal ions in this system. This can be all manganese atoms or all iron, or it can be mixture of both. So we compute the Hubbard parameters. So here I report Hubbard values for 4 types of manganese at concentration X equal to 0, so no lithium. So we report U, which are all the same values of Hubbard U, and V is in some certain range of values. Yep, thanks. So then if we increase the concentration of lithium in the system, we will notice that actually the first 3 manganese don't change much, but the last manganese actually changed abruptly. The Hubbard U value for this manganese changed abruptly. We also computed the Hubbard parameters for the other concentrations, and we can also check how Hubbard parameter changes for all transition metal atoms. We did the same type of calculations for the iron olivine, but the bottom line is that the Hubbard parameters are site-dependent, and they change upon lithiation or dilithiation. So what people commonly use, they use empirical U, the global value across all lithium concentrations for all transition metal ions. But actually what we can do and what we actually see that Hubbard U is not global. It actually depends on the transition metal ion, and it does change upon lithiation or dilithiation. We computed many properties, but I would like to show you the most interesting. So let's consider atomic loading populations. Here I show 3 panels. The top panel corresponds to DFT in PB-Sol, the middle panel hybrid HSE06, and the bottom DFT plus U plus V. On the y-axis, I show you the 3D shell occupations of transition metal ions, manganese in this case. And the x-axis is the lithium concentration. And for each concentration, we have 4 bars, and each bar corresponds to 4 types of manganese. So at concentration of 0, we have all manganese in the same oxidation state 3+. And at concentration 1, all of those ions are in oxidation state 2+. When we're adding lithium one by one, we see that only one transition metal changes occupations at a time. So we see this very clean and clear digital change in occupations. If you use hybrid functional, you also observe the same trend. But if you use DFT, and we know that there are self-interaction errors, we see that all occupations of all atoms change in the same manner, because the electronic charge is delocalized, it's spread around equally on all atoms. So that's why you see that you don't recover these digital change in occupations. We did the same analysis for iron. Again, you see that DFT plus U plus V works very well. Instead, here hybrid tries to do the good job, but it's actually not as accurate as DFT plus U plus V, because you don't really see the very clean and clear digital change in occupations. And again, DFT fails like in a manganese olivine case because of self-interactions. We also studied another mixed valence material where we have manganese and iron. Again, we can see the same trend that DFT plus U plus V works well. Hybrid also good, but not as accurate as DFT plus U plus V, while DFT fails. Also, I would like to mention that for the concentration from 0 to 1/2, it's the manganese that is redox active, and then from 1/2 to 1, it's actually the iron which is redox active. So the bottom line is that DFT plus U plus V is very accurate to reproduce the digital changes in occupations, which are really critical to recover experimentally observed redox plateaus in voltages. We also computed lithium intercalation voltages. So all what we need is to use this thermodynamic equation. This is a total energy at lithium concentration x2 minus total energy at concentration x1 minus energy of bulk lithium. It's a total energy workshop, so all what we need is just total energies. And this is the result. We see that the last bar is the experimental voltage. DFT largely underestimates the voltage. Hybrid and DFT plus U add corrections. They overshoot, overcorrect. And only DFT plus U plus V is in very good agreement with experimental voltages. We also did the same analysis for other cathode materials. We always find that DFT plus U plus V is the most accurate for computing voltages. We also check spin polarized projected density of states. At concentration x0, we see that DFT plus U plus V and HSE06, they are very similar, while DFT fails. When we start increasing the concentration of lithium, we see again that DFT plus U plus V has very similar trends to hybrid functionals, while DFT fails. And also for other concentrations, over and over, we see the same trends that DFT plus U plus V mimics very nicely hybrid functional. We studied also other families of cathode materials. This is the so-called spinel cathode materials. On the left, we have antiferromagnetic insulator. On the right, ferrimagnetic insulator. Both have 56 atoms in the supercell to accommodate these complicated magnetic spin configurations. And the bottom line is that hybrid functionals are expensive, computationally expensive, these kind of systems, and less accurate, while DFT plus U plus V has a moderate cost. We computed different properties. I would like to show you just voltages. The same trend is in the previous phospholivine cathodes. DFT plus U plus V is in a very good agreement with experimental voltages. And I'm coming to conclusions, but before I finish my talk, I would like to mention briefly about computational cost. So when we know U and V, DFT plus U plus V is actually only marginally more expensive than DFT. Computing these parameters using DFPT is about 20 times more expensive than DFT, so it's not negligible. U and V from DFPT allows us to generate some databases, and we can use those and use machine learning then to predict inexpensively Hubbard U parameters. So in collaboration with Martin Urin and other coworkers, we developed a machine learning model, and on the y-axis is the predicted values, on the horizontal one is the one we compute with DFPT, and we see really good agreement. And finally, if you compare the DFPT cost of computing Hubbard parameters, which is HSE06, you will see in the last column that still the ratio of the timing, still DFPT for computing U is cheaper than using hybrid functionals. And another slide, very important, there are some limitations and open questions in all this. So first is that linear response theory for closed shell systems gives very large values of Hubbard U parameters, which is, we need to find a solution to this problem. Then U and V are position dependent, so we need to have these derivatives of Hubbard parameters. I forgot to mention, but in our case, we neglect these derivatives. But in principle, one has to include them, as Young-Woo mentioned in the previous talk. Hubbard functionals are not variation with respect to Hubbard parameters, no proof or theorem. And DFT plus U plus V is a mean field, a single determinant approach, so no correlations. One has to use multi-determinant method instead. And finally, the piecewise linearity in the Hubbard manifold is a heuristic. There is no proof or theorem. And with this, I would like to conclude my talk. I've shown you that DFT plus U is really robust and accurate. It can be broadly applied to mixed valence functional materials. We use U and V. We compute U and V using linear response theory. And in the case, on the example of lithium-ion batteries, I've shown you that the computed properties, electronic, electrochemical, are in very good agreement with experiments. And with this, I would like to thank my collaborators, Nicola Marzari, Matteo Coccocioni is also in the audience, Michele Cotiuga, Francesca Culante, our sponsors, Marvel, SNSF. Of course, thank you for your attention. And finally, I would like to briefly mention about the Advanced Quantum Espresso School that will take place at the end of August this year in Pavia. If you're interested, please stay tuned on the Psyche mailing list for more information. Thank you.
Great, thank you. Thank you, Yuri, and we are open for questions.
If I understand correctly, as was replied in the earlier talk, the V is actually between the transition metal and the oxygen.
Correct.
So suppose I'm doing a calculation at the model level, which is, for example, if you take a cuprate, just a one-band Hamiltonian,
okay,
then of course, the oxygen degrees of freedom are integrated out. Then actually the V term should be included in the effective U you are thinking about. So did you had any attempt of calculating that? And will that, I think that was the question asked by Zilke, so will there be some effective V, which actually in terms of Hubbard model, that's the V between the transition metals?
Okay, so applying V between transition metals. From my experience, we have those V's also, but they're actually vanishing. They're very small. So computing, we have them, but they're vanishing.
No, but the point is if you really downfold or integrate out the oxygen degrees of freedom, they will show up in the one-band limit.
Yeah, we haven't done this, but it would be interesting to check. Yeah.
Let me take the micro on the way. So we actually computed those from CRPA, and we also confirmed that the UPD, the interaction between ligand and D, is actually large. And then the question you're asking is, can we actually downfold or not, right?
Yes, exactly.
Other questions?
When you use machine learning methods, can you choose the local environment of your atoms? So, for example, in the lithium-ion battery you were showing, you see that the parameters depends on how much lithium is around. Can you do this also at the machine learning level, or you have enough data to do this, or you need to implement your algorithms in that case?
Yes. So the answer is yes. So in our model, we use occupation matrices as descriptors. So with the projection of Conchem functions on the localized orbital, these are the main objects. And so we do take into account these changes in the local chemistry. So what we need to provide to our model as these occupation matrices. So what you will see that when you change the concentration of lithium, the occupations on transition metals change. And so we give this to the model, and the model realizes this and gives on the output the respective changes in the Hubbard parameters. So yes, our model is sensitive to this local chemistry.
And also the machine learning approach is sensitive.
Yeah, so we use how to build the database. We use DFPT. We apply it to a number of systems. We predict Hubbard parameters, and we also have the respective occupations. So we provide all this to the machine learning model. So the model sees, okay, for these occupations, I should have these values of Hubbard parameters. So you train it, and then let's say you take a new system for which we don't know anything, and what you need is just to compute occupations, and then you put this in the model, say, okay, now I have these occupations, what would be the Hubbard U? And the model gives you this certain value of the Hubbard U.
Okay, thank you very much for the nice lecture. I see it is impact on this lithium intercalation, voltage, and the other electronic structure. But what do you think on other electrochemical properties like energy barrier or ionic diffusion? Because we want to study this charge transport, right, in these cathode materials.
Yeah, it's a very good question. I think we just need to try. We haven't tried for those examples that you mentioned, but I think this method is generic, is general. We can apply it to any problem. So it's also open source. You can just, if you're interested, you can give it a try and see if it works or not. Yeah.
Okay, thanks Yuri for the talk.
Thank you.
And so the next speaker will be Nong Artricht from Utrecht University, and it will be about accelerating the construction of machine learning interatomic potentials using surrogate models.
Actually, I'm using my own computer, and we tried already, but okay.
Okay, help is at hand.
It was working.
Great, thanks, Nong.
Okay, first of all, thanks a lot, Nicola, for the kind introductions, and also many thanks to the organizers for inviting me here. Actually, my talk is slightly different from the rest of the talks from the communities or from this conference, but I'm really happy to be here. So my work, mainly we are developing machine learning models, try to understand the complex energy materials. And today I will focus on how we accelerate, how to construct the machine learning potentials using surrogate models. And we develop our own machine learning model tools and also database, and we also share with the scientific communities. So the software package that we develop is Atomic Energy Network. It is open and free software package. It is really nice that the previous talk already introduced and give introduction on batteries, but I just wanted to repeat again that actually atomistic simulation to understand batteries is really very complex and complicated. But understand many properties of material as atomic scale is very important. For example, the properties of interface and also nano transports according to the interface is very important. And you can see that on the left-hand side, the interface of a solid-state batteries that contain the order of a lithium cobalt oxide, like you can see here, and also the interface of the electrolytes. It is like a disorder of lithium cobalt oxides, or even the electrolyte, the lipon here, and also the anode. And another side is the anode, lithium silicon. This is kind of like amorphous structures of the lithium silicons. But what we are trying to understand the complex, because it's so important at atomic scale. For example, the important domain like a nano size, like you can see here, or even interfaces and also amorphous phases. So what we like to do, we would like to make use of accurate and also reliable of first principles, or the DFT, that we can generate atomic structure at realistic and larger scale like this. So together with the Columbia Center for Computational Electrochemistry, we also started to combine the atomistic simulation and also machine learning to develop database and also make use of machine learning, trying to understand such a complex interface. For example, in this cartoon that I draw. So we try to understand and characterization of interface, which is like a resistance and also interfacial like degradation, for example, here. So, and also many other parts, as already you mentioned that cathode material also very complicated. What we do, or what our work, that we try to develop machine learning models that based on learn from accurate and reliable electronic theories, for example, DFT, how to learn the atom interact. So we develop very reliable and accurate, for example, quantum mechanics or DFT database, and then we interpolate and also use machine learning models to learn and to construct efficient and accurate machine learning models so that we can really learn from the DFT database, and then we get really efficient and accurate energies that we can use in application, for example, in Monte Carlo simulation, and also can get accurate forces that we can use in realistic and larger scales in molecular dynamics simulations. So the model that I'm going to talk and discuss today, so we use artificial neural networks for the interpolations, and it's really easy to use and also based on only atomic positions. And it also can really reference once we train and we fit, it can get the results as accurate as, for example, DFT. This is the whole workflow of our work. So as a practice, like you can see here, so we need to get really reliable and also accurate database. And then we select the data that we hope that it can really capture the application that we are interested in, that we construct like a full potential energy surface. And once we get the data, and then we can select like a model selections, and then model trainings, and then we start to do model validation, like you can see here. And if we validate our model already, if it is working or not, we start to test by looking at the complex model that we're looking at. In this case, I show like the interface between solid and liquid, for example. If our machine learning model or machine learning potentials is accurate enough, it should be able to work directly as our intended applications. But if it doesn't work, we can also use another workflow of feature-assisted active learning so that it can help to find and capture what the structures not include or not seen in the training set. So we do this iterative refinement. And maybe this is kind of like a very abstract. Let's look at one concrete example. We are using like a water model as example here. The active learning constructs such a training set, which is also very important. First, we have initial data set, and then we construct the neural potentials, and then we fit. And then we use the neural potential in the application, for example, MD simulations. And then you can see that in x-axis, this is our structures along the MD trajectory that you can see here. And we detect the binding energies on the DFT reference data in the red cross here, and also our neural potentials along MD trajectories in the black. So we take a look at the errors between our reference data and neural networks. You can see there's still quite high errors. So the criteria is also depending on your application. You can set up as you wish to have. And then you can see that some structure, if it's not close to the DFT reference data, then we can include them in a training set. And then we do like this iterative refinement. So we implemented our models in the atomic energy network. If you are interested in, this is the website. We also plug it in, and we have the NL library that can use directly in the many application software package. For example, like ASE, LAM, and also Tinker, also DL Poly. This is the references if you are interested in. So let's take a look how we apply and also construct machine learning model, for example, to understand the lithium transport amorphous silicon for high energy density batteries. As already shown before that, batteries are really complex. Is for the positive electrodes and also electrolytes and also negative electrode, right? They are not the static, it's dynamics. So the number of atoms is changing all the time while the battery charge and discharge, like you can see here. So we trying to understand and try to optimize the composition so that we can find what is the best performance of materials. So the first example, we're trying to draw the full phase diagram of, for example, lithium silicons. So this is the whole workflow. Sorry, is it kind of like complicated, but we would like to overall, if we don't have data, we cannot have machine learning models. So the most important is that we generate a DFT database. So this is the initial that we can start. For example, we get the structure from crystal structures and then run some short AMD simulations and also distort structures by scaling the structure that we have. And then we construct the preliminary results of neural potentials. And then in the same time that you can also use the genetic algorithm to help to find the new phases by make use of the accurate neural potential that we have. And we increase the temperatures that we are running also MD simulation between 700 to 1,500 Kelvin. It's depending on also materials. And then we can also estimate the conductivities by using the linear plots, and also can draw the phase diagram and also do structure analysis, for example. Let's take a look at the first example. This is a lithium silicon anode for lithium-ion batteries. So we construct like a large DFT database of the lithium silicon, like you can see here. On the left-hand side, this is a computed phase diagram that you can see both from this axis. This is the lithium in the silicon, like you can see. So our reference data and neural network prediction is the same. So in this plot, I only show the DFT computed phase diagram. So our NN potentials and also DFT can predict like both crystal structures of the lithium silicons and also high energy amorphous structures that complete full the phase diagram, the formation energies that you can see here. And then in the same time, we also compare the voltage profiles. The blue that here, this is as a room temperature. And our voltage profile is predicted also in good agreement with experimental measurement. But we show is it in a few compositions based on the convex house that you can see here. And to understand the lithium transport, so we have also to make sure that our potentials or neural potentials really accurate for diffusion. So we also create a model that can represent that different compositions, neural network can predict the diffusion part accurately. So I show only two examples, the lithium 3.75 silicon and lithium 2.25 silicon here to show. And the two parts here, the x-axis is the NEV images of the part that it can move the lithium from A to B side. So you can see that the two structures that we independent, not included in the training set, that neural potential can really represent DFT result accurately. And then we use these neural potentials to run long-term MD simulation with different compositions that you can see. And also from the beginning until long-term MD simulation, like 2 nanoseconds. So neural network potential represents DFT reference data accurately. So this is really nice that we have efficient and accurate NN potentials. And then we can understand the compositions while we are running the MD simulation, also different compositions. And to make it more realistic, we're also looking at like the nanoparticles that you can see on the top of the figures. And we also estimate the conductivities or the activation energies using the linear plots with different compositions. So you can see that we can identify the atomic structures of different compositions and also how atomic rearrange. And we also can learn that the diffusities that we can predict from neural potentials that can also provide the atomic structures. So overall that we see that our neural potentials can also predict the diffusities close to experimental measurements, like you can see from the reference on the left-hand side here. And we can identify that the highest diffusities is between the lithium 1.0 to 2.25, for example. So once we learn this, we can also optimize or try to find what composition is it the best for our materials. And not only that, we're also looking at a more complex interface. For example, our students and postdocs, Chen Wang, and how you're looking at amorphous, like lithium phosphorus sulfides, and also anicate, and also INVON, looking at the interface between lithium anode and also the electrolyte ethylene carbonate. Let's take a look at the first phase diagram by Hao Yu and also Chen. So we also draw the phase diagram of the lithium phosphorus sulfide, or LPS. So we see that we use the same technique, and once we use our machine learning models and also can map the compositions between the material like a P2S5 and also lithium 2S, and we can draw. So the blue one is its crystal structures, but in realistics, right, when the battery is moving like a charge and discharge, the composition is slightly changing, but it's not very easy to understand the properties. So then we try to find the relationship between structure stabilities and conductivities. And this is the structure that we can extract from, in this case, I show as crystal structures in the graph that you can see here. But then we also want to understand the amorphous structures or glassy ceramics, like you can see here. So when we know this type of structure already, and then we can also estimate the activation energies. Like you can see that the composition that we found, this is slightly closer to the parent crystal structures. On the left is the lithium PS3, and on the right, lithium for P2S7, and in these structures. And let's take a look, because it's so many structures in our database. So we also make use of the another machine learning model like clusterings, try to learn what is similar to the lithium environment and close to the parent crystal structures. And then we find a relationship between the structures of the amorphous structure here. And I don't talk about the local environment here, because we also take the structures to calculate, for example, spectroscopies. And then we can also understand the oxidation state of like sulfur and also phosphorus. But today I will only show the conductivities and compare with experimental measurements. So to identify the new structure that we get from glassy ceramics is also compare like a reference with the previous work that's done with the crystal structures. Like you can see, it is compared with experimental measurement. But for our work with the full method of phase diagram, we could identify the amorphous structures. And then we found that it is have a higher conductivity than the perfect crystal structures. So if I have enough time, so far I only discussed like between database, only energy only, and we generate really large and big database. But for the beginner, sometimes how to start to develop your own neural network potentials, maybe it's easier to have some efficient tool. So in 2020, together with April Cooper, we proposed one way that how to construct neural potentials that include atomic forces. For example, in this case, wire Taylor expansion. So just to brief, because I also discussed this in 2021 in this workshop already. So as you know that the more data points included in the training set, you will get really accurate target potential interface. In this simple Lennard-Jones energies in the gray region here of the hydrogen dimer, as you can see. And the data original sample is the DFT. The more data points you have, you will get closer to the target like Lennard-Jones energies. So, but we don't get large data set directly, right? When we start to construct our neural potentials. How to do that? This is also another visualization to show also for water. Like you can see that if you have more data points, you will really have really accurate energy and forces, like you can see here in this demonstration that you can see. But most of the time, or sometimes that including forces in the training set it's quite expensive and also take a lot of CPU time. That's why we introduce another methods by including approximate forces information, which is kind of like a linear approximations. By include like a linear Taylor expansion, you don't need to do new DFT data set, but you introduce small displacements and then estimate the energies via the displacement that you have and include in a training set. So like you can see here that if you have, for example, the blue one, this is 7 data points. If you train your potential, sometimes you miss like the atomic energies. They slightly predict inaccurate. But when you include more data points, here the cross like a minus X or plus X, in this case, the hydrogen dimer. So you get more data points, and then you construct any potential while use more data points from Taylor expansion, and then you get the right energies and also the right structures. Again, if you can, using all force information, direct force that you can generate from your first principles calculation, that is the best way to do, but it's just more expensive. In this case, we also demonstrate for water 6 molecules, like you can see. If you use all information, like the force information as a direct force training, you get really very accurate forces, like the absolute error forces is really nice and perfect. But it takes like 8 times more expensive than to include like a force information by Taylor expansion, like you can see. But using Taylor expansion, very efficient, but also improve the force information too. This is for a molecular system. I also did benchmark for a solid, the cathode, the combination of lithium and also some tungsten metals oxides. Like you can see that when we include the force information, why Taylor expansion is also include or improve the force information. And we also test, sorry. Sorry. So we also test by running this simulation by using 2 types of calculation. The first one, only energy only. So you can see that sometimes the MD simulation also explode. But include force information, it's just kind of very stable, right? So, but in realistic, we would like to look at the interface, right? So you have more complicated system, like a solid here as a lithium anode, and also the molecules like a solid as an electrolyte. So when we use, for example, Taylor expansion as an approximation, it's kind of like a difficult. Sometimes it's also too large. And it's also make a kind of like a not very easy to predict when you have like a complicated system. That's why we are thinking that maybe include the same idea, but include like a nonlinear, like Gaussian process regression that could help. So we make use of by introduce or additional more data points by introduce nonlinear Gaussian process regressions that we can introduce more data points by getting the learning from the derivative values that you can see here. And then we test this model again with the hydrogen dimer. On the left-hand side, this is the linear Taylors, but we introduce the displacements in many different regions, different displacements, sometimes with small displacements and also large displacements. So sometimes it's also fail to predict the Lennard-Jones potentials. But for the GPR model, as you can see here, that it fits perfectly. This is just to explain what I just explained in the previous slides. When we have like a very small displacements, like 0.03 angstrom. So both methods tailor additional data and also additional data from nonlinear GPR. Both work very well. But then when we include larger distances, the Taylor expansion slightly fail. But for GPR, it's working really very nicely. And then we also extend this method model to our interface between the ethylene carbonates as the molecules and also the lithium anode. So with the early distributions of, you can see that with the forces that you can see by using the GPR model, it gets much lower. And using the Taylor expansion also improve a little bit, but only use pure DFT data points have a higher errors. So both energy and forces show that using or additional data points included in the training set improve the quality or accuracy of the forces, which is can be really a good way to get accurate forces for our machine learning models in the future. So this is my last slide that I just explained. So we are still do benchmark on how to run MD simulations by getting more data points from the nonlinear GPR models. But in summary, that we want to construct machine learning potentials. We make use of the force informations. So you can see that we can reduce the reference data, use less DFT data by actual DFT calculation, but get more data points from Taylor expansion and also nonlinear GPR. And in this case, that we use more data set, it also allow us to run stable or long MD simulations, which it also will be good for materials prediction or to understand material properties. So I hope that I could demonstrate that training machine learning models on data from simulation, it is useful for accelerating the computational material discovery, and also validate your machine learning model is very important, especially compared with more accurate data or together with experimental measurement. And also sharing your model and database, it will be beneficial for scientific communities. Yeah. Thank you very much.
Thank you, Nonga. Very nice talk and perfect timing. So we have time for questions. Let me run up there.
Thank you for your very interesting talk. I have two very quick questions. The first thing is, I heard that you use artificial neural networks. If I'm correct, you mean multilayer perceptions. Have you compared this multilayer perception-based like models to graph-based models? If you know the crystal, some very popular things called crystal graph convolutional neural network, and a lot of things are based on that. Have you compared it? The second one is, I heard that you use it for molecular dynamics. If you want to predict the dynamic things, you need a very precise potential energy surface. Have you do this before? Do the molecular dynamics before you test? Use something like Energist elastic band or dimer method to test if your potentials have the same potential surface as a DFT one, and you have the same set point. Yeah, I'm serious about this because it's very seldom to hear that someone use like multilayer perceptions in this field. Thank you for your talk.
Thank you very much for the question. The first question that you asked, no, I didn't. I haven't construct or developed the graph network as a descriptor yet. So the descriptor that we use here is based on the two-body and three-body, like a local atomic environment. So that developed first is it with the Baylor and Palinello, and then we extended to more easy to use by including the Chebyshev polynomials, so that it is more easy to use by having many more order.
So you still bring a lot of prior knowledge to your network. You still, okay.
Yeah.
Okay, thank you.
Not the graph network. But then the second question, your question asked like, is this okay to compare my DFT and neural network here, then to see if it's accurate to use in MD simulations, right? Yes. The answer is that I just wanted to make sure that if the neural network potential that I construct, is it really also work for the diffusing part or not? As you can see that the activation energy is really very high here because it is not really optimized. But just to see the part to get the images from the NEB calculation, and then we just predict the structure that we get with NN potentials. So, and this is really just to show that it's really capture the structure that really not included in the training set. Yes. Yeah.
Thank you so much for your answer.
Can you guys help?
Okay, thank you very much for the nice work and presentation. So if I correctly understood it, you said that it's possible to model this electrolyte interfaces using this machine, this method, coupling with for this DFT or machine MED. So my point is, what do you think about the stability issue when modeling these interfaces, either in the anode or cathode parts?
So this is quite complicated, right? This is just to demonstrate that you have really a mixed bond between solids. That you have, like a lithium is like a solid, but our molecules, like ethylene carbonate, for example, in this cartoon, they have mixed bond like oxygen and hydrogen, or carbon and hydrogen here. So we cannot, I mean, it is nice that you can develop big data from the FT directly, but it will be really a large and big data because it is also not accurate by GGA, by PBE, even +1 wow that we already test. So we need more accurate methods, maybe hybrid functional, which is very, very expensive. Because we check, of course, we cannot find the experimental measurement to confirm. So we try to look at like formation energies or binding energies, but there is no experimental measurement to validate our prediction. That's why we try to develop really very large and efficient to get the method, like a very efficient by generate like a, let's say, artificial new structures, but not doing DFT by itself. So this is the idea. Just try to use not too many accurate DFT or even hybrid functional DFT calculation, but we derive more data, more structures by using like expand by Taylor expansions or expand by Gaussian process regression to get new structure and new energy and new force so that we can include in the training set. So this is just the idea. Yeah.
Thanks for the very nice talk. I have two questions, a little bit following up a previous question. So my understanding is that your training data set, basically your training data points are configurations of your system that you put into the neural network. So in your slide 12, you're showing like a time-dependent simulation. So do you have like training data point for each of those times, or these are predicted, you train at a time and then you predict the time evolution? So that's the first question.
I'm not sure if I understood your question. So you see like if I predict also the time?
So in your slide 12.
Okay, 12.
Yes. So each of the red dots, which I understand comes from the Artificial Neural Network, are predicted at different times, right? So for each of those times, do you have like training data points that you learn, or you learn a time, I don't know, 0, and then you predict a time as the times goes by?
So in this case, so we run long MD simulation with neural network potentials. And then we select the frame that we get from neural network potentials and then recalculate with DFT. So this is we get the red one. So because we know that we construct neural potential based on DFT, right?
Yes.
And then we use the neural potentials, run long MD simulation like a 5 nanosecond or 2 nanosecond. And then we selected the frame from the A and MD, and then we recalculate the DFT with that structure.
So you have new sample set at each time and you learn from that?
That's correct. But in this case, this is independent that we just run, you see, we run MD simulations of the water structure that we have it here, and then we predict DFT of that structure, that recalculate single point DFT of that structure that we get, and then we see the error bar.
I see.
Between.
Interesting. And then my second question is actually the structure of the neural network you are using. He mentioned graph neural network. You said you are not using that. Are you using fit for neural networks? Because if you use fit for neural networks, I imagine that you basically take the structure of your system and then you have to basically flatten it into like a single layer that you input, but then you totally lose the knowledge of the symmetries. And so how do you do that in practice?
You mean we use feed-forward neural network?
Are you using fit for a neural network?
Yeah.
Okay, then it means that you take basically different positions of your atoms and you flatten it as a vector to put in your neural network. But then you totally lose, you totally lose the idea of the symmetries, right?
But actually it's not like that because we transform the atomic structures to the local environment, right? And the neural network only will learn just the number that you extract of the atomic structures and energies, and then transfer to the machine learning models. So our neural network don't learn atomic position like XYZ coordinate directly, but we transform the XYZ coordinate to set up the local
so there's a pre-processing step. Okay.
Yeah,
I
that's
see.
correct.
Okay, thanks.
Yeah, I skipped this part, sorry, because maybe it's already known before, sorry. But we can talk about the descriptors later. Yeah. Thank you very much.
Great. Thanks again, Nong. Great pleasure. And the next talk will be given by Zili from ICTP here on the phase diagram of iron in Earth's core from deep learning. Give you a signal at 5 minutes.
Okay, thank you. Okay, just So, okay, good afternoon. My name is Zhili. I'm a postdoc here, working with the Central Scale. So today I'm going to show you basically is a different topic, which is about the phase diagram of pure iron in the Earth's core from deep learning. So this is the outline of today's presentation. So I will start to show that actually we can apply the methods from computational material science to study the problems in Earth science. Then I will move on to today's main topic, the pure iron at extreme conditions. So in order to study the phase stability, I developed a neuron level potential for that. So to study the mechanical stability of the BCC phase, then I will show you the phase stability of all the possible solid iron phases. So this is followed by a very short, a brief summary. So Earth is the planet we live. So of course we want to understand what is inside. Then geophysics is the method you can use to decipher the density, the compression wave velocity, and the shear velocities as a function of depth. And based on these continuities, we can divide the Earth into different layers: the crust, the mantle, outer core, and the inner core. And the shear velocity for Earth outer core is 0. That means it is in the liquid state, and for the other parts, it is in the solid state. But that is not enough. We also would like to know what kind of minerals that could be present
at Earth mantle conditions and at Earth inner core conditions. So this could be provided by mineral physics. And in the figure on the left-hand side is one of my favorite. So they clearly summarize what kind of minerals that could be present at the Earth mantle conditions. So probably you are more familiar with this phase, the ferropericles. So it's a magnesium-rich FeO. So because it's FeO, no, it's really high debated about this phase at low mantle conditions. But from mineral physics, we cannot know precisely what is the relative percentage of different minerals. So for this, we need to know the thermodynamic properties for all these minerals. But in order to check our predictions, we need to know the elastic properties for all these minerals. Of course, Earth is not static, it is dynamic. So you have subduction zone, that means very cold, very heavy materials that will sink into the Earth's deeper interior, and these very light and hot materials will rise up along this core mantle boundary. In order to study this dynamic process, we need to use fluid dynamics. For this, we need to calculate the viscosity or plastic properties and the transport properties for different minerals. That is the input for this fluid dynamics. But nowadays, I realize the isotopic fractionation is a new trend in our field. So in the past, so one of the central problems for earth science is to understand all these properties for different minerals. And in the past, it's very difficult. But in the last 20 years, lots of methods has been introduced from computational material science that really make the geologist's life easier. I just want to show a few cases just to explain to you the chemical reaction when the computational material science meets earth science. This is from my previous work. The first case I want to show you is about the deep carbon circle. This is actually my master work. At that time, people were more interested in the deep carbon, the carbon circle in the deep Earth's interior. We know that at the Earth's surface, most of carbon is stored in this carbonate phase, such as the siderite. But from our calculations based on ab-initio largest dynamic simulations, we found it out at high pressure and high temperature, it will dissociate into this iron-rich carbonate phase plus diamond. So from our study, we found it out this diamond is everywhere in the low mantle conditions. We also did a test and compared the performance of different exchange ecology functional, and in this case, we found this hybrid functional performs better than the DFT plus U method. The second case I want to show is about the formation of moon. This is actually my PhD thesis. So after the Apollo's mission, people start to realize there's lots of similarities between the moon and the Earth. In order to explain these similarities, the giant impact model is actually developed. So in this model, the Mars-sized object will collide with the proto-Earth. So it results in the formation of the proto-lunar disk. From this disk, the moon is formed. But for us, we would like to know the behavior of these impactors iron core during this giant impact process. So for this, we use ab-initio molecular dynamics simulations to calculate the Huygens lines. The Huygens lines tells us the peak conditions that could be reached during this impact process. So as long as you give me the impact velocities, I can tell you the highest pressure and temperature they can reach. We also calculate the entropy along these two Huygens lines. Then after we obtain all this information, we develop a thermodynamic model and we found it out lots of iron vapor that could be produced during this impact process. Then after my PhD work, I got opportunities to continue my work on this pure iron to stay with the central scale. So this time I'm be focused more about the phase stability of this solid iron phase. And of course, iron is the major component of the Earth's core. Every properties about this phase is very interesting. For example, we would like to know its melting curve. We also want to know that its thermal conductivity at the Earth core conditions. And of course, you can go beyond that. You can determine the melting curve to the super Earth conditions, because we would like to know that whether there's life in the other planets. Because due to these very important properties, lots of work has been done in the past. I just give you a very brief summary of this work. So suppose suppose the most stable structure before melting is ATP iron. The F et al. Perform ab initio molecular dynamics simulations up to the inner core boundary. They found it out that the melting temperature at the inner core outer boundary at around 330 GPa, the melting temperature is about 6,000 Kelvin. But the problem is that their simulations use a very relatively small simulation. Number of iron atoms is only 150. Probably it will make a difference if you use a larger simulation cell. So a following work done by Lau et al., they performed molecular dynamic simulations with the embedded atom models. They found that actually the melting temperature at the inner core outer boundary is only 4,000 Kelvin. So it's actually 1,000 Kelvin lower than the estimation done by F et al. That will make a huge difference if the melting temperature is very low. And the debate is also present in the experiment work. And one of the experiments support the high melting temperature at the Earth's inner core outer boundary. And one of the work done by from the K-Hilosas group, they found out the melting temperature is still very low. So my conclusion is that the melting curve of this AGCP iron remains highly debated. Then after the publication on the melting curve of this AGCP phase, people started to realize that probably AGCP iron is not the most stable phase before melting. And indeed, the work done by Cataldo and Belnoschko, they found it out. Actually, at high pressure and temperature, the AGCP phase will transform into the BCC phase. That's very interesting. I mean, if the BCC phase is present at the inner core conditions, we have lots of stories has to be rewritten about the geodynamo. However, with the rise of the computational power, a larger simulations has been done by Godwell in 2015. And they found it out, actually, the BCC iron is even not mechanically stable. It is located at the saddle point along the beam path. That means you deform the BCC iron along and change its C/A ratio. But this picture is changed again by Belnoschko in 2017, and the new phenomenon is emergent. They found out in this BCC iron, they found out this fast diffusion. Because this is a liquid component, it will entropically stabilize this BCC iron phase. So my conclusion about stability of BCC iron, so it remains highly debated. And of course, probably FCC iron is the most stable phase. And there's only one work to support this idea. As you can see in the right-hand side, the figure on the right-hand side, that actually at high temperature, at 6,000 Kelvin, that the Gibbs free energy of the FCC phase is lower than the AGCP phase. So to summarize, the thermodynamic stability of the solid iron phase remains highly debated. And in our work, we would like to solve all the problems in one piece of work. So for this, we develop a neural network potentials for iron, and the packaging we're using is called DeepMD, which is developed in the Rebecca Carr's group. And I won't give too many details about this method because it's already a dedicated talk on this. I just want to stress one more point that you can actually treat deep learning as a function with the atomic positions as an input and the energy force and stress as the output. And nowadays, there's a lot of packages you can use to train the neural network potentials. And they differ a little bit in the atomic descriptor and the neural network structure. And in DeepMD, they use some embedding techniques to construct this atomic descriptor. As you can see, that is all matrix operations. That's very good for GPU calculations, because nowadays GPU is a new trend. And they also try to use a residual neural network structure, which will greatly enhance the learning performance for very deep neural network. So after we train the neural network potential for iron, we use an independent test data set to characterize the performance of the DP models. As you can see from the figure on the left-hand side, the x-axis represents pressure and the y-axis represents temperature. We actually characterize the performance of DP models on energy, force, and pressure over a wide range of pressure and temperature conditions. And for one of this column, that from top to the bottom, it represents a different phase, such as liquid, this is FCC and AGCP and the BCC phase. And we also check the performance of the DP models with a different number of atoms, just to make sure that its performance remains stable if we want to perform larger scale simulations. As you can see from the upper panel, that the root mean squared error of energy is less than 6 MeV per atom. Think about this, we are performing simulations at 6,000 Kelvin. The KBT is very large. And the error on the force, so in most of the cases, is less than 0.3 eV per angstrom. That's super accurate. For the pressure, in most of the cases, the root mean squared error is less than 0.6 GPa. We also did a comparison between our DP models and the EM potential developed by Noshko. As you can see that the root mean squared error of force predicted by EM potentials in the most of cases is larger than 1 eV per angstrom, so it's huge. After we check the accuracy of these DP models, the first questions we want to solve is the mechanical stability of the BCC-RN phase. For this, we use different techniques. And the first technique we're using is to directly calculate the elastic constants. I just remind you that for FCC or BCC phase, there are 3 independent elastic constants, the C11, C12, and C44. And the stability conditions requires that the C11 must be larger than C12, and the C44 is also positive. And for this, we use 2 different stream metrics. We deform this, the BCC-RN lattice, then we run MD simulations to obtain this resulted stress tensor. From this, based on this, we can estimate the elastic constants. So after we obtain the elastic constants, we estimate all the pressure temperature conditions, that is C11 is equal to C12. So above this BCC instability line, the BCC-RN phase is mechanically stable, and below it is not mechanically stable. We also check our predictions based on this elastic constant calculations. For this, we take several conditions along this instability line. Then we deform BCC-RN along this beam path by changing its C versus A ratio. After we deforming this BCC-RN, we calculate the stress difference. And from this, we can calculate the work that is done to deform the BCC-RN. And in the figure on the right-hand side, this tetragonal distortion T, you can treat it as autoparameter. If it is equals to 1, that represents this structure is the BCC phase. And if it is equal to 1.26, it corresponds to the FCC phase. So based on the work that is done to deform from the BCC phase to FCC phase, we can sum it up to calculate the free energy difference between the BCC phase and the FCC phase. However, from our calculations, we found it out that actually the stress difference does not change continuously as a function of the tetragonal distortion T. That means there's a phase transition here. We cannot use this method to estimate the free energy difference between the BCC phase and the FCC phase. But we can actually integrate this stress difference around the T equals to 0 to show that actually the BCC phase is located in a local minimum. So now we finally sorted out the mechanical stability of the BCC-RN. We found it out that BCC-RN is mechanically stable at Earth inner core conditions. So we move on to calculate, but we would like to know whether temperature alone is enough to mechanically stabilize BCC-RN phase. So for this, we use a SHA. I want to give more details about this method because in Dublin, there's a dedicated talk on this. So from SHA, we can obtain this auxiliary photon spectrum. It agrees very well with the previous studies, use a very similar approach. But the problem is that for this strongly harmonic system, whether this auxiliary photon spectrum is meaningful is problematic. So there's another method in SHA which is called positional free energy Hessian, which is a second-order derivative of the free energy with respect to the atomic positions. So as long as you find this unstable mode like here, collective motions along this imagined mode that will decrease this free energy of the system. That means in this case, it is not mechanically stable. We also consider the effects of temperature. We found it out that temperature will greatly stabilize the BCC-RN. As you can see here, at 4,000 Kelvin, the frequency at the endpoint is negative, but with increased temperature, the unstable region shrinks towards the Brillouin zone center around the gamma point. However, from this calculation, we found it out. Even at 7,000 Kelvin, BCC-RN is not mechanically stable. So there's a difference between the calculation with the shell and our elastic constant calculations that actually reflect the contributions of the self-diffusion. So the self-diffusion will stabilize BCC iron at the highest temperature at 7,000 Kelvin. So our research highlights the roles played by self-diffusion in mechanically stabilize the BCC iron. Then we move on to calculate the Gibbs free energy for different phases because we want to build the phase diagram. For this, we use thermodynamic integration method to calculate the Gibbs free energy for the FCC phase, for the ICTP phase, and for liquid phase. Basically, in thermodynamic integrations, you couple your system of interest with a system that has a known free energy. But this method does not, you cannot apply this method to the BC phase because BC phase has a self-diffusion. If you do this, the simulation will not converge. So for this, for BCC iron, we use a two-phase coexistence method. In this method, we put the solid iron and the liquid iron in contact. Then we run simulations in the NVE ensemble. From the simulations, we can obtain the equilibrium pressure and temperature. But as you can see here, there's an interface, okay, that will really affect the final results. But we don't have such problems because we can systematically test the effects of the number of atoms on this melting pressure and the temperature. And during the simulations, we constantly monitor the structure change just to in case whether there's a new phase that is present. And this is in this figure, I show you the Gibbs free energy difference calculated with the DP models. And the different color represent the different temperatures. And this dotted line represents the liquid phase. And this solid line represents the BCC phase. And this dashed line represents FCC phase. And we treat the ICTP iron as a reference. As you can see, at 5,000 Kelvin, near the melting point of the BCC of this ICTP phase, the Gibbs free energy difference between FCC and ICTP phase is on the order of 10 MeV atom. So we now start to worry about whether the accuracy of our DP models is enough to distinguish these two phases. So for this, we use a free energy perturbation theory to check the accuracy of the Gibbs free energy of our DP models. So in this method, we first run simulations in the MPT ensemble, then we extract several snapshots to run this density function theory calculations. From these calculations, we can get the energy at the DFT level. Then we plug in back to this formula, we can calculate the free energy, the Gibbs free energy difference between the DFT potentials and the DP models. And from the figure on the right-hand side, you can clearly see that actually the accuracy of the Gibbs free energy in our DP models is quite good. It's usually, in most of the cases, is less than 3 MeV per atom. The most interesting feature of our DP model is that its performance is really stable with respect to the number of atoms. Just to give you an example, let's say for the ICTP phase, the free energy difference between the DFT model and the DP model at around 200 atoms, it is around minus 1 MeV per atom. If we use a much larger simulation cell at 500 atoms, it stays quite stable to minus 1 MeV per atom. So that's really good because that indicates that other potentials can be used for larger scale simulations. And this is the major conclusion about this work, that we finally sorted out the thermodynamic stability for all the solid iron phases. And in this figure, this blue line represents the melting curve of this BCC iron, and this green line represents the melting curve of the FCC iron, and this red line represents the melting curve of the ICTP iron. As you can see that ICTP iron has the highest melting curves. So that means ICTP iron is the only stable phase before melting. There's no solid phase transition at a high temperature. Another feature is that the melting curve of this BCC iron phase at around 4,000 Kelvin, if we extend this blue line to around 4,000 Kelvin, is actually fall within this instability region. So that's the reason we cannot perform the simulation here to determine the melting temperature of the BCC iron. And the inset is a short comparison between experimental work, and from our calculations, we do support the melting temperature at the inner core outer boundary is very high, it's around 6,000 Kelvin. So after we know that HCP iron is the most stable phase, we would like to know whether this phase yield a seismic velocity that is compatible with the geophysical observations. For this, we calculate the shear velocities as a function of temperature, and the inner core temperature is very close to the melting temperature of the HCP iron phase. As you can see that at the melting point of the HCP iron, the shear velocity is still very high comparing to the geophysical observations, which is 1 kilometers per second high than geophysical observations. So in our previous work that is accepted last December, that we suggested that it is probably caused by the effects of viscous grain boundaries, because we need to transform or translate our single crystal elastic constant to the shear velocity for polycrystals. And there's another work suggests that probably the low shear velocities is caused by the superionic HCP iron alloys. That means you put light elements in this in the interstitial side of the HCP structure. But we found that actually the BCC iron have very low shear velocities that is compatible with the geophysical observations. That's very easy because now we found out BCC iron is not thermodynamically stable, but it has a very good geophysical properties. And this is my summary. So finally, we determine the phase stability for the pure iron up to Earth's inner core conditions. And it remains debated about the origin of all the observed low shear velocities in the Earth's inner core. And thanks for your attention.
Thank you for the great talk, and we're open for questions.
You show that the energy differences are not large.
Yeah.
Besides, so can we trust DFT energies, or there are Monte Carlo estimation on the relative error of DFT? So what is the scale? Besides, because you study the error due to the neural network.
Yes. So the energy we use
eventually could be the BCC is more stable because DFT is not predicting the right energy.
So the energy we are using here is at the DFT level. We use a free energy prediction theory, but the problem is that we don't really know that. We actually did a test with a different exchange correlation functional, and we confirm that our conclusion will hold with the different exchange correlation functional. But the problem is that we still don't know the accuracy about this DFT at a high temperature. Yeah, that remains a problem. I mean, the normal quantum Monte Carlo simulations usually put the electron temperature at T equals to 0, but we will not hold for this case. But temperature is the electronic temperature is very important. That will greatly stabilize the BCC iron phase.
So can you help me just understand a real basic thing? You have a very nice curves up there for different structures, and you've shown us some stability arguments. But if I look at that curve, which phase is the most stable?
It's HCP, yes.
It's HCP, and,
yes.
How do you know that from that graph?
How I know? Because let's say, let's compare the melting curve of BCC iron and the HCP iron. At these conditions, the Gibbs free energy of the liquid phase is lower than the BCC phase, but it is still less than the Gibbs free energy for the solid HCP phase. So that means the HCP phase is the most stable phase.
Okay, so if you had a real melt of liquid and you cool it then you would see that structure is more stable.
Yes,
would be the first one to solidify.
Yes.
Good. Thank you.
Other questions? When we tried to predict the Gruneisen parameters from, in our case, we were using the Gaussian approximation potential for BCC iron. It was incredibly difficult, and one needed to have absolute K-point sampling convergent to make sure all the training was consistent. Is this something that you also observed, or do you have any comments there?
We didn't really calculate the coordination properties, but for our training data set, it's always larger than 200 items, so then we use 2 by 2 by 2 like key points to sample the brilliance zone.
Yeah, but indeed we were surprised because, I mean, in an equivalent system with just, say, 1 atom of iron, we needed to go up to 40 by 40 by 40 sampling, or equivalent dense sampling on the supercells to actually be able to get the right Grüneisen parameter. And the way we interpreted data was that the machine learning was getting a little bit confused by having supercells of varying size with somehow still some remnants of K-point sampling. But maybe GAP is more sensitive also to this and this.
Probably, I guess you're working on the lower temperature one, probably.
Yeah,
that's the reason.
sure. Yeah.
Now the temperature here is very high.
Yeah.
So the density of steel will be very smooth.
That could also be,
yes.
Yeah. Okay, I think if there are no more questions, we thank Z and all the speakers. I'm looking at Nicola Seriani here. We are meant to start at 2 o'clock, but maybe we should do 2:15. So, yeah, so everyone can enjoy ICTP culinary might. And so we meet again at 2:15 here.
Which get together?
Friday afternoon?
2 p.m. Is it okay? Yes.
Right.
Thank you.
I mean, I think if we just meet and introduce ourselves, and each of us can say something about the programs is leading. You can say something about you.
That's fine. You invited me. Now I understand.
But maybe you can still say a few words, 1 minute.
Actually,
and I don't know, maybe you want to say something about assessment, and maybe I say 1 minute about assessment act, for example. No, so and there will be each. I mean, because Matteo Gatti will be there, a lot of other people. So if you spend 1 minute each, the say, and then everybody introduces the African scientists, that's already probably 40 minutes. And then we'll see. It's not very structured. Well, in that list, in that email, everybody was clear. So I invited all the people somehow are involved in African things. Mazzari, Jeff Hinton, Matteo Gatti, Lucia Raini, Sean, of course. So if you meet somebody that don't know, extend the invitation.
It's difficult. It's very difficult. That's why I said it's difficult.
Ah, okay.
Am I saying wrong?
Oh, okay. Well, that's great. Well, that's great. Okay, I will try to remember.
This is just a model. Just a model to try, right? To understand how procedure and forming and breaking. But in the
Oh, well, we could make a general announcement. Hoping that not everybody will come, otherwise it will be unmanageable. Yeah, but we can say that. We can say that. I mean, I still suspect that a few people will leave right after the end, and a few people will not be interested. So I guess we can probably say. And if there are too many people, we'll find a way. I mean, to chat, exactly. It's anyway just a get together. No? Yeah, we can say it. Probably we should say we can tell a reminder on Friday morning. Yeah. Well, essentially, yes, it's here. There are only the three of us,
when you're coming
and Chopin, right? So we can have a discussion if you want.
Maybe Friday I have a meeting in the morning.
Well, since it's only the three of us, we can catch over lunch or over coffee or at the end of the session, for example. No, and see what we can discuss. Okay. Okay, let's try. Oh yeah, well we can maybe yes. Okay. Okay. Are you doing the lecture? Yes. Yes.
So Nicola, you work also on battery.
Yes.
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 Well, yes.
I don't dare to show. We can test and run so many and we don't have conclusion. This is the reason why I don't show.
It's so...
I cannot show all mistake. I know what is so wrong, but I cannot bring to talk. I only show what is good.
It's really a tough field, right?
We have to have a close discussion what is wrong. But open discussion.
No. Yeah. Okay. It was yes. Okay. So
thank you for the nice talk. You're right with me. Yeah, that is the word. It's very
difficult. It's so difficult.
Well, especially
the interface.
Especially this is the interface is huge.
I didn't dare to show many results that I don't feel confident.
No, also because
expert here.
Expert in the techniques, but probably not in the problems or in the applications. So
shall we sit here or here? Whatever. Maybe here. Here is better. Oh, I'll get out anyway. Okay.
that's exact. So for instance, I cannot read this.
I know by the group they come from.
Yeah.
So that's how in fact, I was in just on Monday. So that was for a job interview in India. And they give 20 marks based on their credentials. So those who got 20 out of 20, they got the worst.
Yeah, no, absolutely.
So, and then we had only 30 marks in our band. So you can't give minus.
That's true. And yeah, it's very true. We have an oral interview as a second stage, but again, I mean, it's like a few minutes when you actually ask.
Yes. I've worked with last quantum espresso.
Yeah.
And
I see these things.
ICTP.
Yes, whoa.
So I asked, what are the differences between them? Then we got a lot, then he said, you have to pay for once. And I said, are there any technical differences?
That's actually a very good question. I think I'll borrow that. No, that's true.
Then he found out and he said, class is all electron calculation.
Oh, no, okay.
Then I said, no, it's not. And then I said, why? How do you decide which code to use for which? And he had no clue. Then he said he's going to do machine learning, he's going to do big database. But he didn't know what's machine learning. I said, can you tell me what is machine learning? He had no idea. So, no, in fact, one of the candidates. So he is a person who did a lot of PhD applications. So I said, what is a density function? He said, with that you can calculate that sort of density or something. And I was like,
no, but
this guy
I
was
totally
at that
understand.
level. This guy was at that level.
Yeah, but it's a bit of a problem for us because we cannot. So we have a lot of rules in this
That's what
selection.
Maria was saying.
It's
You
really
have to justify.
yeah.
If you reject them.
It's in principle supposed to be objective. How can we be objective? Of course, like a ranking, something that you do. You put a formula, you put the numbers, and you get a number.
Any of this interview committee, we keep the note of what are the questions asked and what are the answers given.
No, but that's a bit low.
No, but some bureaucrat won't understand that. They will only
Exactly.
understand number of publications,
Yeah, that's
age
the problem.
index,
Yeah.
We can always say these are the questions asked, and as judged by the expert,
Exactly.
these were
That's what
incorrect
we
answers.
say. So we can use a lot the second stage for this, but but the first stage is a bit random, as you said. So it's matter of luck, really. So thanks, really, thank you for the effort. Okay, so you're the next one. Yeah. So last minute, they ask you.
Yeah, sorry.
No, don't. It was.
And thanks. You
No.
all agreed.
No, thank you because it's very good.
Because some of them said whether they can be online, but then we thought then the spirit will get lost.
So I tried my own laptop and it seems to work. Otherwise, I think you can upload a PDF. It's a PDF.
Is this your laptop?
No, this is the desktop. That is.
So you can try. If I fall asleep in your talks, it's because I got in very, very late last night.
Yeah, I can imagine. Yeah.
So, I'm there to keep an eye on her.
Yeah.
But I might say myself. So this is what I'm really scared of, that I'm going to be chairing the session and I will fall asleep.
So I'll do my best to keep everyone awake.
Yeah, make it very humorous.
Yeah, no, that's fine. That helps a lot. How do we go into screen?
Control L, I think. Or you can go to view and then
should be.
Yeah. That's fine.
button and keep, yeah. Ah, I see. There's a lag of 1 second. Okay. Coherence, I don't like it. Just there is a small mistake in the program. Yeah, so that, but I think everyone is yeah, that's how it could be. Yes. Plus, at least in economy class. Thanks very much.
Ok, le chiedo se può togliere il badge. Prova? Ok. Sense working. Ho già provato. Può lasciarlo qui sotto?
Sì, just check very quickly without spoilers. Okay, it works. Without spoiler.
Continue. Yeah, so the 5 minutes is a bit difficult because people do ask a lot of questions.
Like 20 plus 10.
Yeah, 20 plus 10. Now we can't even tell speakers 20.
Ciao. Grazie.
So there are only 2 before the coffee.
Yeah.
We'll be short.
And I'm going to ask Tanushree to go up and down with the mic because my knee hurts. How is it from Lorenzo Monacelli?
Yes. And another thing that in the program there is written the wrong affiliation. The correct one is the École Polytechnique Fédérale di Lausanne.
Okay.
Thanks. Just to upset Nicola. Yeah, I think it's my fault.
Hello. Nice to see you.
Okay.
How was the travel?
Good. Not so bad.
Okay.
Yes, I arrived yesterday at 10 o'clock.
parts in the floor and parts will be hanging. I noticed, yes, I noticed. I don't know why, how is that possible? Well, if you remain 15 minutes later, it will be great.
Do you want me to be strict with the time for questions, or I let the questions go?
Maybe it's better.
Whom should I ask for uploading the talk? I want to upload the talk.
We are starting in 2 minutes, so maybe during the coffee break.
Ciao.
Se ti ricordi di me, sono male.
Sì, sì.
It will be here around the lecture hall. Yes.
Okay.
In the entrance, and there is a floor here.
Yeah. Okay.
Oh, okay.
mic is for the questions? The mic for the questions.
Sorry, you have your own, right?
Yeah.
Okay, welcome back. So we have talks from 2 different sessions now. The first one is a session called Methods for Phonons and Thermal Transport. Oh, I forgot to introduce myself. Sorry, I'm Shobhana Narasimhan from the Jawaharlal Nehru Center for Advanced Scientific Research in Bangalore in India. So we will now have a talk on thermodynamics and dynamical properties of strongly anharmonic and quantum materials. The talk is by Lorenzo Monacelli, who is from EPFL in Lausanne.
Thank you very much for the introduction. And I want to thank the organizer for giving me the opportunity of speaking this very broad audience today. I am Lorenzo Monacelli, and I will tell you something about how to compute thermodynamic properties in materials and dynamical properties in materials that suffer from strong anharmonicity in the ionic displacement and also show sizable quantum fluctuations. So why we are interested in computing thermodynamical properties? Because it's the study of a system in equilibrium, and in particular, we are interested in linking what are the microscopic properties of a material that we can simulate in a computer to the mesoscopic properties that are, for example, described by temperature, volume, and number of particles. And these links is done by statistical mechanics, and in particular, by a quantity which is fundamental in this field, which is the free energy. So if we know the free energy of the system, we can establish which is the equilibrium, a specific thermodynamic condition. For example, in a canonical ensemble, the free energy, the minimum free energy at fixed temperature, volume, and number of particles determines what is the equilibrium. And so we can use this property to compute phase diagram. Now, from thermodynamics, the free energy is simply the internal energy minus the temperature times the entropy. And this is linked to microscopic properties of the system with this equation, which is quite simple, which is just the internal energy is just the average of the Hamiltonian, and the entropy can be computed with the Boltzmann definition, is just the average of the logarithm of the density matrix. Now, in this equation here, in principle, there are both ionic degrees of freedom and electronic degrees of freedom, but for thermodynamic room temperature or temperature which are lower than thousands of Kelvin, the electronic degrees of freedom are not so important, at least directly, because the temperature is not sufficiently high to excite electronic transitions. Therefore, in most cases, we can do a very good approximation, which is the Born-Oppenheimer approximation, which consists in integrating out the electronic degrees of freedom and treating the system as it is always in the ground state of electrons. And therefore, the degrees of freedom that I'm describing here are ionic degrees of freedom, so are ions. And this density matrix actually describes the ionic positions. This Hamiltonian here is the Born-Oppenheimer Hamiltonian, which can be computed at any level of theory, density functional theory, more sophisticated one like quantum Monte Carlo, or even machine learning potentials. Now, the free energy is very important because not only allows us to describe which is the equilibrium of a system, so the phase diagram of a system, but also its thermodynamic properties through the derivatives of the free energy. So the derivative of the free energy with respect to volume gives us the pressure, for example, and this allows us to compute for thermal expansion of a material. And if we do other derivatives, we can compute thermodynamic observables like the bulk modulus, the specific heat, the heat capacity, and the thermal expansion. And so we can completely characterize a system of its equilibrium properties by just knowing the free energy and its derivatives. So it's a very important quantity. Unfortunately, it's also extremely challenging to compute free energy from a simulation. And the reason is that this average here
cannot be done by a simple sample sampling of the potential energy like we are used to compute observables. And the reason is that this logarithm has an important contribution from region of the phase space which have a very low probability of occurring in a simulation and in the equilibrium condition. Therefore, we cannot compute this integral using standard approaches. However, there are methods that have been developed to compute free energy, and one of the most effective methods is so-called thermodynamic integration. And in this method, what we actually do, we define an auxiliary Hamiltonian for which we know how to compute the free energy because it's analytical. For example, it could be an harmonic oscillator. And then we parameterize a Hamiltonian with a parameter lambda so that this Hamiltonian is equal to the auxiliary Hamiltonian when lambda is equal to 0, and is equal to the exact Hamiltonian when lambda is equal to 1. And then we can integrate between lambda that goes from 0 to 1 and get the exact free energy. So this equation here is exact, and is a way of computing the free energy. And the cool thing about this equation is that actually this derivative of the free energy can be computed using standard sampling techniques because this object here is actually an observable that can be computed with standard approach. And this is just the difference between the exact potential, for example, the one we get from density functional theory, and the auxiliary one that define our auxiliary Hamiltonian. Now, this is, as I told you, a feasible approach. So there have been already many calculations exploiting this approach. But it can be extremely expensive anyway. And in particular, this is true if our system suffers for sizable quantum fluctuation, because then sampling this object here for many values of lambda between 0 and 1 becomes challenging because molecular dynamics, for example, is not anymore a good way of doing this sample. We need to rely on more sophisticated approach like path integral, and doing this with many values of lambda could be challenging. It is not impossible. Some cases has been achieved, but it's still computationally extremely expensive. So we wonder, is there a way of starting from this approximation, so from this exact expression, to get an approximated one which is more feasible computationally? And the first thing we can think of doing is actually to assume that this value here inside the integral is a constant, and then we can take out from the integral, and we approximate the free energy in this way. Now, this is accounting for anharmonicity because this term here is correcting our Hamiltonian accounting for all anharmonicity. And we can prove something which is very important for this approximation here, is that this approx symbol here is actually a lower equal. So we can prove that the exact free energy is always below the free energy we obtain with this approximation. And this is very interesting because while this is already a quite good approximation for the free energy depending on the starting Hamiltonian, auxiliary Hamiltonian, we can do more. We can now say that among all possible trial Hamiltonian that we can use, the one that gives us the lowest free energy as a final value of this equation will be the best one, because we know that the exact free energy will be always lower than this value. And this allows us to formulate a variational principle in which we can say, OK, now we can choose among all possible Hamiltonian the one that gives us the minimum value of the free energy. And indeed, we cannot choose all possible Hamiltonians, but only Hamiltonians for which we know how to compute the free energy. And these are, for example, harmonic Hamiltonian. And that's how we define the self-consistent harmonic approximation, it's called, in which this Hamiltonian is chosen as the most general harmonic Hamiltonian, and optimizing this Hamiltonian just means optimizing the parameters, which are this auxiliary force constant matrix and the average centroid position, the centroid position of the atoms in the system. And by optimizing this, we can compute the free energy. And the cool thing about that is that we don't need to evaluate, to do any kind of molecular dynamics here, because we know how to sample this Hamiltonian analytically, even for quantum fluctuation, very quickly. So we don't need to thermalize anything. We just need to extract. We need to perform the minimization, but we need just to extract randomly distributed atomic configuration and compute this average here. And this is extremely efficient and can be done ab initio quite easily. And I will show you an application in which we did this with Nicola Marzari, very interesting, which is the case of metal halide perovskite, which are a very important family of systems which for application in perovskite solar cells, which is the fastest growing solar technology nowadays. And the very cool thing is that one of these perovskite halides reached the power conversion efficiency of 25.2%, which is competitive with silicon, which have been achieved after 60 years of optimization, while this is pretty young candidate. The problem of these candidates is that they contain lead, which is toxic. And so we need to find a substitution to lead, which can be feasible. And this perovskite here with tin is one of the most promising eco-friendly solution. But while its performance are competitive with the one of lead, it has a major drawback, which is that it's unstable if we expose this system to the air. And what happens actually is that it tends to oxidize, and it decomposes in a different phase, which is not perovskite, it's a yellow phase, which then further oxidize and transform and degrade the performance. So if we can prevent this perovskite to transform in this yellow phase, it will be extremely useful. And the problem with this perovskite is that we don't know the real phase diagram. And the reason is that this is a phase change material, which have the all perovskite polymorphs from cubic, tetragonal, and orthorhombic at different temperatures if the system is synthesized under inert atmosphere. But if we take this system and we expose to the air, it rapidly changes the structure into this yellow phase, which can be then restore the cubic structure by rising the temperature above 425 Kelvin. So this is a quite complex phase diagram, and it's not clear which one of these two phases is actually more stable. So is the air simply pushing this perovskite structure toward the real ground state, which is the yellow phase, or rather it's just a surface effect of some kind of impurities that generates at the surface, and so a more complex effect. And to answer the question, the only way we can do with calculation is computing the free energy of the two phases and compare them. And that's what we did. And this is the result, interesting result we get. So here I'm comparing the free energy of the yellow phase here in orange with the free energy of the perovskite structure. And what we observed that in the working condition, which are between 300 and 350 Kelvin, we observed that that actually the cubic phase of the perovskite and all the perovskite structure are more stable than the yellow phase. So it seems that the perovskite structure is more stable, and so this formation of the yellow phase is not an intrinsic effect, but it's due to surface and impurities and other more complex effects, but that can be treated with better engineering of the system. And we can also go beyond, and if you wonder about the accuracy of this free energy, I can show the next slide in which we, thanks to the derivative of the free energy, we can characterize the thermodynamic properties of this system. And for example, here we relaxed the volume, including all anharmonicity at finite temperature, thanks to the fact that we can compute the pressure to the derivative of the free energy. And we computed the thermal expansion, which is in very good agreement with the experiment, and also the transition between, here you see this angle here that identifies the difference between an orthorhombic cell when theta is different from 90 degrees to a rhombohedral cell when theta becomes 90 degrees. And as you can see, the system is transit. The experimental transition temperature is 360. And so if you look at this line, this point here is 350 Kelvin. So it's very good agreement with the experiment. And also the transition between the rhombohedral structure and the cubic structure occurs when the A and C parameter becomes the same. And as you can see here, this occurs at 450 Kelvin in our simulation, while the experimental transition temperature is found to be 440 Kelvin. So again, a remarkable good agreement, which seems that this method is very powerful and very predictive. So this is another example that we recently, that has been recently accepted in Nature Physics, and this work is done in collaboration with Michele Casula, which we'll present tomorrow, and so probably we'll give you more details about this. on the phase diagram of hydrogen, of high pressure hydrogen. Here we are at 0 Kelvin, so all the anharmonicity is given by the quantum fluctuation of the H2 molecules. And you can see here the difference between the static phase diagram, so the enthalpy you get from a standard DFT calculation, and what you get if you add on the top of the static enthalpy the harmonic 0-point energy, which was the state of art before this work. And then we can add the total contribution of the free energy using this self-consistent harmonic approximation. And as you can see, the phase diagram changes completely. And in this last term here, we observe a first molecular to molecular transition between phase 3 and phase 6 of hydrogen. And then we observe the atomization at 577 Kelvin. And this is very important because the atomic phase of hydrogen is predicted to be a room temperature superconductor. So it's very interesting. And the interesting thing about this work is that so we reproduced this transition temperature, which has been observed by an experiment to another molecular phase. And we did the calculation also for deuterium to try to predict what is the isotope effect. And we obtained a shift for this transition of 32 GPa. And after we published on arXiv this work, almost contemporary work by Paul Hubert measured this isotope effect to be 35. So we were, both of us, not aware of one of the other work. And we got a very good agreement with the experiment. So I hope this can convince you that this method has really a very important predictive, even in very difficult systems like this one. So, but these are thermodynamics. So this is to characterize thermodynamics. But sometimes we want to do more, and we want to study the phonons. However, there is a caveat on all these methods, both the SHA, so the self-consistent harmonic approximation, that even similar methods like self-consistent phonon, temperature-dependent energy landscape, and these similar methods as these have, is that one is tempted to take these phonons defined by the harmonic auxiliary Hamiltonian and define phonons through them. But unfortunately, this is not correct, because this Hamiltonian is just an auxiliary quantity to describe the thermodynamics of the system. To compute the phonons, we need to ask ourselves what a phonon really is. And a phonon is an excitation of the lattice. So unfortunately, a phonon is a dynamical quantity, intrinsically speaking, while this theory is a static quantity because it's based on free energy. However, there is a case in which the excitation of the lattice can have a zero energy, so can be described by static theory, and it is when we have second-order phase transition, in which the displacive phase transition, in which we have a lattice excitation whose energy goes to zero and trigger a symmetry lowering of the system. And this can be computed with the static response function, which is related to the Hessian matrix of the free energy, which is not the same thing as the auxiliary force constant. And therefore, we can compute the Hessian matrix. And let's take, for example, the example of the perovskite I showed you before. This is the CSSNI3 perovskite in the harmonic phonon dispersion in the cubic phase. You can see we have imaginary phonons in this region, which means this phase is unstable at 0 Kelvin, which is common for many materials. And then if we do the simulation of the Hessian matrix at 250 Kelvin, we see a strong renormalization of all the bands. And as we increase the temperature, this soft mode starts increasing up to 450 Kelvin when finally it becomes stable. And we can therefore say that the transition temperature is of displacive kind and occurs between 400 and 450, which again is in extremely good agreement with the experiment, in which this occurs at 440 Kelvin. And however, the phonons we get, the band structure I show you, is good only to compute second-order phase transition. Again, those are not the real phonons of the system. Real phonons are dynamical quantity and must be computed with a dynamical theory, which is we can compute them as the poles of the dynamical spectral function obtained by the Green function of the lattice. And to do this, indeed, in the static case, in the case of frequency equals 0, the inverse of the Green function coincides with the free energy Hessian. So the theory match. But we need a dynamic theory to compute phonons. And this can be done with the time-dependent self-consistent harmonic approximation, in which instead of optimizing the free energy, we find a dynamical equation that makes the action constant, so that kill the derivative of the action. And we get this self-consistent equation, which is very close to self-consistent R3, so the time-dependent R3-Fock or time-dependent density functional theory. And if we take the linear response of this equation, we can get the Green function. And this can be done, for example, the details of these are done in this paper here, in which we show the implementation of a Langchos algorithm, which is similar also to what done in time-dependent DFT to achieve this. And actually, I can show you the results again in the perovskite, the cubic phase of the SNI3. And in this case, we see this is the spectral function, and you can see how this system actually is really an harmonic. This is not the logarithm of the spectral function. This is the spectral function. And so it's really broadband, and as you can see, all the phonons here mix one to each other. So in many cases, it's not even, we cannot distinguish even anymore which phonon is what and they overlap. And this is very important and relevant if you are studying thermal transport, for example. And there is a poster this afternoon by Giovanni Caldarelli, in which we talk more about this, and I think also the talk tomorrow by Michele Simoncelli, if you are interested. We can also plot the same quantity, that is a spectral function, resolved mode by mode to have an idea on understanding what is happening and why this spectral function is so broad. And you can see a lot of satellite peaks, and this is very, very interesting by itself. We can also use the same technique to actually compute Raman spectrum, infrared spectrum, which has dynamical quantity. And here I'm showing the hydrogen Raman spectrum of the phase 3 at 250 GPa, and the comparison between the harmonic approximation, the auxiliary frequency you get from the self-consistent harmonic approximation, and the full time-dependent self-consistent harmonic approximation result compared with the experiments. And as you can see, if you don't fully account these dynamical properties, you miss an important shift. This is completely non-negligible, almost 50% of the energy, which is relevant if, as in this case, Raman spectrum is used to determine which structure correspond to each phase, because hydrogen at these high pressures is very difficult to probe with other techniques. And this work has been done by Antonio Siciliano, who will present a poster tomorrow. So if you have more questions, you can go and see his work directly. So these are my conclusions. So I hope I convinced you that the self-consistent harmonic approximation is a very good way of computing free energy and its derivatives, and to calculate phase diagrams and thermodynamic properties. And this presentation comes with a big warning for any of you that are working on phonons, that if you use this approximation, be careful that the eigenvalue you get from these auxiliary Hamiltonian are not the real phonons, but they must be corrected. And the real phonons can be computed with a time-dependent extension of the theory. So the code to do this is all open source. It's available at this website, www.sschA.eu. And we are organizing currently a school about the code between 26 and 30 of June at San Sebastian. So more details are available on the website, and the full program will be uploaded in a few weeks, hopefully. And I want to thank all the collaborators that make this work possible: Francesco Mauri, Michele Casula, Nicola Marzari, Antonio Siciliano, and Giovanni Caldarelli. And thank you very much for the attention.
Thank you for a very interesting talk. Questions? No? Yes? Can you just pass the mic back to me?
Thank you for your talk. It's really interesting. So my question is that how would you estimate the error bar for your energy from the shell and compare to the thermodynamic integration method? Thank you.
Okay, so this is a very nice question. Actually, in this case, the error bar is present, but it's not visible. So it's present in the problem because the dots are bigger. So you can see a bit there, here the error bars. And we have two kinds actually of error bars. So this is a stochastic method. So we are sampling this average through a stochastic approach. So we have a trivial error bar, which is given by the fact that we have a finite number of configurations. And this is trivial to estimate, and is provided by the code at the output as an error, and is what is plotted here. Then there is a second error, which is more difficult to estimate, which is what is actually the error of the approximation. And I mean, it's very difficult to guess it, and I don't know actually how to answer to this question. The point is that what you can do is to try to not describe just one quantity, since after one simulation you get a full thermodynamic description, you can compare with other quantities, and then see if some of these quantities are known experimentally, how they compare, like in this case. So we have other phase transition that we know where they are, and so if there is a very good agreement, then it's very likely that this is a good approximation.
A curiosity, when the temperature goes to zero, your free energy goes to zero, you have a residual quantistic zero.
You have all the quantistic effects here. So it depends on so in this case, this is a free energy difference. So, it's just, but you have all quantum effects. So here I've not shown this, but if you go to very low temperature, you see in this material, quantum effects at this temperature are not so relevant. But for example, in the case of hydrogen, they are. I mean, this is all quantum, here the effects are all quantum effects. And you have, I mean, if you do, for example, thermal expansion, you see that up to the Debye temperature, the volume remains almost constant and then goes up, and all the thermodynamic properties reflects this approach.
Any more questions? Okay, so let's thank the speaker again. Okay, so we now switch topics to spins and magnetism. And the first talk will be by Antimo Marazzo of the University of Trieste. And the title is Digital 2D Spintronics with Electric Dipoles, from spin FETs to ferroelectric topological insulators.
Can you hear me? Yeah. So thanks for the introduction, and good afternoon to everyone. Let me just thank all the organizers for inviting me here today. It's really a true honor and a great pleasure. What I would like to talk about is actually two different projects. The first one will be about modeling novel 2D materials as with strong Rashba-Spinobit coupling for spin field effect transistors, while the second one will be about these ferroelectric topological insulators. But these two projects, as you will see, they have actually a lot in common. And they are, in a sense, two different ways to achieve control of the electron spin, so to manipulate spin currents in a digital way. So we will just see that we need to care about the sign of a gate voltage. So everything is either black or white, 0 or 1, yes or no. And with this digital control, we can realize kind of spintronics, or probably I should say spin-orbitronics devices made of 2D materials. And the way we're going to do this in both cases will be exploiting, hopefully in a smart way, the presence of very, very strong electric dipoles. So spintronics has been around for a while. I think the field is a little bit gigantic. So today we'll be concerned with two basic concepts that you see here. The first one will be the spin field effect transistor, as it has been put forward by Dat and Das more than 30 years ago. And the other one is the concept of topological insulators. So the spin field effect transistor is actually a very simple concept. You have a spin current that is injected through this ferromagnetic contact here, and that goes into a two-dimensional electron gas, which is in presence of Rashba spin-orbit coupling. Now, in order to have spin-orbit coupling in an electron gas, you need to break inversion symmetry. The way you do this is through an external out-of-plane electric field, which is driven by this gate voltage here. Okay, so with this gate voltage, you control the amount of Rashba spin-orbit coupling you have, and because of Rashba spin-orbit coupling, the spin in the electron gas precesses. So there is a precession here in the channel. And then at the end, you put another ferromagnetic contact. And then depending on the relative alignment between the spins, you can have different output signals, OK? And all of this can happen because electron gas with Rashba interaction has this very nice band structure here with the rich spin textures, with the spins winding around the center of the valley. Okay, and in principle, you can control the rate of precession with the gate voltage. Okay, so this seems very interesting, but still we don't have a data spin FET in our pocket. Okay, after 30 years, and in fact, it might be actually a little bit naive proposal, and there are many problems associated with realizing this device. The one that I think is one of the most important, I think, is that you in principle would need very large electric fields to basically control this rush. To induce a Rashba effect, okay? To have relative short channels and a device that you can consider to be sufficiently small, you will need exceedingly large electric fields. And to me, the situation changed radically about 10 years ago when people like Arthur Freeman, Alex Zunger, Zhang, Liu, and Luo realized that actually what was essential to make progress in this was there just in front of us, but we were blind to it. We couldn't see it. And in fact, they call this effect the hidden spin polarization. And I'll try to explain you this mechanism, which is astonishingly simple and yet rather important. So as I said, to have Rashba spin-orbit coupling, you need to break inversion symmetry. And people used to think that that meant breaking the global inversion symmetry, okay, so in terms of the space group. But they realized that actually spin-orbit coupling is a local effect, is an atomic almost effect. So you only need to break inversion symmetry locally, okay, from the point of view of the point group. So you can have a situation where you have a centrosymmetric material with strong dipole fields that compensate each other, okay? And these two components lead to doubly degenerate bands that have opposite spin polarization. So you can have strong Rashba bands, but they are doubly degenerate, and the polarization sort of cancel each other, okay? And these two states are localized on one of these two separate sectors that you see here, forming the inversion partners. And in their work, Zunger, Freeman, and others not only proposed this idea, but they also made a list of materials. And this is one of their materials. It's made of lanthanum, oxygen, bismuth, and sulfur. And you see that it has a strong Rashba split band structure, both in the conduction and valence band. And it's doubly degenerate, so you have opposite spins. I think they use the green and orange color that are they compensate each other, okay? And about the same time they proposed this, actually they also realized that you can use this effect, this kind of materials, to substantially improve the original proposal about Dat and Das, okay? And you see it here. Now, you have this strong Rashba split band structure, but you cannot use it unless you break really now the space, the global inversion symmetry, and you do this now with a gate voltage again. But a variance with the original proposal by Dat and Das, now the strength of the Rashba spin coupling is entirely given by the internal intrinsic electric field that is in the material, which in this case is very strong because essentially this material is made of by portions that are bound together by ionic bonding, okay? And now with this external field, you just break the degeneracy between these two Rashba bands, okay? You see there is a splitting in energy, and you can select which one of these two hidden spin polarization you want to use when you dope the material in this field effect transistor. So now here I try to show this in more general terms. We take, again, this simplified model by Dat and Das, but now our 2D material, which is this type 2 Rashba materials using the nomenclature by Zunger, has a strong Raspberry coupling, and we just use this gate voltage to split the degeneracy and, and decide whether if you have a positive gate voltage, one of the two spin textures goes up in energy, and if it's negative, the voltage goes down in energy. Okay? So we can select which one of the two we want to use. Okay? So we want these centrosymmetric materials. We want them to have local dipoles, and of course, we want strong spin-orbit coupling. And so what we did was actually to try to search for other materials like this. Okay? So we screen our database of easily exfoliable two-dimensional materials, and our best shot was this candidate here. It's made of lutetium, iodine, and oxygen. Okay? It comes from an experimental parent compound, so it's a structure that's supposed to exist. What we calculated with simulations is first that it's easily exfoliable. It has a binding energy that is actually slightly lower than the one of graphene, so we really think this should be easy to isolate it as monolayers. Okay? And it has a very strong Rashb effect. Okay? Just to give you a feeling how strong this number is, if you want to convert this into a simple, with a simple-minded calculation into a, how much distance it takes for this electron to flip the spin by 90 degrees, it would be of the order of, let's say, 1 nanometer, just to give you a feeling. And this is the lowest conduction band. You see, there is a strong Rashba splitting. This is valley number 1 that I'm talking about. And why is there such a strong Rashba effect? Well, you see here, this is the potential profile. There is a strong drop from the outer region to the internal region of the material. Okay? And here, there is basically a strong dipole. And there's another one here, and they compensate each other. And in fact, overall, the structure is centrosymmetric. Okay? And so this, as explained by Zunger and Freeman, this valley is doubly degenerate, of course. And these minima are localized. One is on the lower part of the material, and the other one is in the upper part. And now, of course, what we do is we put an electric field in the simulation. So we put an autoplane electric field. And as expected, what you see is that we break this degeneracy, and there is a splitting in energy between the two Rashba bands. But for the first time in the literature, what we did was actually to dope the material, okay, to do a real simulations with real electrons, okay, added. And this was possible thanks to the methodological work done by Thibaut Soyer in his PhD thesis with Matteo Calandra and Francesco Mauri, where he implemented the whole DFT and DFPT framework in a field effect double gate step. Okay? So not only now we put an electric field, but we also put electrons, we dope the material. And what we observe that the splitting, which is the fundamental quantity we want to optimize here, this energy splitting is actually reduced. So it's lower than what it would be otherwise without considering the doping. And this was not explained at the time, so we tried to understand a bit why this happens. And to do that, of course, we did first principle simulations, but we also did a very simple electrostatic model that you see here, where we have the top gate, the bottom gate that are represented as charge planes. And then we have the material that is also represented as charge planes, separated, two planes separated by the electric constant. Now we have this band splitting S, which is proportional to the internal electric field. And it's made of two contributions, this field. It's the screen external field due to the gates, and a sort of internal field due to these charge planes in the materials. Okay? Because these two Rashba bands, as I said, correspond to states that are localized in different sectors of the material. Okay? So once you start to dope it, the electrons don't go everywhere, but they just go on one of the two sides, basically. And in fact, this is what happens when you study the splitting versus this gauge charge difference, which is basically this external electric field. And this is done with dense function theory in the field effect setup. But if you study that also as a function of doping, you really see that the doping kills a bit the effect. And it's even more clear when you consider the slope of this quantity. Okay? There are two different regions, okay, separated, clearly separated here. And so it's actually easy to understand this in terms of the model. So if the doping is low and the electric field is sufficiently high, as I said, you just populate one of these two Rashba branches, okay? And so you have a strong contribution coming from a charge imbalance. You're just putting charges on one side. But then at some point, you start to add electrons. You start to touch and populate also the other Rashba branch, upper, which is higher in energy. And this effect is not there anymore, okay? So you add charge basically on both sides. And then you get to this other regime, we call it low susceptibility regime. And so this, of course, was useful to us to understand a bit the physics here. But it's actually also useful to derive optimal operating conditions for this kind of devices, okay? Because now you can do the reverse process. You can put constraints. You can say, I want the splitting to be larger than room temperature. I want my Fermi level to be in this position. You can put a number of constraints. And then you can derive what are the optimal values that you need to use to operate the device, so to basically set the gate voltages, okay? So this was what I wanted to tell you about this work we did on spin field effect transistors, and I will actually switch gear a bit, but still continue to talk about spin field effect transistors in a very different sense, as you will see. But now we will not discuss things in terms of a volatile effect, so we'll try to move to a more non-volatile approach, which is interesting for a number of reasons. We will not do too much anymore computation discovery, as I've shown you up to now, but I will try to move towards a materials design effort where we engineer an artificial heterostructures to have the desired functionality. And still, it will always be about this strong electric dipoles. And so now we'll talk about the second work we did on ferroelectric van der Waals topological insulators. So topological insulators are, there are many kinds of them these days. The first one to be realized in experiments, and actually among the first ones to be originally proposed in theory, is the so-called quantum spin-on insulator. And this is a topological phase that occurs in two-dimensional systems with time reversal symmetry, so they are non-magnetic systems. And they're described by this Z2 topological invariant. The invariant is trivial. You just get a normal two-dimensional semiconductor. And if it's non-trivial, what you get is this topological phase with helical edge states. You see them here crossing the bulk gap. And these edge states are actually spin momentum locked. You see you have opposite spins going basically towards opposite directions, okay? Now, these materials are interesting for applications because they have these properties here. For instance, the electron transport that occurs at the edges is low dissipation, or we expect it to be low dissipation because time reversal symmetry forbids elastic backscattering, okay? And then, as I said, these edge states are spin momentum locked, which is, of course, something very interesting if you want to make a spintronic device. And all these effects are robust because they're protected by the topology of the bulk electronic wave function, meaning that if you now start to consider disorder, impurities, vacancy, it doesn't change. And of course, since the very early days of the field, people try to come up with devices you could make out of these properties, out of these materials. The simplest device is always, you always think about the field effect transistors, and indeed people try to propose this very simple device. Here I'm just showing one of these many examples you could find in the theoretical literature, and here on the right-hand side, the experimental counterpart. The idea is very simple. You take these 2D materials that are topological, you put them under an autoplane electric field, and then if the field is sufficiently strong, you basically close the gap and reopen it in the trivial phase, okay? And so you can switch on and off the presence of these edge states that are potentially low dissipation and are spin momentum locked, okay? But the problem, or let's say the feature of this is that it is volatile, but what we want is actually to have a similar effect, but to be non-volatile, or to be a little bit more persistent. And if you want something non-volatile, well, you typically think about ferroelectrics, okay? So we wanted like a ferroelectric material that is a bit special because we want now the polarization direction to be coupled to the topological invariant. So for one direction, it is topological. For the other direction, it is trivial. And if you think for a second, or for more than a second, this is actually very unlikely to occur in a single bulk material, or if not impossible to occur. So the question was, can we actually make a non-volatile topological field effect transistor? And I think the question is yes. And today I will talk about our own work on the subject that goes back to my PhD thesis some years ago and then some later follow-ups. But I really want to mention that there have been also other independent related efforts all around the globe that kind of elaborated on similar ideas. And more recently, I see appearing more and more works on this, and advanced version. And so these ideas that we showed to you are gaining momentum. For now, it's only among theorists and simulation specialists, but I've tried to convince you that the ingredients are so basic, are so simple in general, that I'm confident that at some point in the near future, the experimentalists will start to pick up on this. Now, I said we wanted to have a ferroelectric TI, but it was not really it didn't work that way. It was the other way around. We were inspired to try to have something like that by an early work where we screened for novel quantum spin-on insulators with high throughput computational methods. And among the few candidates we found at the time, the worst performing, really the worst we got, was this material here, made of indium, sulfur, and zinc. That was terrible. It had a small band inversion, almost no indirect gap. But it had a nice feature that it was essentially made by two separate monolayers, okay? So it was a single 2D material, exfoliable from other layers, but still it was made of two sectors. One is indium sulfide, and the other is zinc sulfide. And what is interesting is that this material, if you consider that as a standalone material, is actually a ferroelectric. And so we started to ask ourselves questions like, what does it happen to the band structure if I now switch the polarization? Would it change? I mean, if it is just indium sulfide, of course it doesn't change, but now it's a different, there's an interface with another material. So we started to think about this, and at the end of this thinking, we actually came up with a revised version or a revisited version of the famous band inversion mechanism, okay? So for those of you who have never seen this, so the band inversion is what is basically driving most topological phases, okay? So it's actually very simple. There is two bands. They typically have different orbital character. It can be, let's say, an S-like band and a P-like band. For a number of reasons, being spin-orbit coupling or maybe just crystal field, in materials, they can be inverted. And now if there is spin-orbit coupling, what happens is that the degeneracy points are not there, so there is a band gap, okay? So overall, the system is a semiconductor, and it has these very peculiar band structures around Fermi level. What we did was actually now to assign these two bands not to a single material, but to two different monolayers, okay? One is associated to this monolayer, the other to this other monolayer. And now we put these two monolayers one next to the other, okay? And this is basically can occur thanks to van der Waals interaction. They just stay together. And now if there is spin-orbit coupling, well, you might actually open a gap and have this kind of inverted band structures that might lead to a topological phase. So this is interesting, I think, but you can do more than that, because now you can play with the nature of these two monolayers. And for instance, you can now take one monolayer to be a ferroelectric. So you consider the interface between a ferroelectric insulator and a trivial insulator. And now, because this is a ferroelectric with an out-of-plane polarization, depending on the side that you look at, you might have, let's say, different vacuum levels, okay? So actually, what is different is that the band alignment between these two monolayers. So in one case, if you consider one side, you might have band inversion, so you can have bands crossing each other. Or in the other case, you can have just a trivial semiconductor, okay? And this realized exactly what we were trying to achieve. You see, in one case, for one polarization direction, the system is trivial. In the other case, the system is topological, okay? So it has this non-volatility we looked for. But of course, we started with this ternary compound that was not good at all because it was terrible quantum spin insulator. So what we wanted to do was to optimize this. And so we took as our reference ferroelectric indium selenide, which is very well studied, is among the most famous, I think, two-dimensional ferroelectric that has the conduction band bottom at gamma, and we look for a partner for this. And we screen materials databases, not only our own one on the materials cloud, but also the one by DTU that you find online. And we tried to find a semiconductor that was compatible and had the top of the valence band at the gamma point, and it had to add the correct band alignment, okay, to show both trivial and topological phase, depending on the polarization direction. We'll show you the simple condition for this in the next slide. For the moment, I just show you the result of the screening. And I will not explain the details of this, but just to tell you that these are all partners, possible partners. The ones that have the solid bar in this window here are very likely to show this effect. And the message is, this is not rare, because in the end, we are starting from trivial semiconductors. I mean, they don't have to be topological themselves. They become topological when you put them together. And so this is, there are many candidates, and what I will show is what me and Marco Gibertini decided was best for us to show this effect. As an example, it was good for simulations, but definitely I think there are better combinations out there that waited to be found, and especially from the point of view of experimental work. But so what we decided was the optimal couple, it was indium selenide and copper iodine. Essentially because the copper iodine is lattice match, so simulations are easier to do, but also because they are both easily exfoliable. So we propose something that should sort of make sense to do in experiments. You see the two band structures here. And the condition that I mentioned before is that the conduction band of the indium selenide and the valence band of the other material needs to be closer. The difference needs to be lower than half the potential drop due to this ferroelectric polarization. But of course, things are slightly, first of all, it works. So when you do the real interface, you simulate with the FT, it works. You have, in one case, a 50 milli-electron volt band gap quantum insulator, which is ferroelectric, and the other case, a trivial ferroelectric. But things are more complex than what you would expect by just looking at the two monolayers isolated far apart. So in the trivial phase, you get the band gaps lower than what you would expect because there is a strong interlayer repulsion. And in the topological phase, the polarization is slightly lower. So now you get a material, a heterostructure, where not only you couple, you have different polarization direction with different topology, but you have different magnitude in the polarization strength, okay? And this is going towards the end. We wanted to understand a little bit why this happens, because spin-orbit coupling is, again, as I said, typically a local effect, while here the two bands sit on two different monolayers. And so we studied things like the band gap versus the interlayer distance. You see it increases a lot if you push together the two material. We built a simple Slater-Koster tight binding model inspired by a maximally localized Wannier function Hamiltonian to describe things in simple terms around the Fermi level. And you see, again, the band gap increases strongly with the interlayer coupling term that is present. And so what we understood at the end is that, yes, the gap is driven by spin orbit, but is mediated by the interlayer coupling, okay? So by the hybridization between the two monolayers. And if you look at the numbers, okay, you see here the gaps converge, or let's say saturate at some point to a value that is proportional to the strength of spin-orbit coupling. This mechanism is such that the strength of the spin-orbit coupling is almost entirely, or it can be entirely transferred to the band gap, okay? It's a very efficient way to open a band gap. So you can imagine materials where spin-orbit coupling is stronger, okay, because there are more heavier chemical elements, and you might find band gaps that are even larger than the one that I show. And 50 milli-electron volts is small for a semiconductor, but it's actually not so bad for a topological insulator. And finally, all what I've shown is resilient to the twisting angle. So you can, we rotated, we twisted the two materials, and the band structure is the same. So the effect does not depend on the alignment or anything like that. It's just about the band alignment between two materials. You need to have proper band alignment between a ferroelectric and a semiconductor. So this is what I wanted to say for today, and let me just acknowledge all the people who were involved with this. You see here Rong Zhang, Thibaut Soyer, Nicola Mazzari, Matteo Festrate, and Marco Gibertini, all these institutions who supported our work, and also Praise, who gave us basically the fuel to run all the simulation you've seen. And before I stop, two advertisements. First one is two posters. The first one is by Marco here. Where we discuss all this work we did together on this ferroelectric topological insulators, but also other work he did on a similar topic. And then there is another poster by Roberto Favata, PhD student here in Trieste, about how to calculate actually Z2 invariance when you have large supercells and disordered systems. And finally, with Maria Peressi, we might have still a 2-year postdeposition if you're interested in first principle modeling of 2D materials and interatomic potential based on neural networks. If you're interested, really drop me an email or just talk to me, but you need to do it today because the position is being closed. And with this, I thank you for your attention.
Okay, thank you very much. Question?
Yeah, thank you for your nice talk. I have a question concerning Rashba effect. I want to know if graphene can also be considered as a material that presents this effect, because its band gap presents this semi-metal behavior, or if there is a need to dope it in order to slightly open the gap and then be considered as presenting a Rashba effect.
So, but do you refer to the first way of doing the first way? So, let's say this one here, something like this. No, actually, I mean, you can't really use graphene to do this because you really need this special symmetry. You really need this type 2 Rashba material. So you need to have something centrosymmetric, and that would be okay for graphene. But you need to have these strong dipoles, okay? You see, it's this spin layer locking FET, that some people call it. It's really based on this. So you need to have, this kind of structures, okay? You cannot do this. In graphene, you can do other spin orbitronic devices, but they're not based on this idea.
Nice talk. So I was wondering exactly on the same thing. The bands showing the Rashba, are they iodine derived?
Are they?
From iodine?
Are they from iodine?
Iodine. Ah, yeah. So that's a good question.
You had this
LuOIO,
Well,
right?
yeah, they are located on iodine. Yes. So this purple dots here are iodine. This is lutetium. The green one and the red one is oxygen. Yeah. So they are located there. So yeah, we're likely they.
Yeah. So my question actually was, is there a role of the? So I guess they are the p orbitals of iodine.
Well, yeah. I mean, I don't remember by heart all the density states, but
my question more precise is there any role of orbital degeneracy of the p's? I don't know what was the crystal symmetry.
Well, I mean, in a sense, yes. It's all about the side symmetries. You need to have the correct side symmetries to show a Rashba effect. So you can, for instance, what you could do is you could screen materials without doing explicit calculation, but just looking at the side groups and thinking about what are the right side groups.
The reason I am asking it, because recently there have been papers which actually show that if there is an orbital degeneracy, so then actually there is, these crossings are more like anti-crossing, and the Rashba effect can be very severely enhanced.
Okay, no, that might be very interesting. We did it, the hard way. So we just actually look for the strongest. Actually, what we did was we didn't look for this type 2. We really looked with Rang Zhang, who did the screening. We really looked for the largest Rashba splitting we could find. And it happened that the largest splitting we could find corresponded to a material that was centrosymmetric. So actually, it was really serendipitous, so to say.
You can just pass it.
Thanks for the nice talk. You might have mentioned it and I just missed it, but what functional did you use?
Okay, so whatever you have seen up to, let's say, up to here is DFT in sort of standard PBE, GGA.
Yeah.
We have done a DFT plus U calculation to check that the F electrons don't really interfere for this part of the talk. In the next part of the talk, we actually have done also, I mean, what I've shown is just DFT and of course, van der Waals, non-local van der Waals functional to get the equilibrium structures for the heterostructures, but we also done, just give me a second. Yeah, we also check what happens if you consider hybrid functional G0, W0. The situation is actually complex for this heterostructure in the sense, in one line, if you do things with hybrid functional, you still see this in the sense that you still get a topological heterostructure in one case and not in the other. With GW, we couldn't do the full heterostructure. We could not afford it. We did just the isolated monolayers, and there, actually, you would not see, GW would not predict, to have, a topological, say, phase. The problem with this is that if you want to study heterostructures, you don't really want to use things like G0 B0, because you lose all this, all the charge transfer, all of that would remain at the DFT level, okay? Because it's just one shot. So we prefer actually to do hybrid functionals here, because at least you consider all this charge transfer, all these self-consistent effects.
Right, thank you.
I forgot who it was. Okay.
Hi, thank you for the nice talk. So my question is, when you were talking about the twist angle and robustness to twist angle, if I understand correctly, you kind of got a few snapshots of one that were computationally tractable.
Exactly.
Which probably don't have very long Moiré length scales. I was wondering if there's a way to show it's tractable at I mean, I know I do DFT,
that's a very good point. So let's say, in this specific case, we think there is no problem because they are lattice matched. So the idea is that, if they are lattice matched, there shouldn't be any real moiré. Of course, if you rotate things, I mean, anything can happen. But, I would say I don't expect any moiré physics to occur here. But in general, if you consider general heterostructures, of course, there can be moiré, and that can change a lot. I mean, topological heterostructure, superconducting heterostructure, it changes the entire physics. But what is nice about this is that the band inversion is at gamma, as in this case, by the way. We actually think that even if there is some moire, I mean, of course, it depends on the numbers, but I would be confident that even with some moire modulation, some moire patterns, the effect should probably be there. So it should be at least, I think, more robust than the moire strength.
Okay, thank you. I think in the interest of time, we'll conclude this session. Thank you, Antimo. And I thank both speakers for sticking to time. And we'll now break for tea, and we'll come back at 3:40.
Thank you. Oops, sorry, I need to switch this off. How to switch this off? Check.
Okay, so welcome back to the last session of this afternoon, before the posters, obviously. My name is Ralf Gebauer. I'm here from ICTP, and I will chair this session. And we continue with the topic we have already started, meaning magnetism and spins and all this. And we are very happy now to have Sophie Weber from ETH in Zurich. And she will talk about surface magnetization in antiferromagnets from symmetry considerations and first principle calculations. Please.
Thank you very much for having me. So today I'll be presenting some of our most recent results from DFT on surface magnetization in antiferromagnets. So since I'll be talking about antiferromagnets or AFMs for the next 25 minutes, I'll first remind you from a big picture level some reasons why they're interesting, or at least for our purposes, why we care. So in the field of spintronics, traditionally ferromagnets were the material of choice, and this isn't surprising because they have a bulk magnetization that can be measured by direct methods in a lab and manipulated with external magnetic fields. However, more recently, AFMs have emerged as an alternate material in spintronics. Even though, by definition, they have a vanishing bulk magnetization, they still have a bit-like quantity, the Néel vector or staggered magnetization, which can be serve as a bit-like quantity to store information and can be manipulated and read out indirectly, for example, by anisotropic magnetoresistance. If we want to go back even farther, for many decades now, AFMs have been a key component in the read heads of magnetic recording devices where a phenomenon called exchange bias is leveraged, whereby the exchange coupling between an AFM interfaced with a ferromagnet fixes the direction of the magnetization of the ferromagnet. So AFMs are already useful. The presence of surface magnetization enhances this utility. So as I said before, AFMs have zero bulk magnetization. However, this does not preclude the possibility of for bulk AFMs with certain symmetries and surfaces with certain symmetries, which I'll get into what I mean by that later. It is possible to have a finite magnetic dipole moment per unit area on the surface, which I'll call surface magnetization, because it's easier to say. This is easy to see for the 001 surface of chromia, which is a prototypical AFM, which I'll be focusing on for the first part of this talk. So you can see just by virtue of cleaving the surface and introducing a vacuum, you get this ferromagnetic layer of chromia spins. And one of the cool things about surface magnetization is that it is a directly detectable probe of the AFM domain state because the direction of the surface magnetization is directly connected to the bulk underlying AFM domain. So in this case, if your moment is up, it corresponds to a bulk AFM domain with Néel vector +1. If it's down, you have a bulk AFM domain with Néel vector -1. So now you don't have to rely on indirect methods to detect the state of your AFM domain. And this surface magnetization is actually a quantity that can be measured in experiments. The most common method is nitrogen scanning vacancy magnetometry. It shows up in DFT. If you do a slab calculation or slab geometry of chromia in the 001 direction, you get the spin polarized state. And another application is thought to be an exchange bias, which I talked about before. So this was an experiment by the Binet group where they switched the direction of surface magnetization in 001 chromia, and when they did this, the direction of the exchange bias field shifted or switched signs. So it's not fully understood, but surface magnetization is believed to be connected to exchange bias. Now, magnetoelectric materials are a subset of AFMs which are particularly relevant for the case of surface magnetization. Just if anyone needs a reminder, for materials which have the linear ME effect, they must have broken inversion and time reversal symmetries in their bulk. And as a consequence of this, if you apply an electric field, you induce a bulk magnetization in the compound. Conversely, if you apply a bulk magnetic field, you induce an electric polarization. and the proportionality is governed by this linear response tensor alpha. Now, it turns out that the symmetries required for non-zero linear ME response are intimately related to the symmetries that are required for non-zero surface magnetization. And we can see this from kind of a qualitative picture by considering that an electric field and a unit vector normal perpendicular to a surface are both at their core just polar vectors. So in the presence of either of these polar vectors, we can expect the symmetry, the bulk symmetry, to be reduced in the same manner. So this has the consequence that if you have a surface whose normal is parallel to an electric field, we expect the surface to acquire the same magnetization components as the bulk if the electric field were applied in that direction. Another reason to focus on MEAFMs is that the direction of the surface magnetization can be controlled and manipulated via magnetoelectric annealing. So there's this term in the free energy of linear MEs that's proportional to the product of electric and magnetic fields times alpha, and since alpha switch is signed for opposite AFM domains, that means that by applying either anti-parallel or parallel magnetic and electric fields, you can preferentially select the state of the AFM bulk domain, and as a consequence, the direction of the surface magnetization. And this is in contrast to non-MEAFMs, where you usually need a prohibitively large magnetic field to switch surface magnetization. So in the cartoon picture I showed, looking at the 001 surface of chromia, it was relatively straightforward to believe me when I said that there was a non-zero dipole moment per unit area, because you just saw a layer of magnetic spins, ferromagnetic spins. However, there are more subtle cases where the reduction of symmetry by the surface actually leads to a finite surface magnetization, even when in the ground state it appears to be magnetically compensated. So, for example, in the case of -120 chromia, which is perpendicular to the 001 surface, if you look at the chromia atoms here, it appears that they're going left, right, such that this surface should have a magnetization of 0. However, and I'll go into it more, it turns out that the symmetry of the surface is such that an induced ferromagnetization is allowed once you create the surface, and this occurs by a canting of the surface moments. And this is also possible in non-ME AFMs and centrosymmetric materials. For example, iron difluoride, for a long time, people were confused about this material because it has a very large exchange bias when you interface the 110 surface with some ferromagnet. And if we look at the 110 surface, the in-plane iron moments look to be magnetically compensated, so there's no surface magnetization. However, again, because the reduction of symmetry at the surface causes these sublattices to become inequivalent, the magnitudes of the moments can change such that you actually get a net surface magnetization. So that's an introduction to this topic in case you are not so familiar with it. And this is the outline for the rest of the talk. I'll first give a straightforward group theory formalism, which allows you to identify bulk AFMs and their particular surface terminations, which allow for a finite equilibrium surface magnetization. And this has been developed in these previous papers here, so we're really just expanding on it a bit. Then I'll focus on chromia for the first part of the remainder of the talk. We'll look at the uncompensated 001 surface magnetization and its temperature dependence, as well as inducing magnetization on the -120 surface. And then we'll also quickly go into cases of surface magnetization in non-ME AFMs. Okay, so here's the procedure. So we're just going to focus on collinear AFMs for this entire talk. So at first, we have some AFM with a bulk magnetic space group. Let's call it G, and it contains the point group operations R, which may or may not contain time reversal, and the spatial translations. Now, let's consider a Miller plane with a normal vector perpendicular to this plane, and this is our surface of interest. And we want to see whether the surface has, we expect an equilibrium magnetization on it. So what we do is find the surface magnetic subgroup. And the way that that's defined is you consider all of the operations of the bulk space group G, which basically leave your surface normal invariant modulo translations, which are parallel to the surface, which I tried to depict here in this cartoon. And we exclude symmetries which involve translations perpendicular to the surface because our translational symmetry is broken in that direction. So once you have that subgroup, then we just consider the point group associated with that. So just the point group operations are in. And we just check, we can look up in Bilbao whether this group is compatible with ferromagnetism. There are 31 of these groups, and the definition is that if you act all of the operations on a magnetization pseudo-vector, at least one component is left invariant. And if the subgroup is compatible, it has an equilibrium surface magnetization. If not, it has no equilibrium surface magnetization. So let's work through some examples. So I'll go back to the case of chromia, which is a magnetoelectric material with a lot of interest in applications because it has a relatively high nail temperature of 300 Kelvin. So it has a bulk magnetic space group with broken inversion and time reversal symmetries, and the moments are polarized along the 001 direction. Now, if we look at, if we want to consider the 001 surface, we consider the operations which leave this surface normal invariant. And if you work through all of that, I won't go through the details, you get this magnetic point group 3. And if we look at what these 3 operations, these threefold rotations about 001 and the identity due to the magnetization components, the only thing that you have to pay attention to is that the MZ component is the only Cartesian component which doesn't switch sign under any of the operations. So this means that this surface is ferromagnetically compatible, and the ferromagnetism has to occur along the 001 direction, or the direction of ground state spin polarization. And indeed, there have been multiple experimental verifications of this roughness robust surface magnetization in 001 chromia. For the case of the magnetoelectric AFMs, there also exists a convenient bulk descriptor which we can use in order to give a quantitative estimate of the surface magnetization in terms of Bohr magnetons per unit area. And this comes from higher order terms in a multipole expansion of the interaction energy. If you have a magnetization density mu of r interacting with a magnetic field, and you do a multipole expansion, the first term is your normal magnetic dipole, and then the second order term, which involves a derivative of the magnetic field and a spatial component. The coefficient of this is called the magnetoelectric multipole, and because it breaks both inversion and time reversal symmetries, it's non-zero in MEAFMs. And there's a concept you may be more familiar with is in the modern theory of polarization, there's a elegant connection between the bulk electric polarization and the amount of charge on a surface, which is perpendicular to the polarization. And if you indeed look at the units of volume normalized polarization, it's charge per unit area. Analogously, if we look at the units of multipolarization normalized to the unit cell, it's 4 magnetons per nanometer squared. So analogously, we can say that this multipolarization tensor corresponds to the amount of surface magnetization we expect on a surface with surface normal parallel to I, the spatial component, and magnetic dipole parallel to J. So one of the reasons my advisor, Nicola, first got interested in this was that there's a surprising discrepancy between estimates of the 001 chromia surface magnetization using nitrogen vacancy magnetometry and what is expected based on this multipolarization expectation, where, I forgot to mention this, we just, rather than this integral form, we just, if the magnetization is fairly localized, you can approximate it with this point, assuming that you just have point magnetic dipoles centered at the atomic sites, and you sum over the magnetic unit cell. So this is what we're using. So anyways, what you get with theory does not agree with experiment. But when we got to thinking more about this, we realized this is not so surprising. you can, from a mean field argument, you can say that the temperature at which a given magnetic moment orders is roughly proportional to its effective Heisenberg coupling, which you can define just by summing over all of the nearest neighbor Heisenbergs for a given sublattice. So if you look in the bulk, based on our, so there's 5 nearest neighbors in chromia that are relevant, and based on our DFT calculations, this bulk effective J is around 40 millielectron volts. If we look at the electrostatically stable surface of 001 chromia, you see that a bunch of the nearest neighbors are just cut off. So by virtue of the termination, the effective J, even if we don't consider surface relaxation, is 2 millielectron volts, so more than a factor of 8 smaller. So it stands to reason that at room temperature around which the experiments are being carried out, the magnetization of the surface sublattice is going to be essentially paramagnetic, even if the bulk Néel vector is ordered. And this is what we get based on a Monte Carlo simulation, so this is an agreement. But we can still rescue this quantitative estimate using this multipolarization bulk quantity, as long as we just use a different basis. So as I said before, if you, to calculate it using this point dipole approximation, if we use the unit cell corresponding to the electrostatically stable surface, we get 12 Bohr magnetons per nanometer squared, give or take. However, remember we just said that the magnetization of the topmost chromia doesn't actually contribute at the experimental measurements. So a more appropriate basis in order to capture these surface magnetization is basis we get by taking this moment and translating it down by 1 C lattice vector. And if we recalculate using this, we get a value of around 2.4 Bohr magnetons per nanometer squared. And this is actually in quite good agreement with estimates from nitrogen vacancy magnetometry. OK, so that was the sort of intuitive case of surface magnetization. So let's go to the slightly more subtle cases. So I'll stay with chromia for now, and we'll go to a surface that is perpendicular to the 001 direction. So the minus 2 bar 0 has a surface normal, which is parallel to a 2-fold axis. And again, in the ground state polarization with the moments all directed along 001, this surface is magnetically compensated. However, if we look at the magnetic point group of the minus 120 surface, which is the point group 2 with just a 2-fold rotation, the magnetization component, which is left invariant, is the one which is parallel to minus 12y, which is the surface normal. So that means that ferromagnetism is allowed on this surface, and it has to occur by a canting of the moments along the surface normal. So this is all well and good from a symmetry perspective, but in addition to symmetry arguments, it would be good to see whether we could expect this to actually occur in a real material. So to that end, we did DFT calculations. These are constrained magnetic calculations in VASP using a slab of minus 120 chromia. So what we do is we fix the direction of the 2 center chromia layers along the ground state 001 direction, and then we cant the moments of the 2 surfaces with the canting angle defined with respect to the 001 axis. And even from a zoomed out picture, you can see already that this energetic parabola is asymmetric with respect to 0. And if we zoom in, the energy scale is really, really tiny, but based on multiple tests that I can talk about if you're interested. And we think that this energy lowering is real. So what this means is that this surface in DFT is stabilized energetically for a non-zero canting or induced surface magnetization of about 0.25 Bohr magnetons per nanometer squared. OK, so in the last few minutes, I'll briefly talk about extensions of this surface magnetization idea beyond ME-AFMs. So I talked about this group theory formalism before, which allows us to identify surfaces that are compatible with ferromagnetism, meaning they can have an induced surface magnetization. However, something I swept under the rug is there's a subtlety between cases which are roughness robust, meaning even in the case of surface roughness or atomic steps, the sign and magnitude of the surface magnetization stays constant, or roughness sensitive cases where you only get surface magnetization for an atomically pristine layer. And the way you can check which one you have is so once you have your surface magnetic point group, you go back and check whether in the bulk magnetic space group, the higher symmetry bulk magnetic space group, whether there are any operations that take the combined vectors, so the surface normal and the magnetic pseudo vector, and translate the surface normal perpendicular to the surface and switch the direction of the magnetization vector. If you do, that means that you have surfaces that occur on atomic steps that are symmetry connected or energetically degenerate, but they have opposite magnetization. So it'll average to 0 for a macroscopic area. If you don't have operations like this, so any operation which translates your surface normal to an atomic step, keeps the direction of magnetization, then, like the case of 001 chromia, you really have a roughness robust surface magnetization, which is more useful for device purposes. So an easy example of this more trivial case is the rock salt nickel oxide. So if you look at the 111 surface, just looking at it, you can tell me that there are ferromagnetic layers of spins polarized in plane. However, in the bulk magnetic space group, which is a type 4 antiferromagnet, so it has time reversal in its symmetry, you have a symmetry which is time reversal multiplied by a translation along the 111 direction. So that's just the operation that takes this moment to this moment. So what that means is that these two surfaces, which are symmetrically equivalent but have opposite signs of magnetization, will exist in the material in the presence of roughness. So 111 nickel oxide would not have a roughness robust surface magnetization. Okay, and finally, I'll go to the centrosymmetric case, and I'll go back to iron difluoride. In addition to its interest as a exchange bias material, it's also gotten some attention recently as a candidate ultramagnet, one of these AFMs which has spin splitting along certain directions of K-space. So it has a couple of cool features. But anyways, we can do this formalism again. And this bulk magnetic space group has inversion symmetry, but broken time reversal symmetry. And if you look on the 110 surface, again, the moments are polarized in plane and pointed along opposite directions. And it looks to be completely magnetically compensated. And if you go through the magnetic point group formalism, it's 2' M M'. You go through all these operations. The one that I've underlined, the MY component stays invariant. And in the basis of this point group, Y is parallel to 001. So this surface is, again, ferromagnetically compatible. And the component is allowed along the 001 bulk direction. So this is in contrast to chromia, where the ferromagnetism was induced by a canting away from the bulk ground state direction. In this case, the iron moments have to stay aligned collinearly in the 001 direction. And the only way that you can get a finite ferromagnetism on the surface is by the magnitude of the moments becoming inequivalent. So we want to check this again in DFT. So these are not constrained calculations. These are just self-consistent calculations neglecting spin-orbit coupling. We don't need it. We're not checking canting. We're just looking at moments magnitudes. So this is a slab of 110 iron difluoride. And all we do is look at the projected site-projected magnetic moment as a function of layer for iron difluoride. And we look at the two inequivalent iron sublattices, center and corner, refer to the positions of the sublattice in the bulk unit cell. And they're not the same. The key takeaway is if you sum up the sublattice moments to get the total magnetization per layer, in the center of the slab, it's roughly 0, whereas for both surface layers, you get a non-negligible magnetization of about 0.014 magnetons. So it's very small, but it's there. All right, so that comes to the end of my talk. In summary, I presented a group theory formalism which allows you to distinguish identify AFMs with surface magnetization and distinguish between these different cases: induced, uncompensated, roughness robust, roughness sensitive. We've talked about the case of 001 chromia and how in the case of ME AFMs, you can describe or estimate the quantitative value of surface magnetization by a bulk multipolarization, as long as you account for temperature dependence and use the right basis. And we've also shown through DFT calculations that in agreement with symmetry expectations, the creation of a vacuum-terminated surface means that if it's that you get a stabilization if you induce a non-zero magnetization on these surfaces. And overall, I guess the key takeaway point is that this surface magnetization is probably more ubiquitous than I think a lot of people realize, even though it's a concept that has been studied for a long time. It's kind of on the back burner. And I hope this influences people to study it more. I'll just acknowledge first and foremost, my advisor, Nicholas Bolden at ETH, Andrea Uru, who is also at the conference, and Shine Tikabel, who contributed with discussions and calculations, and also the materials theory group at ETH. Thank you.
Thank you very much, Sophie, for this nice talk about surfaces, symmetries, magnetizations. Yes.
Thank you for the very nice and interesting talk. I had one question about the terminations of chromia surfaces.
Yes.
Especially, you've shown in case of disorder that there's a different termination of the surface. I'm wondering if you consider if there are why this specific one?
About, you're talking about this.
Yes.
Yeah, sorry, I didn't explain this properly. The experimental termination of chromia is known to be the one on the left-hand side. So this, I mean, there are some controversies about the possibility of some disorder, but for sure, with electrostatic arguments, this is the electrostatically stable surface, and this surface does not occur naturally. The point is that when you calculate this multipolarization, what you do is you take, you choose a bulk unit cell, and if you take this bulk unit cell and tile it periodically, when you cut it off at some point, that sort of defines your surface. So it's basically the basis that defines the surface termination. So you have to choose this bulk unit cell, and you choose that according to the surface termination. And if you use this bulk unit cell, which corresponds to the actual termination, you get a magnetization that is much larger than what is found in experiment. This is only just a theoretical construct. So this is, all I'm saying is that this is the bulk unit cell that is more appropriate to calculate the experimental surface magnetization at room temperature, because at room temperature, this magnetic moment is disordered or essentially paramagnetic. Does that make sense?
Just very short, but the calculation is done for a bulk or for a slab then?
The calculation is done for a slab. Yeah.
Okay, other questions? Yes.
Thanks for the interesting talk. I have a question regarding to when you construct the different magnetic configurations for the surface state. Like you have this, especially when there's some of them, they're canted. I was just wondering, how did you consider if there are spring correlations, or when you do calculate the energy, would you allow for relaxation of these spin states? Because
you're talking about the this slide here?
Yeah, for this one.
So you're asking whether I just relax, rather than doing constrained calculations, relax the material and see whether I get, or see what I get, basically?
Yeah, I think especially for this one, because I'm just curious about when the spins they're pointing to different directions, and then how did you consider the property would have different size or a different effect between its size, because the orientation of the spins they're different, and how this effect taken into consideration?
sorry, I'm not quite sure I understand your question. So this, so for sure you're right, the energy changes as a result of, you get canting and you get this, you get Cialo-Shinsky, Moria interactions and such because the spins in the center are still pointed towards 001. But I guess we didn't worry about sort of the different spin correlations that were affecting the energy change. All we wanted to see is whether the energy lowered if we induced a magnetization on the surface.
So just one last quick, just make sure. So all these spin directions, they are fixed, right, during your calculation?
They're fixed, right, yeah.
Okay. Thank you.
Okay. Anyone else has some question? No? Okay, so thank you very much again. Okay, so this is set up. Okay, so the next talk, again, about magnetism is by Anita Halder from Trinity College in Dublin. And the topic is tuning the magnetic anisotropy at metal molecular interfaces. So please.
So good afternoon, everyone. I am Anita Halder. I'm a postdoc in Trinity College, Dublin. The title of my talk is Tuning the Magnetic Anisotropy at Metal Molecule Interface. Let's start with thanking my advisors in Trinity College, Dr. Andrea Docchetti and Professor Stefano Sanvito. I also want to thank my collaborators, Shumanto and Professor David Oregon. Also, I want to thank the organizers here to give me the chance to present my work. Let's start with defining magnetocrystalline anisotropy. So it's basically described as the dependence of the energy of a magnetic system along some certain direction. That is the preference along some certain magnetization axis. So this is basically a pure relativistic effect and coming from spin orbit coupling. This certain axis is called easy axis. The easy axis can be in plane or out of plane, or that is perpendicular to the plane. And the perpendicular magnetic anisotropy is key ingredient in technological applications. For example, in permanent magnetism, memory devices, spintronic devices, and the design, fabrication, and characterization of outer perpendicular anisotropy have drawn lots of attention of scientific community. If you think about the memory devices, the recording density has been increased several order of magnitude compared to the first time when it was launched. And the efficiency, to increase that kind of efficiency, the two requirements are, one is you need high saturation magnetization, and also you need strong out-of-plane anisotropy. And actually, you can define kind of hard magnet, semi-hard magnet, or soft magnet, depending upon the value of its K1 and saturation magnetization. Now, you can see from this plot that most of these magnets are transition metal and rare earth intermetallics. The transition metal part is giving you the high saturation magnetization, while the rare earth part is responsible for high anisotropy. And they sometimes grown in thin films to enhance the anisotropy, perpendicular anisotropy. But with the film thickness, it is seen that there is a significant suppression in the out-of-plane anisotropy. So is there any alternative to tune that perpendicular anisotropy? What is about metal molecule interface? Organic molecules, they are already quite popular in spintronics. For 3D transition metals, if you consider their thin films, mostly the surface property dominates. And so if the 3D transition metal in its bulk form, if you consider its magnetic anisotropy, there is almost no anisotropy, or even if there, it's very small. Now, if you consider a surface, due to reduced symmetry, I mean, there is enhancement of perpendicular anisotropy. Now, what is about if you are putting some molecule on top of the surface? Actually, indeed, this works. And in last few years, there are lots of investigation along this direction. I just want to highlight few of them. This PRL paper, they actually talked about cobalt C60. They deposited cobalt C60 on top of HCP, they deposited molecule C60 on top of HCP cobalt, and they found enhancement in out of plane anisotropy. The same group, they also extended their study. They did it for another molecule, LQ3, and they also reported enhancement in perpendicular anisotropy. Then this paper, if you follow, they made a heterostructure of cobalt and graphene, and there is massive enhancement of the perpendicular anisotropy has been reported. Also, this paper, similarly, they reported these two molecules, C60 and LQ3, deposited on cobalt layers, and there are many more actually. The same thing, they made some heterostructure with graphene, cobalt, and heavy metal. And also the magnetic hardening, that is, you can strengthen the magnetic exchange interaction by putting non-magnetic organic molecule. So what is the scope of this work? So till the date, the studies are mostly based on the qualitative understanding between DFT and experimental findings. But to understand the correlation between interfacial magnetocrystalline anisotropy and molecule matter hybridization, a detailed analysis is required. So that can be done with a systematic investigation on model system. So in this study, to fill up this gap, what we did, we studied the modification of magnetocrystalline anisotropy of FCC cobalt thin films by putting different non-magnetic molecules. We used a simple model to understand the basic physics, and then also we quantitatively, from first principle DFT calculation, we calculated the modification for different prototypical systems. With that, I came to my results. At first, I'll start with a very simple system. Let's take the simplest molecule, probably benzene. Now, I considered 5 layers of cobalt, FCC cobalt, and I put a benzene molecule on top of it, and then I relaxed the system. I constrained the last 2 layers, and this is the geometry, as you can see. And then the first thing I wanted to see, what is the change in electronic structure if you put molecule on top of cobalt surface. So the black one here, in the density of state, the black one is for the bare cobalt. As you can see that the majority spin channel is completely occupied for all of them, but the minority spin channel is partially occupied. Now, if you put a molecule on top of it, this orbital, the DZ² orbital, is modified quite a lot. Spatially, you can see there is a formation of bonding anti-bonding state between CPZ and cobalt DZ² orbital. The anti-bonding states are mostly here, and they are spending over wide range of energy, and they are mostly DZ² character. And the bonding state are over here, and they are mostly cobalt PZ character. Next, we calculated the anisotropy energy. To calculate the anisotropy energy, we took the energy difference between total band energy difference between 2 different directions. And then we found that for FCC cobalt bulk, if you consider bulk, it has no anisotropy. Now, if you make some slab, we considered 5 layers. it shows negative anisotropy, that is in-plane anisotropy. And then upon molecular adsorption, the anisotropy is drastically reduces to minus 0.6 from almost minus 5.5. And in the next step, what I did, I removed the benzene molecule from here, and I didn't optimize the structure. This is some kind of a distorted cobalt slab, and I calculated the anisotropy again, and I found it became again in plane, very similar to bare cobalt. So that tells me that the drastic reduce in the anisotropy is basically due to molecule metal hybridization, and the atomic displacement of the top layer has a very minor influence. Next, we calculated the layer-wise anisotropy, and that can be obtained from that delta E SOC. You can calculate delta E SOC from the SOC matrix element, and if you sum over orbital, you will get the atom-wise value, and then you have to take like difference between two different directions, and that is proportional to your anisotropy of a particular atom. So if you see this plot, the red one is for bare cobalt, and you can see that for all the layers, for all the atoms, it has like negative anisotropy. So that is why in total, for bare cobalt also it prefers in plane. Now, if you put a benzene molecule on top of it, the atoms which are particularly connected to the molecule, they are showing an out of plane component. And some of the atoms in the second layer also, I indicated here, they are also showing out of plane anisotropy. So they are actually cancelling the in plane anisotropy of the inner layers, and as a whole, the total anisotropy is very close to 0 for benzene cobalt interface. Next, also we plotted the transition matrix element between different d orbitals, and if you see for bare cobalt, the strongest negative anisotropy is coming from dyz and dz square orbital, and if you put cobalt benzene atom on top of it, that quantity is going to 0. Now, to understand the basic physics, we model it in a very simple way. From second order perturbation theory, we can write magnetocrystalline anisotropy like this, where psi O and psi U are corresponding to occupied and unoccupied orbital. And then you can, actually they are promoting in plane or out of plane anisotropy. You can calculate it analytically. We consider our d orbitals, like the energy levels of the d orbitals in that way. Just I want to mention that since our majority spin channel always filled up, so we didn't consider it in our simple model. Crystal field split it in that way, which is very similar to what the result we obtained from DFT calculation. These two levels are degenerate. Again, these two levels are degenerate. We consider it in our model. And then if you calculate the total anisotropy, it is something like that. And the negative sign shows that already from our simple model, it shows in-plane anisotropy, which is coming from our DFT calculation as well. Now, when you are putting benzene on top of cobalt, what is happening? Due to hybridization, there is bonding and anti-bonding states are forming. Now, the anti-bonding states, now the difference between from this orbital to this new anti-bonding states are delta prime. Now, if you calculate the EMCA, it becomes this. Now, depending upon this value of delta prime, it can be positive or negative. Now, if your metal molecule hybridization is not that strong, it's very weak, then it will be like the total quantity will be negative, it will be in plane. But if you have a very strong hybridization, there is a chance of switching from in plane to out of plane anisotropy. Next, we kind of relate our calculated orbital moments with a simple model called Bruno model. What is Bruno model? So Bruno model basically relate the orbital moment with anisotropy, with total anisotropy. So the easy axis of magnetization coincide with the direction of maximum orbital moment. And this is exactly what we got from our DFT calculation. So if you consider the red dots here, these are for bare cobalt. And for bare cobalt, you can see that the in-plane orbital moment is greater than out-of-plane orbital moment, and that's why it prefers in-plane anisotropy. Now, upon benzene adsorption, the atoms particularly, which are attached to the molecule, they showed a sharp drop for in-plane orbital moment, and that's why they prefers out-of-plane anisotropy. Then we also compared the anisotropy obtained from Bruno's model and whatever we obtained from our DFT calculation. And it shows a good agreement, though there is some quantitative difference between bare cobalt, but for benzene cobalt system, the agreement is quite good. Next, after understanding the basic physics of metal molecular hybridization and how it is affecting the total anisotropy, we would like to study how the chemical reactivity of the molecule affecting the total anisotropy. So we considered a different molecule, COT, which is more reactive than benzene. So it has a larger hybridization, and that is reflected in the total density of state. If you see here, the formation of bonding and anti-bonding states is more distinct. So we should expect more effect in total anisotropy. So next, we calculated the total anisotropy, and I found that for COT cobalt interface, there is actually switching from in plane to out of plane. From in plane to out of plane. So this is because of the strong hybridization, the delta prime I was mentioning in my simple model, the delta prime is such that the total anisotropy becomes positive. And if you plot the layer-wise anisotropy, you will find the very similar thing to benzene, but here the magnitude of these 4 atoms which are connected with the COT molecule is has more value, like is much more than the benzene. Then I also plotted the the transition matrix between different d orbitals, and I found that this transition element between d by z and bz square, which was negative here and which became very small or 0 for benzene cobalt system. For in contrast to that, here it became positive. So totally, I mean, it's giving positive anisotropy. Next, I also studied how the molecular coverage affecting the anisotropy of the slab. So for that reason, I considered different molecules with increasing surface area. And I found the trend is very clear here. And especially if you consider the surface layer anisotropy of the top surface, then you will find that there is a in-plane to an out-of-plane switching. Next, I also studied the dependence of anisotropy of the cobalt slab thickness. For that, I considered different layers of cobalt slab starting from 3 to 10, though their magnitudes are oscillating, are different for different number of layers. But the trend is very similar for all of them. For bare cobalt, it has negative anisotropy. You are putting some molecule. There is some suppression of in-plane anisotropy. This is for one representative case, the layer-wise anisotropy for 8 number of layers, and this is very similar to the result I have shown you for 5 layers. Now I also studied for another facet of cobalt, HCP. And for HCP, in contrast to FCC, for bare cobalt slab has already positive anisotropy. So when you are putting molecule, it's basically when you are putting some molecule, you are basically adding adding the positive anisotropy. So it is basically enhancing the out of plane anisotropy. But the physics, whatever I described, it's coming from metal molecular hybridization. Then finally, I did some calculation for two metal molecular interface which are experimentally observed. The first one is C60 cobalt system. So for C60 cobalt system, I considered 4 different type of configuration, and I found this one is the lowest one. And if you can see from this layer-wise plot that again the atoms which are connected to the molecule, this atom, they are giving like out of plane component of the anisotropy, but with the varying magnitude, and that magnitude depends upon the strength of hybridization. So just to show, I considered 2 different atoms. One is with highest anisotropy and another is this one. And if you see their density of state for this atom, it shows clearly the formation of antibonding and bonding state. Whereas for this atom, this is, the hybridization is comparatively very weak. That's why it's very close to bare cobalt system. And next, I did it for another system, as I told, for AlQ3 and cobalt. And from experimental result, it has been reported that it favors out of plane anisotropy. And as you can see here, here also the atoms attached to the molecule, they are showing perpendicular anisotropy. And I have chosen 3 different atom just to show their hybridization, different kind of hybridization with the metal, with the molecule, and the strongest one is with the highest anisotropy. With that, I came to my conclusion. So I studied the modification of magnetic anisotropy of the thin cobalt films upon the adsorption of molecules. And the main physical phenomena responsible for the modification is cobalt digit square and carbon PZ hybridization. We used a simple model based on second order perturbation theory to identify the electronic transition promoting in plane or out of plane transition. And then we also showed that the suppression of the in-plane anisotropy depends upon the choice of the molecule, and as I showed that it can switch from in-plane to out of plane for COT molecule. And then there is a possibility to engineer out of plane anisotropy by increasing the molecular coverage. So, so we are preparing the manuscript. I think it should be online within 1 or 2 weeks. And these are my fund. I want to thank for the funding agencies and computational resources. And thanks for your attention.
Thank you very much, Anita, for this nice talk. Yes. Ladies first.
Thank you. Yeah, thank you for your nice talk. I have a question. You previously mentioned that you have constrained some bottommost layer of your cobalt. I just want to know if you have applied a dipole correction in order to obtain a correct absorption energy. And also another question is, as cobalt has 3D orbital, I just want to know if you have used the DFT plus U and which value of U have you used?
Okay, so for the first question, I applied the dipole correction, but then I also calculated the anisotropy, but I found almost there is no change. So I did it for one system, and then I just followed without any correction for other systems. And what was the second question? Okay, so cobalt is like moderately correlated. So for these calculations are GGA. I didn't use any U plus U correction.
Okay, I think Antimo had.
So thank you for a very nice talk. So my question is about the orbital moments. At some point you mentioned this Bruno model, and the fact that, and you show this plot where there is an orbital moment associated to each atom, right? Yeah, this one.
Yep.
So you are calculating a local orbital ionization, right? And the question is then, how do you do that? Because this is from DFT, right? So it's the DFT calculation which is behind the orbital ionization.
Yeah, I mean, I switch on the spin orbit interaction, and that will give you the orbital moment.
Yeah, so was wondering more if you want the formula for the orbital ionization, is it how do you define the fact that it's associated with that specific atom?
Specific atom. Probably I didn't get your question correctly.
So there is an orbitalization and then an atom index. So I imagine this is, each point is associated with specific atom,
but,
right?
I mean, when you are switching on the spin orbit interaction, you will get like the orbital moment per atom, like for each and every atom, like the way you get also the spin magnetic moment. So if you switch on the orbital spin orbit interaction, you will get also the orbital moment for each and every atom, and then that I just considered.
Thanks.
Okay, further questions? No, well, I have one myself. So when you put these kind of closed shell molecules like benzene molecule or C60 on the metal surface, then the strength of the interaction will depend very strongly on the level of theory you're using, if you include van der Waals or not, and all these kind of things, which will then, as a follow-up, change very much how strongly distorted your surface atoms and so on. Have you looked kind of at the influence of these things on your results?
I didn't look at the influence of this thing, but I found especially for HCP cobalt, I mean, there is strong effect of surface distortion. But for FCC cobalt, I mean, there is almost nothing. I mean, if you see this plot, yeah, this one, like I put the molecule and the surface atoms got distorted because of the bonding. Then I removed the molecule and I didn't optimize the structure, and I calculated the total anisotropy. And it is very similar to the bare cobalt. So it shows that the main reduction is coming from the metal molecule hybridization.
Yes, and then it would be interesting to see how strongly this depends on the surface molecule distance which you have there.
Yeah, that I did actually. Yeah. That I did. I don't have the result here, but that I did. I just shifted the molecule like from surface to.
Because I mean, this will depend very strongly, as I said, on what you use.
Yeah, I mean, like it goes from chemi-absorption to physi-absorption. You mean like?
No, but I mean, different functions will give you very different distances.
Okay, I didn't check for different functions.
Okay. No further questions? Okay, so thank you very much again. Okay, so we will now switch gear and move from spins and magnetism to quantum computing.
Okay.
But this is not your slides we are seeing.
Oh. No, but it should be.
Oh, strange. Are you sure you have connected it?
Yeah. Okay, I can reconnect it.
Well, anyway, help is on the way, so. and he will answer the question about what quantum computers can do for material science. And I very much hope that the answer will not be that all DFT people will very soon. Okay, so please.
Well, thanks for the introduction. And I would like to start by thanking the organizers for inviting me here. And so first, let me tell a few words about where I work. So I work in a private company, Atos, who traditionally sells high-performance quantum computers, the kind of computers where you run your DFT computations. And they have customers like you who want to understand whether they could get some help from having some quantum processors inside these HPC quantum systems. So in the quantum R&D lab where I work, the question we're trying to address is if and how we could make use of some quantum processing power inside supercomputing architectures. And in fact, last time I came to Trieste, I was on the classical side. So I was trying to solve material science problems with classical methods, and I kind of always run into an exponential wall. And as you all know, when you do strongly correlated physics, there is always an exponential somewhere. So if you do a diagonalization of your Hamiltonian or FCI techniques, there's an exponential in the size of the system. If you do quantum Monte Carlo, there's an exponential in size or in temperature or both. Or when you do tensor network techniques, there's also an exponential in the entanglement in your wave function. So whatever you do on a classical computer, there is somewhere an exponential, which doesn't prevent you from doing your computations. You always try to find smart ways to go around the exponential problem, but in some regimes of interest, you're stuck by this exponential sign. On the other hand, now, since a couple of years, we have first prototypes of what people call quantum computers. These quantum computers are physical experiments with, for instance, superconducting aluminum, with trapped ions, or with the electron of spins, which are trapped in quantum dots, or photonic circuits, or, for instance, Rydberg atoms, which are trapped. And the premise of these quantum computers is that since they have quantum physics inside, they should not have an exponential wall, because they have entanglement built in a way. And I put a question mark here, because what I will try to show you today is that indeed quantum computers do have some promises of some speedups compared to classical computers, but they also have exponentials somewhere in the form of decoherence, which kills the quantumness of the machine as time goes by. And that's a big issue today that people are trying to solve to make them helpful for solving strongly correlated problems. And so the outline of my talk is going to be in two parts. So first, I'm going to go more on the optimistic side, let's say, and try to tell you what quantum computers can do today to solve many-body problems. And then I will try to shed some light on some experiment that you've probably heard about. A couple of years ago, Google claimed they had reached so-called quantum supremacy, namely that they had done something that a classical computer could not do. And I will argue that their claim can actually be countered by using many-body techniques on a classical computer. So let's see what quantum computers can do for many-body problems. So as I said, quantum computers are just controlled many-body problems. They're more or less controlled. They're more or less open. But they're many-body problems, which means that from a theory point of view, what they realize is some strongly correlated problems. For instance, superconductors realize a Bose-Hubbard model. Trapped ions realize a spin boson model. A trapped spin in a quantum dot realizes a Fermi-Hubbard model, or in a low-energy limit, the Heisenberg model. And similarly, Rydberg atoms, depending on which levels you're looking at and how they couple to each other, may realize an Ising model or an XY model. And why am I doing this list of models? Is just to tell you that since they're synthetic many-body problems, they can explore exotic portions of large Hilbert spaces. And this is what you want to explore when you want to solve material science problems. And now I'm going just to introduce a bit of vocabulary about quantum computers. The building block of quantum computers is what is called a qubit. And a qubit is nothing more than a quantum two-level system, or a spin, which has a level 0 or level 1, which you may think of as level or as spin down and spin up if you want. And the key property of this two-level system is that it can be in a linear combination of the two basis states or in a quantum superposition. And when you put several of these qubits together, then the wave function can be decomposed, for instance, for 2 qubits as such. And you see here that if you have 2 qubits, you have 4 components to the wave function. And if you have n qubits, you have 2 to the power n complex coefficients, which makes it hard to simulate a quantum computer on a classical computer, because in principle, you need to store 2 to the power n complex coefficients, which of course you try not to do in practice. And when people say, I want to do some quantum computation, what they actually do is that they want to manipulate the state of their quantum computer by basically evolving the Schrödinger equation. And the degree of freedom they have in order to manipulate this state psi is just they are going to devise a clever h of t. So their Hamiltonian as a function of time is going to be what they change over time to reach some sought-after state. And at the end of this evolution, they can measure the state. And there's a second key property of quantum computers is that measurement is probabilistic, as you know, meaning that suppose you are in a state, in this superposition state, and you measure along the z-axis, then you're going to get, for instance, say, state 0, 1 with probability given by the squared modulus of the coefficient. So that's just quantum mechanics 101. And so you may have heard of quantum circuits. Quantum circuits are just a language to describe what your Hamiltonian as a function of time is or looks like. So for instance, if you see such a diagram, that means that you have here 5 qubits because you have 5 lines. So 5 two-level systems. And if a box here, which is called a gate, acts only on this qubit here, it means that the Hamiltonian it corresponds to is a Hamiltonian that acts only on the first Hilbert space. So it's basically, for instance, sigma x times identity. And for instance, if you see a gate here that acts on qubit 1 and qubit 3, it means that the corresponding Hamiltonian acts only on the first Hilbert space, first qubit, and the third qubit or the third Hilbert space. So that's what people have in mind when they see a quantum circuit, when they draw such a quantum circuit. And now there's an important distinction to be made, and that I will use throughout the talk, that the quantum computers that we have today in the lab look more like these boats here that may be in the Trieste Sea in the summer. So as you can see, it's a boat which is quite small and not very stable. And this is what quantum computers of today are like, meaning that they have a very small number of qubits, from 50 to 500. And they have what is called decoherence, meaning that a state which is in superposition, like 0 plus 1 over square root 2, which we could say is 0 and 1 at the same time, like Schrödinger's cat, becomes 0 or 1, or dead or alive, after a characteristic time, which limits the number of gates that you can actually run on your quantum computer. And in practice today, it means that you can run quantum circuits or quantum programs of 100 to 1,000 gates. And after that, basically, your state becomes classical again. So you've lost the quantum properties. Of course, that's not what you want. In principle, in the future, what people would like to have is more something like this. Which is a big machine, which is stable and large. And with these quantum computers with a lot of qubits and of good quality, what people hope to reach is do something called quantum error correction. Quantum error correction is a process by which you group qubits together so that when they are together, they're better than a single qubit, individual qubit. And this is shown in such a graph here, where here I plotted the logical error, which is the error of several qubits grouped together, versus the physical error, or the individual error rate. And you see here that when the physical error goes below a given threshold, so when your qubits are good enough, when you put them together, it actually helps. So when I put more physical qubits together, you see that the curves here go down. So the error rate is better. And that's a very important property, and that's actually the holy grail of today's hardware makers, is to try to have physical error rates which are below the error threshold. And then they know that when they group qubits together, they will be better and better, and even exponentially better, which is a very important property. But today, we're standing basically here in this region. So today, we cannot do quantum error correction. So what I'm going to talk about today is what one can do with so-called NISQ quantum computers. And the goals that I'm going to set for myself is, let's say I want to solve the electronic structure problem, and I'm going to write it in a second quantized formalism with a kinetic term, an interaction term, and if I have n orbitals, you see here that I have n to the 4 terms in my electronic structure Hamiltonian, which means that, roughly speaking, my Hamiltonian is a sum of terms with a number which is, roughly speaking, n to the 4 terms. That's what I'm going to start with. And what I want to do is find, for instance, the ground state of this Hamiltonian. And if I can do it, then probably I can extract some forces. And at some point, I would like to have access to excited states, to do spectroscopy. And I may also want to do dynamics, for instance. But today, I will mainly focus on ground state energies. And something that one would like to do with a quantum computer which has no errors, or which is error corrected, which we don't have today in the lab, is something called quantum phase estimation. Let me tell you a bit how this is supposed to work. So suppose we define a unitary function, exponential minus IH, where H is the Hamiltonian whose energy I want to find. And if I find an eigenstate psi of this Hamiltonian, this is also an eigenstate of the unitary, such that if I apply the unitary to psi, I find exponential of minus E, so that E, the energy that I'm looking for, is the phase, it plays the role of a phase. And now, if you want to find a phase in physics, what you do is interference, or interferometry. So this is a Young slit kind of diagram where I shine a light, and if the two, and here with my two slits, I dephased the two beams with respect to each other, and I can see an interferometry pattern on my screen. And now if I put several of them together, I see an interferometry pattern which is more peaked, so that I can have a more precise estimation of my phase. Well, what a quantum computer does, when a quantum computer does with quantum phase estimation, is precisely interferometry. And the circuit, the quantum circuit that is done in the quantum computer looks like this. What you do is that, so you have to think here, this is like this qubit 0 is like your light here that you start with, and you split it in two, like with two Young slits. So now the state after this gate here, which is not the Hamiltonian, but a gate called the Hadamard gate, then you're in a superposition state. Then you have a gate here, which is a controlled unitary. You don't really need to know what it does, but what you know is that after this gate, the state of your qubit here is 0 for the first ray of light, if you want. So this would correspond to this beam here, plus some dephasing times 1. So that would correspond to the second beam here. And then you apply, again, a Hadamard gate to have those two beams interfere with each other, as you would do in a Mach-Zehnder interferometer, for instance. And then if you measure here this qubit, the probability of getting 0 is going to be the famous interferometry pattern. Now, if you replicate this idea to a case with many of these slits, you have, in fact, more qubits here to do the interferometry experiment. And at the end, what you need to do is not a Hadamard gate, but an inverse Fourier transform, as we do in interferometry. What you read on the screen is basically the inverse Fourier transform of the transmitted intensity here. And when you read something here, what you will read is actually the phase of your unitary, which is the energy of your system. And when you do this procedure, you actually get an exponential advantage with respect to what you can do on a classical computer. Now, this is all good, but in practice, you cannot really do it on today's computers. There are many reasons for this. I can give you some. So first of all, you need to prepare an eigenstate to start this eigenphase estimation procedure, which is something which is complicated to do, because if you want to prepare an eigenstate, you need to know about it. Or you need to do an adiabatic preparation, for instance, which is a long process. And therefore, decoherence will probably kill your state before you have prepared it. Now, suppose you have prepared it, then you need to do these controlled unitary operations in the phase estimation procedure. And these basically give rise to very long quantum circuits. And they're too long for the coherence times that we have today. And finally, also, the Fourier transform is also an operation which requires a number of gates, which is incompatible with today's coherence times. So that's something that is very, very nice in textbooks, but we cannot really do today. So now I'm going to focus on what we can actually do today, which is something which is called the variational quantum eigensolver. It's not new. It's just a variational method. What you suppose you have is that you give yourself a family of variational states, psi theta. Theta are going to be my variational parameters. And I know that the matrix element psi theta h psi theta is larger than the ground state energy. So what I'm going to do is try to optimize theta in order to minimize this variational energy. And the way that I'm going to do it on a quantum computer is by having a combination of a quantum computation and a classical computation. I'm going to use my quantum computer to compute the energy of the quantum state. This is a good idea because a quantum computer is probably better suited to do this than a classical computer. Then I'm going to get my energy and find new parameters and so on and so forth until I converge my variational parameters. And the classical computer is going to give my new parameters. And so in practice, the way it works is that, let's say I start with some variational parameters. I prepare a state on my quantum computer using a quantum circuit with some parameters, which can be rotation angles, for instance. At the end here, I can measure some observables. And these observables are basically the observables which combined together give me my Hamiltonian. So these are the OI terms in my Hamiltonian. So there are n to the 4 of them if I have n orbitals. Then I repeat this measurement over and over again to get my averages. So there's here a statistical error that I'm doing. Then I combine the OI together on my classical computer. I get my energy. And based on the energy or its gradient, I can get new parameters and so on and so forth. So in principle, this is cheaper than a classical computer because the classical computer here, to do this, would require an exponential computation, at least in principle. So all I gain compared, so the good part of this method is that here I can choose my variational states such that it's compliant with the limitations of my quantum computer. So I can choose a circuit which is short enough that it can fit within the coherence time of my quantum computer. Then I can also be clever about how I initialize my variational parameters. I can pick an active space. I can do all the tricks that I can do in classical computations. I can also be clever about how I group the terms in my Hamiltonian. So for instance, if I know that some operators commute with each other, I know that I can compute them simultaneously, and so on and so forth. And so that means that today what we can do with this method is do first proof of principles computation for chemistry or material science on very small molecules that would probably make you laugh when you look at the size of molecules you can do on a classical computer. But nevertheless, these are proof of principles. And you can also do excited states with this method. And most importantly, these proof of concepts are starting points for more sophisticated methods that I will talk about a bit later. Of course, there are some downsides that, as always in variational methods, if you have too many parameters, you may get stuck in plateaus of the landscape, for instance. Here you also have an issue that you may have too much short noise in the sense that when you compute an average in quantum mechanics, you have a finite number of times that you do your measurement. And that means that you do a statistical error instead of getting the true expectation value. And also, probably, if you use a very short circuit to prepare a state, the state you're going to prepare is something that is not so interesting. It's probably not entangled a lot, because if you don't have enough time to entangle your system, the state you're going to produce is not entangled enough. So this means that today, this method is probably too slow to get something which is going to be competitive with classical methods, and also not enough accurate due to the intrinsic noise or decoherence of quantum machines today. But let me nevertheless give you a small example. So here, let's take an example. This is, let's say, a CO2 molecule, and I would like to have the energy landscape with respect to the bond length here and the angle here between the between the two bonds. I have my Hamiltonian, and here I know that the classical gold standard method for this type of molecules, for instance, could be coupled cluster with singles, doubles, and maybe perturbative triples. Now, I can turn this method into a quantum method by making it unitary, because since I'm doing a Schrödinger evolution, I'm always doing unitary evolutions on a quantum computer. And therefore, the ansatz, or the variational state that I'm going to propose, is something called unitary coupled cluster, which is basically a unitary version of coupled cluster theory. Now, that means that I need to prepare on my quantum computer a state, which is the exponential of these terms times the Hartree-Fock state, for instance. And then I'm going to optimize the parameter theta here. So there's a whole machinery how you do prepare those states. Then one thing you need to do is convert this exponential in a circuit. And for this, you're going to do a very simple trick that we know from classical theoretical physics, which is I decompose the t minus t dagger as a sum of operators, and then I approximate the exponential of a sum as a product of exponential. And for each term, I can then build a small quantum circuit. So this is something that people know how to do routinely today. The problem is it gives very long circuits. And so what people have come up with in the recent years is methods to reduce the size of the circuits without losing accuracy. And one example is an iterative technique where instead of having a variational state which is given from the onset, they grow the size of the variational state adaptively. And the way they do it is that when they want to grow the size of the variational state, the new operation or the new gate they add is the one such that the gradient of the energy with respect to the variational parameter is the largest, so that their gradient descent goes as fast as possible. And this can give quite reasonable results. Here are results we obtained in our group, where you can see here the ground state energy as a function of the variational iteration for several molecules, up to 20 qubits, which means 10 orbitals. With spin, it's 10 orbitals times 2. And so you see here that you can reach chemical accuracy, a couple of milli-Hartree, really fast with this kind of methods. And of course, I should warn you here that these are simulations without noise, so without decoherence. So it's all good in a way. Let me give you yet another example, which is another game that one can play in order to make the most of what we have today as quantum computers. So let's suppose I start with my electronic structure Hamiltonian. Of course, I have a freedom in how I choose the basis in which I write down this Hamiltonian. I can do a basis rotation from, let's say, the basis CQ dagger to CT the Q dagger. And this doesn't change my problem. It just changed the representation of the wave function and of the Hamiltonian. And of course, I can try to exploit this freedom because different bases have a different sparsity, and I can use it for my quantum computation. Why? So let's suppose the state I'm looking for in my original basis is 1, 1, or up, up. Let's suppose my new basis is C0 plus C1 over square root 2 and C0 minus C1 square root 2. Then the same state in this basis is written in this way. Now, if I ask you to build such a state on a quantum computer, this one is much easier than this one because basically you have more terms. So you have more gates in the circuit to build this one, which means that in one basis you have a very short circuit, so decoherence is not going to kill your computation. But in this basis, decoherence is going to kill your computation. So you'd better find the basis in which the way you write your wave function is the shortest. And there's a well-known basis to do this, which is the natural orbital basis, which is used a lot in quantum chemistry and in material science. This is the basis that diagonalizes the one particle density matrix. And so what you gain basically is that if you go to the natural orbital basis, you need shorter circuits, and therefore you need less coherence to build the state. Of course, it comes at a price. Probably the Hamiltonian expression in this basis is not as sparse as the one you had in the original basis, so there's no free lunch. But basically here, what you did is you put more burden on the classical computer and less on the quantum side. And this is the game that people are trying to play today. Try to adapt to the coherence they have on their quantum computer by adding more classical power. So it's really a game of hybridizing the two computations. And Another example of this hybridization of classical and quantum computation is, suppose you want to tackle a problem that I do not need to present here, which is the Hubbard model. One way would be to attack it directly on a quantum computer. Another more clever way would be to say, let's do some embedding method like DMFT or Gutzwiller or slave boson or any embedding methods or DMET, all the embedding methods you may think of. This kind of method allows you to do a mapping between the original extended model, which can be in the thermodynamic limit, to a model which can be called an impurity model or fragment, which is much smaller and therefore can fit on your quantum computer. And then you can solve this much smaller model and yet still a many-body problem on your quantum chip. And this is something we did in our group. And here, so as an example of results you can get is I plot here the quasi-particle weight, which is an order parameter for the Mott transition, as a function of the Hubbard interaction. At some point, what you expect is your quasi-particle weight to go to 0, which means we have gone from a Fermi liquid to a Mott insulator. And what you can see here is that this is what you can get on a classical computer, because here, of course, in this case, I can do this computation on a laptop. So on a laptop, I would have gotten this black line here. And what I get on a decohered quantum computer, so doing emulations, is these yellow points here, which, as you can see, are not perfect. They're far from the black line. But this is the best, more or less the best you can do today. So it gives you an idea of what you can do today if you tune your computation by doing some tricks. So this is the conclusion of part 1, which is the largest part of the talk. So today we have hardware and software progress. We have many variational algorithms and sophistications of them. But we don't have useful quantum supremacy. Yet, 2 years ago, or 3 now, Google claimed that they had reached quantum supremacy. And I'm going to explain in the 5 remaining minutes why, on the one hand, we have something which is not useful, and on the other hand, some people who claim, oh, but we have very powerful quantum computers. So just give me let me tell you what Google's game for supremacy was. What they did is that they took their computer, with 53 qubits, and they measured bit strings. So they measured the state at the end here of their computation. If they had a perfectly bad quantum computer, they would have gotten uniform bit strings. So basically, the probability of getting one bit string would be 1 over the number of bit strings, which is 2 to the power n, 2 to the power 53. So if they were to draw the histogram of their bit strings with a perfectly random quantum computer, they would have gotten a peak here centered at 1 over 2 to the power n. If they had, on the other hand, a perfect quantum computer, they would have gotten a distribution here called Porter-Thomas distribution. And the goal of their experiment was to understand how far the bit strings they had gotten out of their quantum computer was from the Porter-Thomas distribution. And to do this, they measured a quantity called the cross-entropy benchmarking fidelity, which we don't really know. We don't really care what it is. What we're going to see is that we can have a rough idea of what this quality is by just making a product of the quality of each of the successive operations that they did in their quantum computer. So here I'm basically doing a multiplication of the fidelity of each operation. So 2-qubit gates, 1-qubit gates, redot errors. And what I get here is a number which is 0.15%. So it should be 100% for a perfect quantum computer. So the quality of Google's results were 0.2% if I do a back-of-the-envelope computation. And that's also what they measured when they did their computation. Yet they claimed that with such a quality, which is not good, they had something which was much, much better than what classical computers could do. And the reason why they claimed it is that it's really hard to do a classical emulation of a quantum computation. The way people do it is usually, so there are many ways. One way is that you represent your quantum circuit as a tensor network. So basically, these tensors here represent these boxes here represent tensors. And you basically contract or multiply matrix with each other. And since the matrix size is exponential, these computations are always exponential. And some people have tried to catch up with Google, and the first estimations were we could do this in 2 to the point days. Then some people went to also 20 days, 5 days, a couple of seconds. So there were lots of attempts to reproduce Google's results, but they all had a flaw, which was that if Google were to add 1 qubit or 1 layer of gates to their computation, the time of these methods was exponential, because by default it's all exponential. So Google was right to say they didn't really care about these claims in a sense. So here, what we came up with is another idea, which is let's use the fact that entanglement is important in quantum computations. Or in other words, if I have a classical state which is not entangled, then it's very easy for me to do a classical simulation. Why? Because if I have a classical state, so a product state, or a Slater determinant if you want, I can always represent the tensor corresponding to the wave function as a product of the amplitudes of each of the Hilbert space states. And I can now try to refine this statement by saying if it's weakly entangled, then it's not going to be a product of potatoes, but basically a sum of a product of a few potatoes, which is called a matrix product state in the tensor network parlance. And I can also then, once I have a matrix product state representation for my state, I can try to compress it by reducing the dimension between these potatoes here, between these tensors. And this is the game that we played, and I'm going to cut to the final slide to tell you the final results, which are here. Here, this x-axis here is the compression that I do, or it's the inverse of the compression. So here I compress a lot on the left, and I compress not a lot here on the right. So here the computation is quite fast, and here it gets longer. And what you see here in gray is the level of noise, the level of quality that Google could reach. So my goal here is to go into the gray area. If I go in the gray area, then I won the game. And let's focus here on the dashed line, which is our best result. You see here that if I don't compress a lot, my average error per gate is 5%. And as I increase or decrease the compression level or increase the bond dimension in my tensor network, you see here that I can go into the gray area. And the time it takes me to get to this area is a few hours. So it's not the 200 seconds that it took Google to do the computation, so it's still more time. But my claim here is now that my method, since it's a tensor network method, it doesn't scale exponentially. It scales linearly with the number of qubits. So I can go to 200 qubits, and I can still produce samples, which are sampled with the same distribution as Google in a time which is comparable with Google. So the conclusion is that here, what allowed us to do the simulation of the Google simulator is that the entanglement level that they had reached in their quantum computer was so low that it was easy for me to do it on a classical computer with a tensor network computation. I'm not saying that this was an easy computation for us. We thought a lot about how to do this matrix product state representation and how to do it in a sophisticated way. But it tells you that today, what we learned is that with today's quantum computers, the level of entanglement that you can produce in the wave function is not high enough that you cannot do the same thing better on a classical computer. Yet, there is really steady hardware and software progress that makes us think that realistically, in a couple of years, I don't know how many, don't ask me, we will probably get to a point where for some parts of a quantum many-body computation, you could use a quantum processor to speed up some parts of the computation. And with this, I'll thank you for your attention, and sorry for the overtime.
Thank you very much, Thomas. Perhaps I abuse my position and ask the first question, because what is for me not clear is why, with these quantum computers, one can only do unitary propagations. Okay, because what we would like to do is e to the minus h times t, not e to the I h t.
Okay, so it's a very good point, and in fact, people have tried. So people have tried to do imaginary time propagation to get to the ground state. And so it does work on very small problems. The problem is that since it's not natural to do it on a quantum computer, since the evolution is unitary, you need to play games, or there are some tricks to do this imaginary time evolution. And this incurs an overhead, which is in fact exponential in the correlation length of the state that you're trying to propagate in imaginary time. So that by doing this kind of weird thing on a quantum computer, that is imaginary time evolution, you have to pay an exponential price in the correlation length of your problem.
I see.
So people are trying, and they have tried. there's another, you could do it in a slightly more sophisticated way by doing AFQMC type of computations, where you do an imaginary time evolution, but then you Hubbard-Swiatkowski transform your interaction term, and then you try to use your quantum computer to compute the overlap that you need when you do AFQMC by using a guiding wave function. And this is something that Google tried, for instance, and they claim that it works well. So there is a way, in a sense, to do imaginary time evolution, but it's more sophisticated.
Okay. Good. So questions from the audience? Oh. This is here exercise.
Thanks. Thanks for the very clear talk. I had a stupid question. So in the example of the Hubbard model, you plot z as a function of u. And for small u or even 0 u, the result is surprisingly bad. What is the bottleneck there?
Yeah, so it's a good point. So here, that's because we were too honest. So here what we did is a computation where we took the same variational state for all the different u's. Meaning that we kept a circuit with fixed length to do the computation for small u and for large u, which is too honest in a sense because we know perfectly well that for small u's, a very short circuit or a circuit which produces a state which is very close to a Slater determinant would be enough. And so if we had used the adaptive methods that I had mentioned just before, so the fact that we can grow the size of the ansatz in an adaptive fashion, then we would have a point which is really on top. So really the achievement of this method is the fact that for u equal 2, which is very close to the Mott transition, we get a point which is very close to the black line. But indeed, this is a very nice remark.
Okay. Other questions? Yep. Obviously on the other side of the room.
So thanks for the nice talk. I might have missed the point, but in the physical realization of the qubits, you say that you implement some kind of models, right? The Hubbard model, the spin boson. But the quantum computer should be universal in the sense that we want to solve, I don't know, superconductivity or the ground state. So is this possible? So there is an overhead in doing, in let's say, mapping one problem like the spin boson on the Hubbard model, or and what is this cost? I understand that you can interface your quantum computer with a classical computer that does this mapping. You do the simulation and you go back. What is the effective cost in doing this in your implementation and eventually in a real full quantum computer?
Okay, so it's a great question, and indeed it's something we have to solve before doing the computation. So for fermions, it's quite straightforward in the sense that fermion is occupied or empty, which is very similar to a two-level system. So the mapping is quite straightforward. The price to pay, though, is that a term which is local in a fermionic Hamiltonian is going to be non-local in the spin language or the qubit language because you have to pay for the anti-fermionic, the anti-commutativity property of fermions. So for fermions, it's quite straightforward, but you have to pay a price. For bosons, it's a bit less straightforward because bosons have several levels. So basically, if you want to keep, let's say, a number of 2 to the power m excitations for one bosonic mode, then you need m qubits probably, if I did the math correctly. So you can map a bosonic mode to several qubits, and you choose the number of qubits to basically match the highest number of excitations you think there are in this particular mode. But you can do it. And the difficult part is that there are several ways to do these mappings. So for instance, to map a fermion to a qubit, there are at least 3 or 4 ways to do this, and they have different properties, which basically the difference between these different mappings are, roughly speaking, visible in the Hamiltonian that you produce at the spin level. So for instance, if you start with a Hubbard Hamiltonian, you have only local interactions. If you use one of the mappings, you will have an interaction which becomes non-local. And if you use another mapping, which is called Bravik-Kitaev, for instance, then you have something which becomes logarithmically local. So it's local plus some logarithmic corrections. And this is something that also people are playing with to try and optimize. So this is also a big study, a big field of study also in this field.
Okay. Are there more questions? Obviously, we are on the other side. Anything more here on this side? I will not come back. No.
Very interesting talk. I had a kind of a naive question that I never really had straight in my mind. So I was under the impression that, and maybe also you touched on this, that if you had if you had a state and you wanted to propagate it in time, that clearly was something that was sub-exponential. But in principle, if you wanted to find the ground state of a general many-body Hamiltonian, then that was, you still had to pay an exponential cost, even if done on a quantum computer. Is that correct?
Yeah, that's correct. So that's more or less hidden here in the fact that when you do here your phase estimation experiment, there is a propagation here, u to the power 2 to the power m, which is exponential in time. So the difference is that if you do imaginary time propagation on a classical computer, you also have to do this on an exponential time to get what you want to get. But in addition, you have some sign problem, which is also exponential. If you, say, do AFQMC or Monte Carlo methods. Here, you have to pay the exponential price of the duration for which you're doing this run. But there's no sign problem because we're not on a classical computer. So that's maybe another important observation, that when you compare a classical computation to a quantum computation, what matters is the ratio of the run times for both. And this is actually something that people who do quantum computations don't show often. They say, oh, I did a molecule, but they don't say that with your laptop you can do this molecule in a much shorter time. So what matters is really the ratio and also the scaling of this ratio.
Okay, so thank you very much, Thomas, again. So this concludes the session of talks, and I remind everyone that we have posters very soon, in some minutes, in fact, and the posters are outside here, outside this hall and in the corridor around. And I feel that Nicola has something to say.
Yes, for those that don't have their own poster, please. You can pick them you can ask the guard to pick them up. There are still 5 people that have not taken the poster, so, okay, that's it. So, enjoy.